Welcome to the TensorFlow full course by Simplilearn. In this course, we will explore everything you need to know about TensorFlow and deep learning. So what is TensorFlow? Simply put, TensorFlow is an open source software library developed by Google that makes it easier to build and train machine learning models. It helps you create algorithms that can learn from data, enabling computer to recognize patterns and making decisions based on that information. We will start with an overview of Python and how to install TensorFlow on your system. You will learn how to implement deep learning using Python and dive into essential topics like probability and statistics. We will also cover CNNs with TensorFlow and compare popular frameworks like Pytorch, TensorFlow, and Keras. Additionally, we will provide a hands-on tutorial on the Object Decision API and explore the top 5 Python projects to enhance your skill. Get ready to embark on the exciting journey into the world of TensorFlow. Also, if you are looking forward to make a career in DevOps, definitely check out Simplilearn's professional certificate program in cloud computing and DevOps. This comprehensive course offers in-depth learning with a thorough understanding of cloud computing principles and DevOps practices, guided by expert instructors with real-world experience. You will engage in hands-on projects and real-world scenarios, building a robust portfolio that showcases your skills. So find out the course link from the description box below and the pinned comment. So without any further ado, let's get started.
So guys, let's start with TensorFlow. As you all know that TensorFlow is an open source machine learning framework which is developed by Google Brain's team. It's designed for building and deploying machine learning models with a focus on deep learning applications. TensorFlow offers a comprehensive ecosystem of tools, libraries, and community resources that make it easier to build, train, and deploy machine learning models across different platforms, from desktops to mobile devices and to the cloud. Now let's get started with the TensorFlow. To get started with the TensorFlow, let's first understand some of the features of TensorFlow. First of all, TensorFlow is a versatile and flexible library of Python. It supports a wide array of algorithms and it is adaptable to a variety of tasks. The next one is it has an ecosystem and tools. TensorFlow provides a rich ecosystem of tools that help researchers and developers to deploy ML models more effectively. And finally, it has a very good community and support. Now to get started with TensorFlow, you first need to install it. And this can be easily done using pip. You can use the Python package installer. You can install TensorFlow using the following command. But before that, let me give you a highlight what we are going to do. So guys, we are going to install TensorFlow. Then we will move with TensorFlow with NumPy, and then we are going to generate the random tensors. Let us try to complete this task. So for the same, we are going to use Google Colab. So guys, as you can see all over here, that we have opened the Google Colab. So this is a cloud-based IDE and it's a very wonderful IDE. I will also recommend you to use the same. Now let's get started. So first, what we are going to do, we are going to install the TensorFlow. So our first task is installing TensorFlow. So for the same, I have used pip install TensorFlow. Now let us try to run this. But before that, you have to connect it. So let it get connected. So as you can see, it has been connected to Python 3 Google Compute Engine. Now let us try to run this. So guys, as you can see all over here, that our TensorFlow is installed and we are installing it using the pip. Now let us move to the next part. The next step is importing TensorFlow as TF. So let us run this. Okay, now we have imported the TensorFlow. Let us move to the next step. Now in the next step, we are going to check the version of TensorFlow. So for the same, I am printing tf.version. Now let us try to run this. So you can see our version of TensorFlow is 2.15. Now we are going to use TensorFlow with NumPy. TensorFlow can be used similarly to NumPy for numerical computations. In fact, many TensorFlow operations mirror those found in NumPy, making it easy for those familiar with NumPy to transition to TensorFlow. Now here is an example of creating a tensor and performing some arithmetic operations. So you can see all over here, I have created a tensor with a equals to tf.constant and parenthesis, and inside that there's a square bracket 1, 2 and 3. Similarly, I've created a tensor B. Now, we are going to perform an element-wise addition. So for the same, I have taken the variable C all over here, and I am adding tf.add A and B. Now, what is this tf, guys? So remember this, we are importing TensorFlow as tf. So for the same, we are using it. Now, we are using a keyword called constant all over here for creating a tensor. Now, in order to perform the addition, I'm using the add keyword, and I'm adding these tensors A and B. Now, similarly for multiplication, I'm using tf.multiply and A and B. Now, let us try to run this. So, now guys, as you can see all over here, that when I'm adding it, it is printing tf.tensor579, and it's telling its shape is 3, and it is of data type integer. Now, similarly, if I want to check for D, so you can see all over here, it is going to print 4, 10, and 80 with of shape 3 and data type as integer of 32 bits. So we have completed this part. Now let us move to the next part. Now guys, in the next step, we are going to generate the random tensors. Generating random numbers is a common task in machine learning, and TensorFlow provides various functions to create random tensors. For instance, you can generate a tensor of random values from normal distribution or a uniform distribution. So for example, I have distributed a random tensor from a normal distribution. So I have declared a variable random normal and tf.random, and I'm using tf.random.normal, and 3 and 3 are the values, where mean equals to 0.0 and standard deviation I have put equals to 1.0. Now let us try to run this. So now let us try to print it. Okay, print. So you can see all over here, the tensor we are generating from the normal distribution is something like this. And similarly, if I want to generate a random tensor for a uniform distribution, okay, with minimum value equals to 0 and maximum value equals to 10. Okay, so these are the parameters that you have to remember. For normal distribution, it's mean and standard deviation, and for uniform distribution, you have minimum value and the maximum value. Let's copy this. Now you can see we have randomly generated tensor from the uniform distribution. The shape of 3 and 3 and data type is float. Now let us move to the next part. We are going to add a dimension to the tensor. In many scenarios, you might need to change the shape of your tensor by adding new dimension. And this can be easily done using the tf.expand dims command. Now suppose this is the code. So guys, you can see all over here, this is our original tensor, and it is declared with a variable tensor equals to tf.constant, and we are adding a new dimension which is expanded tensor equals to tf.expand dims tensor 0. Now we have added a new dimension all over here. So this is going to add a new dimension at a specified index, and it is going to transform a 1D tensor into a 2D tensor. Let us see. So we are going to print the expanded tensor. So you can see guys, I have printed the expanded tensor all over here. Now, let us move to the next part, that is tensor operation. TensorFlow provides a wide range of tensor operations such as reshaping, slicing, and mathematical operations. So here are a few examples. So guys, as you can see all over here, so I have declared a variable called tensor all over here, and then I'm reshaping a tensor, okay, with the given tensor that we have created, and I have also added its shape 3 and 1. Now we are slicing the tensor, so tf.slice tensor indexing 0 to 2. And we are also doing the mathematical operation all over here, which is a sum tensor, and we are reducing the sum to tensor. Now let us try to run this code and see what is our output. So you can see all over here that this is our original tensor with the shape 3, and reshaped tensor is something like this. So it has a shape of 3 and 1, okay. Now the slice tensor, you can see all over here that it is 1 and 2, and with the shape of 2. And sum of the tensor is 6, which shape is null. Now let us move to the next part. That is changing the data type of a tensor. You can change the data type of a tensor using tf.cast. This is useful when you need to ensure that tensors have the correct type for certain operations. So let us try to do this. So you can see all over here, guys, that I'm creating a tensor of integers. Okay. Then I'm changing its data type to float. So I'm using the word called cast. Okay. Now if I try to run this, okay, so print. So you can see all over here that it is coming 1 dot, 2 dot, 3 dot, and it has a shape of 3. Similarly, we are going to remove all the single dimensions. To remove all single dimensions from a tensor, you can use tf.squeeze, and this is particularly useful when you have tensors with unnecessary dimensions. Let me show you one. So guys, as you can see all over here, that I have created a tensor with a single dimension. Okay. Now I'm removing all the single dimensions all over here. Now this is squeeze tensor. So you can see now we have 1, 2, and 3, and we have shape 3 and null. So this is how we have removed all the single dimensions. Now moving ahead, we are going to move on one-hot encoding. Now guys, you will be wondering, what is one-hot encoding? Basically, one-hot encoding is a technique that is used to convert categorical values into binary vector representation. TensorFlow provides tf1.hot to perform this encoding. So here is a sample code for the same. Now you can see all over here that we have performed the one-hot encoding into the categories. Now we can see all over here that one hot encoded equals to tf.1 hot, and there is categories and depth equals to 3. Now and this basically has completed our objective of performing the one hot encoding on the categories. So this was our tensor basically, and here we have used the tf.1 hot for performing the one hot encoding on this given tensor with depth equals to 3. So guys, that was all for today's video. I hope so. You would have enjoyed our today's video on TensorFlow.
So what is deep learning? Deep learning is a subset of machine learning, which itself is a branch of artificial intelligence. Unlike traditional machine learning models, which require manual feature extraction, deep learning models automatically discovers representation from raw data. So this is made possible through neural networks, particularly deep neural networks, which consist of multiple layers of interconnected nodes. So these neural networks are inspired by the structure and the function of human brain. Each layer in the network transforms the input data into more abstract and composite representation. For instance, in image recognition, the initial layer might detect simple features like edges and textures, while the deeper layer recognizes more complex structure like shapes and objects. So one of the key advantages of deep learning is its ability to handle large amount of unstructured data, such as images, audios, and text, making it extremely powerful for various applications. So stay tuned as we delve deeper into how these neural networks are trained, the types of deep learning models, and some exciting applications that are shaping our future. Types of deep learning. Deep learning AI can be applied supervised, unsupervised, and reinforcement machine learning, using various methods for each. The first one, supervised machine learning. In supervised learning, the neural network learns to make prediction or classify that data using labeled datasets. Both input features and target variables are provided, and the network learns by minimizing the error between its prediction and the actual targets. A process called backpropagation. CNN and RNN are the common deep learning algorithms used for tasks like image classification, sentiment analysis, and language translation. The second one, unsupervised machine learning. In unsupervised machine learning, the neural network discovers patterns or clusters in unlabeled datasets without target variables. It identifies hidden pattern or relationship within the data. Algorithms like autoencoders and generative models are used for tasks such as clustering, dimensionality reduction, and anomaly detection. The third one, reinforcement machine learning. In this, an agent learns to make decisions in an environment to maximize a reward signal. The agent takes action, observes the records, and learns policies to maximize cumulative rewards over time. Deep reinforcement learning algorithms like deep Q networks and deep deterministic polygradient are used for tasks such as robotics and gameplay. Moving forward, let's see what are the artificial neural networks. Artificial neural networks, ANNs, inspired by the structure and the function of human neurons, consist of interconnected layers of artificial neurals or units. The input layer receives data from the external resources and it passes to one or more hidden layers. Each neuron in these layers computes a weighted sum of inputs and transfers the result to the next layer. During training, the weight of these connections are adjusted to optimize the network's performance. A fully connected artificial neural network includes an input layer or more hidden layers and an output layer. Each neuron in a hidden layer receives input from the previous layer and sends its output to the next layer. So this process continues until the final output layer produces a network response. So moving forward, let's see types of neural networks. So deep learning models can automatically learn features from data, making them ideal to tasks like image recognition, speech recognition, and natural language processing. So the most common architecture in deep learnings are the first one, feed-forward neural network, FNNs. So these are the simplest type of neural network where information flows linearly from the input to the output. They are widely used for tasks such as image classification, speech recognition, and natural language processing, NLP. The second one, convolutional neural network, designed specifically for image and video recognition. CNNs automatically learn features from images, making them ideal for image classification, object detection, and image segmentation. The third one, recurrent neural networks, RNNs, are specialized for processing sequential data time series and natural language. They maintain an internal state to capture information from previous input, making them suitable for tasks such as speech recognition, NLP, and language translation. So now let's move forward and see some deep learning application. The first one is autonomous vehicle. Deep learning is changing the development of self-driving car. Algorithms like CNNs process data from sensors and cameras to detect objects, recognize traffic signs, and make driving decisions in real time, enhancing safety and efficiency on the road. The second one is healthcare diagnostic. Deep learning models are being used to analyze medical images such as X-rays, MRIs, and CT scans with high accuracy. They help in early detection and diagnosis of diseases like cancer, improving treatment outcomes and saving lives. The third one is NLP. Recent advancement in NLP powered by deep learning models like Transformer, ChatGPT have led to more sophisticated and human-like text generation, translation, and sentiment analysis. So applications include virtual assistant, chatbots, and automated customer service. The fourth one, deepfake technology. So deep learning techniques are used to create highly realistic synthetic media known as deepfakes. While this technology has entertainment and creative application, it also raises ethical concern regarding misinformation and digital manipulation. The fifth one, predictive maintenance. In industries like manufacturing and aviation, deep learning models predict equipment failures before they occur by analyzing sensor data. Their proactive approach reduces downtime, lowers maintenance costs, and improves operational efficiency. So now let's move forward and see some advantages and disadvantages of deep learning. So first one is high computational requirements. So deep learning requires significant data and computational resources for training. Whereas advantage is high accuracy, achieves state-of-the-art performance in tasks like image recognition and natural language processing. Whereas deep learning needs large labeled datasets, often require extensive labeled dataset for training, which can be costly and time-consuming together. So second advantage of deep learning is automated feature engineering. Automatically discovers and learns relevant features from data without manual intervention. The third disadvantage is overfitting. So deep learning can overfit to training data, leading to poor performance on new unseen data. Whereas the third deep learning advantage is scalability. So deep learning can handle large complex dataset and learn from massive amount of data. So in conclusion, deep learning is a transformative leap in AI, mimicking human neural networks. It has changed healthcare, finance, autonomous vehicles, and NLP.
What is Python? Python is a high-level object-oriented programming language developed by Guido van Rossum in 1989 and was first released in 1991. Python is often called a batteries-included language due to its comprehensive standard library. A fun fact about Python is that the name Python was actually taken from the popular BBC comedy show of that time, Monty Python's Flying Circus. Now, let's look at the top features of Python. First, Python has a simple structure and a clearly defined syntax. This allows the learners to pick up the language quickly, so it is easy to learn and use. Python can run on different operating systems such as Windows, Linux and Mac, making it a portable language. It enables programmers to develop the software for several competing platforms by writing a program only once. Third, Python is freely available at the official website. Since it is open source, this means that source code is also available to the public. Now, Python uses an object-oriented approach that encapsulates code within objects. Python provides a collection of libraries for various tasks such as machine learning, web development, and data analysis. And finally, in Python, you don't need to assign the data type of the variable. When you assign some value to the variable, it automatically allocates the memory to the variable at runtime. Now, with that, let's move on to the uses of Python programming. So Python programming language is used to develop desktop applications and build web applications too. It is popularly used in the field of data science, machine learning, and artificial intelligence to analyze data, build predictive models, and make business decisions. Python is also widely used in game development. Now, let's see some of the popular Python frameworks and libraries. Python can be used for web development using frameworks like Django, Flask, Pyramid, and CherryPy. Now you can build graphical user interfaces using libraries and frameworks such as tkinter or just Kinter. You can also use PyGTK, PyQt, or PyJS or Python JavaScript. Now Python is also used to perform machine learning tasks using libraries such as TensorFlow, Pytorch, Scikit-learn, Matplotlib, and SciPy. You can also perform mathematical computations using NumPy and Pandas. Now let's look at the best IDEs that you can use to write programs in Python and perform specific tasks. So we have Jupyter Notebook, which is part of the Anaconda distribution that is widely used these days. Even for our demo in this video, we'll be using Jupyter Notebook. I'll show you in a while. Then we have the Visual Code Editor from Microsoft. This is also one of the preferred IDEs by learners and companies. Then we also have the popular text editor called Sublime Text Editor. Then we also have PyCharm, followed by Python IDLE and Spider as our top IDEs. Now let's look at the top companies that are using Python in our day-to-day work. So we have Google, Quora, Facebook, even Netflix, Spotify, and Instagram. Now there are other top product-based, service-based, and startups that also use Python programming.
Hello and welcome to this session on what is TensorFlow. Today we're going to see what is deep learning very briefly, and then we will talk about what are the various libraries that are available for developing deep learning applications, and then we will focus on TensorFlow and what are the various advantages, why we should use TensorFlow, what is TensorFlow, and then we will talk about what are tensors, which are, as the name suggests, TensorFlow consists of tensors and then they are executed in a certain graphical format of flow, like a graph. And that's why it is named as such, TensorFlow. And we will see how to write programs in TensorFlow. The programming language, of course, will be Python, but there is a certain way in which you write a deep learning application or a program in TensorFlow. So we will take a look at that. This is a basic introductory session for beginners, and then we will see one implementation of TensorFlow code, one full end-to-end, and that's pretty much it, what you can expect from this. Quickly wanted to mention that there are certain prerequisites before you actually go through this. The expectation is that you at least have some idea about some programming language and preferably Python. If you know Python, absolutely it will be much easier to understand the code as such. But even if you know any other programming language, I think it will be okay, and you will at least be able to understand the Python code. In addition to that, this also involves, especially the case study or the case implementation, you will be able to understand only if you have some idea about machine learning. So in case you are very new to machine learning and Python, everything, then it may be a good idea to check other tutorials that we have uploaded on, let's say, about Python and also about machine learning, so that you get a basic understanding and then come back here. Otherwise, it may be very difficult to understand this tutorial. Alright, so having said that, let's get started. So what is deep learning? Again, this video is not about deep learning, but there are other videos we have created in detail about what is deep learning. In this video, we'll just touch upon the basics, so that's like a nice segue into TensorFlow. So deep learning is in a way a subset of machine learning, and we use primarily neural networks in deep learning, and the underlying technology behind artificial intelligence is deep learning. And here we teach them how to recognize, let's say, images or voice and so on and so forth. So it is a learning mechanism, but here, unlike traditional machine learning, the data is far more complicated and far more unstructured. Like it could be primarily in the form of images or audio files or text files. And one of the core components of deep learning is neural network. And a neural network somewhat looks like this. There is something known as an input layer, and then there is an output layer, and in between there are a bunch of hidden layers. So typically there would be at least one hidden layer, and anything more than one hidden layer is known as a deep neural network. So any neural network with more than 3 layers altogether, right, is known as a deep neural network. All right. So what are the functions of the various layers? Let's take a quick look. So the input layer accepts the input. So this could be in the form of, let's say, if it is an image, it could be the pixel values of the images. So that's what the input layer does. And then it passes on to the hidden layers. And the hidden layers in turn perform certain computations. And they have what is known as a part of the training, they have these weights and biases that they keep updating till the training process is complete. And each neuron has multiple weights, and there will be one bias, and these are like variables, and we will see when we go into the TensorFlow code what we actually mean by that. And so that's what the hidden layer does. It does a bunch of computation and passes its values to the output layer, and then the output layer in turn gives the output. It could be in the form of a class. So for example, if we are doing classification, it tells us which class a particular image maybe belongs to. For example, let's say if this is a image classification application, then the input could be a bunch of images of maybe cats and dogs, and the output will be like, it will say, okay, if this is activated, this gives a 0 and this gives a 1, that means it is a cat. If this gives a 1 and this gives a 0, that means it is a dog. So that is a kind of a binary classification, and that can be extended with multiple neurons on the output side to have many more classes, for example. Or it can also be used for regression as well, not necessarily only classification. Again, since this video is not about deep learning or machine learning or neural network, we will probably not go into a lot of details, but you can check other videos where we have given a lot more details about neural networks and deep learning and so on. So in order to develop a deep learning application, how do you go about? Primarily, there are 2 or 3 components that are required in order to develop deep learning application. You need obviously a programming language. So typically Python is used, and that's what we are going to use in this particular video, but you can also use other languages like Java or C++ and so on. And there are some libraries that are readily available, and primarily for doing machine learning and deep learning programming. So these are a list of libraries. These are by no means the exhaustive list, but some of the most common ones like Keras, Theano, TensorFlow, and so on and so forth. TensorFlow has nowadays become very, very popular. This is developed by Google, and it is an open source library. And Keras was there before. Now Keras has actually now become a part of TensorFlow as well. So it is one layer above TensorFlow. So in that sense, they're well integrated. So a combination of Keras and TensorFlow is pretty good. Then of course you have Pytorch and DL4J and so on and so forth. So there are multiple libraries, but this video is about TensorFlow, and we will be focusing on TensorFlow. What are the benefits of TensorFlow and what are its components? And towards the end, we will show you a code in Python. We've written a code in Python. By the way, TensorFlow can be used with multiple languages. It supports multiple languages, though Python is by far the most popular language. So let's take a look at what exactly is TensorFlow and why we are so excited about TensorFlow. So TensorFlow offers APIs Now we can earlier without when these libraries, none of these libraries were there. Even then people were doing machine learning and deep learning and so on. But the coding mechanism was much more complicated. What these libraries like TensorFlow offer is they provide kind of a high level API so that we don't have to go really deep into writing all the stuff that is required, let's say to prepare a neural network and to even configure or even to program a neuron and so on, right? So these are done by the library. So all you need to do is they offer a higher level API. You need to use that API and call that API and maybe pass the data, and that would pretty much, it's much easier rather than actually going down and writing everything by yourself. So TensorFlow, that way it offers APIs to write your code in Python or even C++ and so on, other languages, Java as well. It has an integration with R as well, apparently, okay? And it supports CPUs as well as GPUs. Now, deep learning applications are very compute intensive, especially the training process needs a lot of computation. It takes very long, as you can imagine, because the data size is large and there are so many iterative processes. There are so much of mathematical calculations, matrix multiplication, and so on and so forth. So for that, if you perform these activities on a normal CPU, typically it would take much longer. But GPUs are graphical processing units. You must have heard GPUs in the context of games and so on, because where you need the screen needs to be of high resolution and the images need to be of high resolution and so on. So GPUs, as the name suggests, graphical processing unit, were originally designed for that. But since they are very good at handling this kind of iterative calculations and so on, now they are being used or leveraged rather for doing or developing deep learning applications. And TensorFlow supports GPUs as well as CPUs. So I think that's one of the major advantages of TensorFlow as well. Now, again, what is exactly TensorFlow? It's an open source library developed by Google and open source, and primarily for deep learning development. But TensorFlow also supports traditional machine learning, by the way. So if you want to do some traditional machine learning, we can do it. However, it is probably a bit of an overhead to use TensorFlow for doing traditional machine learning, and this is really good for performing deep learning activities. And again, if you want to get into more details about what's the difference between machine learning and deep learning, there is another video about it. You can probably take a look at that video. What else? It is developed originally for large numerical computation. So originally when TensorFlow was developed, they never thought of it as keeping deep learning in mind, but ultimately it so happened that it's really very good for deep learning development, and therefore Google has open sourced it. And TensorFlow, as the name suggests, the data is in the form of what is known as tensors. These are like multi-dimensional arrays, and they are very handy in handling large amounts of data, and we will see that as well as we move forward. And then of course the execution mechanism is in the form of graphs, so that makes it much easier to execute this code in a distributed manner across a cluster of computers and also using GPUs and so on and so forth, right? So that's a quick overview about what is TensorFlow. We will see a little bit more detail the two major components, that is basically the tensors and the graphs. Let's take a look at what they are. So what are tensors? Tensor is, as I mentioned earlier, it is like a multi-dimensional array in which the data is stored. Now when we are doing deep learning, especially the training process, you will have large amounts of data, and the data is typically in a very complicated format, and it really helps when you are able to use this or store it in a compact way. And so tensors actually offer a very nice and compact way of storing the data, handling the data during computation. This is not really for storing on your hard disk or things like that, but in memory when you're doing the computation, tensors are really very handy in terms of keeping the data compact, because they are like multi-dimensional arrays. So the data is stored in tensors and then it is fed into the neural network, and then you get the output. Alright, so there are some terms associated with tensors. Let's get ourselves familiarized. One is the dimension and another is the rank. So what is dimension? Typically dimension is like the number of elements in a way. So for example, this is a 5 by 4 dimension tensor, and then you can have again multi dimensions, right? So this can be like 3 by 3 by 3. So that is the dimension. And then you have ranks. What are tensor ranks? Ranks are basically, traditionally we would have thought of as dimensions. That is actually, in this case, it is called rank. So it becomes easier when we see examples. So a tensor's rank is supposed to be 0 when there is only one element. We also call this as scalar. So just one element, and this is not really a vector, it's just an element like 200. It's also known as a scalar. So such a tensor is supposed to be having a rank of 0. Then you have, let's say, a one-dimensional array. This is a vector with a row of elements. This has rank of 1. Now if you have traditionally what we call as two-dimensional, like a matrix for example, then the rank is 2, and in this case the rank is 3. And it can have more ranks as well. As I mentioned, it is like a multi-dimensional array, so you can have rank 5, 6 and so on. Okay, so those are the terminologies in TensorFlow terms: dimensions and ranks. So this is just to make sure that we are speaking the same language, so whenever we talk about the rank of a tensor, you understand what exactly is meant by that. Now, in addition to tensors in which the data is actually stored, all right, so the data is stored in the tensors, and then once you have the data, there is a computation that needs to be done. Now the computation happens in the form of graphs. So what we typically in a TensorFlow program, what we do is, it's not like traditional programming where you just write a bunch of lines and then everything gets executed in sequence. Here we prepare graphs, various nodes, and then these are executed in the form of a session, and they use the data from these tensors. Now I know this is a slightly new concept for a lot of you, so it may be a little difficult to probably understand in the first cut, but when we look at the code, when we go into the tutorial, the code walkthrough, I think that time it will become much clearer as well. But to start with, just we need to keep in mind that we have to first prepare a graph, and when you're preparing the graph, none of the code is actually getting executed. You write the code to prepare the graph, and then you execute that graph. So that's the way, by creating a session, that's the way TensorFlow program works. So, and each of these computation is represented as what is known as a data flow graph. And we will also see that whenever you start TensorFlow, when you create an object, TensorFlow object, there will be what is known as a default graph, and then if required, I know probably in the beginning it may not be required, but in more advanced programming you can actually have multiple graphs. Instead of the default graph, you can create your own graph and have multiple graphs and use it as well. But there is always, whenever you create a TensorFlow object, there will be a default graph, and this will be very nicely illustrated in the example code that we will take to explain this. So there it becomes much clearer than in these slides. So the graph gets executed and it processes all the data that we are feeding. All the external data will be fed in the form of what is known as placeholders, and then you have variables and constants. Again, this will also become clear when we take a look at the code. And once you have the graph, then the execution can be enabled either on regular CPUs or on GPUs, and also in a distributed mode, so that the processing becomes much faster. As I mentioned, the training of the models in deep learning takes extremely long because of the large amount of data, and therefore using TensorFlow actually makes it much easier to write the code for GPUs or CPUs and then execute it in a distributed manner. So this is how the TensorFlow program looks. So there is you need to build a computational graph. That's the first step, and then you execute that graph. So the first step is to write the code for preparing the graph, and then you create what is known as a session, and then in that session you ask the session to execute this graph. So this will again become much clearer when we look at the code. Now, what are the various elements of a TensorFlow program? As I mentioned, TensorFlow program is slightly different from regular programming that we do. So even if you're familiar with Python, this may still be new for you. The way you write a TensorFlow program is different from the regular Python programming that you would have done, or even machine learning program. You would have written some machine learning program using scikit-learn or regular Python libraries. This is different from even that. So let us see what are the various elements. So first of all, the way we handle data inside of a program itself is a little different from how we normally do. In a normal programming language, a variable is a variable in your program, right? So you have anything that can keep changing, you just create as a variable, or even constants in fact are actually created as variables. But in TensorFlow, the storage in the program consists of three types. One is constants, another is variable, and the third is a placeholder. So, and there is a lot of difference between these types, and we will see how they vary and how they are used and so on. So constants are like variables which cannot be changed. So for example, if you define a constant like this is how you define a constant, by the way. The simplest format is like this, like for example, b is equal to tf dot constant, and then you give a value here. A slightly more advanced version is you also specify the type. So you say tf dot constant 2.0 tf float 32. So the type is of type float. Now, in case of constants, you cannot, during the computation, you cannot really change these values. So for example, if you want to change the value of b from 3 to 5 or any other number, it is not possible. So that is the meaning of constant. Alright, so then we have variables. So variables we are all familiar with. What are variables? Whenever we use programming, we use variables. So this is pretty much the same. This is the way you define variables, tf dot variable. Now, one thing you need to note is this is the only type in which we have v capital. Okay, constant has c, small c, and placeholder as small p, but variable as capital V. And tf dot variable, and then you give the value, and then you can specify what is the type, and then you can use the variable, change the variable at any point in time with a different value and so on. You can update the variable and so on. So we will see all of this in the code. I will illustrate how a variable is defined and how it can be changed, whereas a constant cannot be changed, and so on and so forth. And then we have placeholders. Placeholders are really a special type, and this may be something completely new for many of us who have been doing programming, but in TensorFlow, this is a completely new concept. So this is very important to understand this. Placeholders are like variables, but only thing is that they are used for feeding the data from outside. So typically, when you're performing some computations, you need to load data from a file or from an image file or from a CSV file or whatever. So there is a provision with this special kind of variables which can be fed in a regular basis, because one of the reasons for having this kind of provision is that if you get the entire input in one shot, typically it may be very difficult to handle the memory and so on. So I think that was the reason they came up with this mechanism where you can feed in batches. And there is a certain way of populating the placeholder. We call this feed underscore dict, and this is a parameter name, by the way. And you feed the placeholders, right? That is the meaning here. So there is a certain way of feeding the placeholders, and we will again see this in the example code as we move forward. Okay, so there are three types. One is the constant, which cannot be changed once you assign a value. Then you have variables, which are like normal variables we are all familiar with. And then you have placeholders. This is primarily for feeding data usually from outside, but of course you can also, for temporary testing purpose, you can feed within the program as well. But primarily the purpose of a placeholder is to get data from outside. So alright, so those were the constants, variables, and placeholders. That is how you handle data within a TensorFlow program. And then you create a graph, and once you create a graph, then you have what is known as a session, and then you create a session object, and you create a session, and then you run a particular computation or a node or an operation. And so typically what you need to do is every variable or a computation that you perform is like an operation or a node within a graph. So initially the graph will be what is known as the default graph. The moment you create a TensorFlow object or TF, this TF here you see, this is the TensorFlow object. And again, in the code, when we go into the code, it will become much easier to understand. So when you create a TensorFlow object, there is like a default graph which doesn't have any operations, no nodes or anything like that. So it's like a clean slate. The moment you assign variables or constants or placeholders, each of them is, in TensorFlow terms, it is known as an operation. Again, you need to get familiar with these terms, and they are not very intuitive. This is not really an operation. You're just creating a constant or a variable, and this C is equal to A into B would traditionally or would intuitively be an operation. Here you're actually performing an operation. But in TensorFlow terms, each of these, everything is an operation. So if you're creating a constant, that is an operation. Another constant or variable, that's an operation. So you can actually run each of these, and they're also referred to as nodes. And when you're in your session, you will actually run each of these. You can potentially run each of these nodes. Okay, so a typical example would look like this. So you have two constants created. A is equal to tf.constant, its value is 5, b is equal to this, and then you say c is equal to a into b, and then you create a session. Now remember, all this you're just creating a graph. At this point, no execution has happened. Correct? So only at this point, once you create a session and then you say session or ses.run, c is when actually this whole thing will get executed. All right, so that is a different way of programming compared to our traditional way of writing programs. So you need to get used to this new format. And when we look at the code as we move forward, and when we look in the Jupyter notebook, it'll become much easier probably to understand this rather than in the slides. So these are the slides showing the code, but what we can do is go straight into the lab and take a look at the various examples that are there, and starting from the very basic one, how you create variables. And so these are some of the slides that are showing. So this is about how to create variables, how to create constants, and the variables or constants can also be strings. So this is like our first hello world program, and we will talk about placeholders, how to define a placeholder and how to execute and populate the placeholder values into placeholder. We will see these examples in the lab. Actually, I will run the code, and we will also perform a small computation of adding and multiplying these variables, and we will, in the end, we will take up a use case implementation using TensorFlow. So let's first go and see those examples and then come back and I'll explain this use case, and then we will execute the use case in the lab.
Hello and welcome to the session on installing TensorFlow. My name is Mohan and I'm going to take you through the process of setting up this TensorFlow development environment. As some of you may be aware, it's not that easy to set up the TensorFlow environment. There are several components, there are several possibilities. For example, you can set up on Windows, you can set up on Ubuntu. Now Ubuntu has multiple versions, which version to use, and then you have Python, which release of Python to use, whether to do a pip install, whether to do install using Anaconda, and how do you then link it up with Jupyter Notebook. These are multiple possibilities and it takes up a lot of time to try all of these. So today what I'm going to do is show you a tried and tested method of setting up the TensorFlow environment. And this will help primarily those who are starting with TensorFlow so that they don't have to waste so much time on setting up the environment and experimenting with the installation and setting up of the environment. Now, what we are going to do is I will show you a method by which it is a tried and tested method. And of course, TensorFlow homepage has an install page and it shows you some ways to install. But again, the challenge is the same. There are multiple versions, multiple methods shown there. So it's highly confusing for somebody who is new as to decide which path to take. So in today's session, what we are going to do is we will set up TensorFlow on Ubuntu, and I'm going to show you in a virtual box. But then if you are using a laptop with Ubuntu installed, you can straight away use the same method. However, we need to keep one thing in mind, that the various releases and versions of Ubuntu and Python and then TensorFlow, not all of them are compatible with each other. So these versions and releases need to be very specific. So I will tell you which is the version and releases, what combination is best suited for you to get started. And later on, of course, you can then experiment with other possibilities and other releases and so on once you get familiar with TensorFlow. To start with, I would also like to mention that it is a good idea to install or start with Ubuntu environment or a Linux, any other Linux also, but here we will focus on Ubuntu rather than Windows. So for those who are already, let's say, using a Windows system, the question may arise, what do we do? But there is an easy option. As you can see, I'm actually using a virtual box. So you need to install virtual box. Let me just show you. So this is the virtual box, Oracle VM virtual box. And there are tons of videos on YouTube how to install a virtual box and how to create a Ubuntu image, I think we will not spend time on that. But if you're using Windows, and my preference would be to set up a virtual box and set up your environment in Ubuntu image. So we will start by assuming that you have an Ubuntu environment, especially release 14.04 LTS. There are multiple Ubuntu versions, and again, we will not try to get the latest and the greatest versions or latest and greatest releases, but the focus here is to take the releases and versions which are working and where you will not waste time. So the setup process will be smooth if you stick to these releases. You can of course experiment later on with other versions and try out, but here we will be working with Ubuntu 14.04 LTS, and we will use Python 3.4, and we will use TensorFlow 1.5. This is a tried and tested combination, and I would also recommend that you use the same if you want a smooth start. And so let's get started with that. Let me log in to my Ubuntu system. Okay, so we have the Ubuntu system running here. Now, if you go to tensorflow.org, there is a page which mentions how to install TensorFlow, and as you can see, there are multiple possibilities. You have Ubuntu, you have Windows and Mac OS and so on and so forth. And if you go to Ubuntu, for example, further you will get multiple options, whether you want CPU or GPU, and whether you want to do pip install or using a virtual native pip, virtual env, Anaconda, and so on and so forth. So all these options are very complicated, or rather they're very confusing, I would say, not complicated, depending on whether you're expert or, of course, I am talking about beginners here. But if you click on some of these options, they may look very easy. So for example, if we go back and if you select, for example, native pip, it may appear like, oh, this is just, one single or two steps and that's about it. Everything gets installed. You see here, it should be just one step install. If you say pip3 install TensorFlow and everything gets installed. Unfortunately, it doesn't work that way. So it's not as easy as, so don't get kind of fooled by the simplicity of the documentation here. Again, it's not their fault. Because of the multiple combinations of releases and so on and so forth, it is not that easy. So what we will do is, we will take a slightly roundabout method, which is using Anaconda, which has a few more steps, but you're sure that this is going to work. So that is what we are going to do, and that's what I'm going to show you. So what are the steps involved? Of course, I will not go exactly by what they have mentioned here. As I said, I will show you the steps which are again sure shot to work, whereas here again, if you follow just this document, there will be some variations which they have kind of not documented. So that's the reason I will show you the steps separately. All right, so these are the main 4 steps. You need to download and install Anaconda, and then create a virtual environment with Python. And the release, as I mentioned, is Python 3.4, and we will install TensorFlow version 1.5, and then we will install and configure Jupyter, which will be our development environment. All right, so let's get started. This is our Ubuntu, and let's get a terminal started here. And okay, yes, so all right, so we started the terminal, and then what we'll also do is we'll go to the Anaconda website, because we need to install Anaconda. We need to download and install Anaconda. So for that, you need to go to the Anaconda website. So you can just open a browser and Google, and you will find the Anaconda website. So this is the site, anaconda.org. Click on this link and it will take you to the Anaconda website. You don't have to sign up or anything like that. Just look for the download Anaconda. So just click on that. It will take you to the download pages, and it automatically recognizes that you are on Ubuntu. So it will show you the links to download. All right. So as you can see, it has recognize that you're on a Linux operating system. So you can just click on this download, and it will start the download. There are 2 versions, of course, Python with Python 3.6 and 2.7. I recommend you start with Python 3.6. Now just want to clarify that we will be actually using Python 3.4. This is just for the initial installation, but subsequently when we set up the virtual environment, you will see there is one more step there where we set up the virtual environment. There we will actually be using Python 3.4, so just that you're not confused. Alright, so it has started the download. We just say no thanks for this, and it is downloading. While it is downloading, you can click on this link saying how to install Anaconda. So there are a couple of steps mentioned there that we will be using. So let me just in the meanwhile click on this. For some reason the network is a little slow, so it is taking time. Alright, so once the download is done, we will be using the options that are mentioned here. Now the first step, of course, is we are already doing the first step, which is downloading the installer for Linux. The second step is not mandatory, so it's an optional step. Most often you can actually skip that. And third step is what we are going to do. And since we are using, at this point, we are using Python 3.6, we should use this command. So basically the terminal we have opened here is to use or to run this command. That's the reason I opened this terminal. However, make sure that the download is complete before you run this command. So we'll just wait for a couple of minutes and we'll come back once the download is done. Alright, so as you can see, the download is done. This is a fairly large file, so if you're on a slow internet or low internet bandwidth, then it might take quite a while. It's about 578 MB, and so this is the file. Now what you need to do is you need to go back to this installation steps, and let me minimize this, and yeah. So this is the command that you need to run. So you can just directly copy and paste this command from here. Okay, so I do copy, right mouse click. Now it will ask you a bunch of questions as documented here. So most of them you need to just say enter or yes, and that's about it, except for the last step. I will just show you what we need. And here you need to press enter multiple times just to make sure you agree to all these agreement, the license agreement and so on and so forth. So once you do multiple enters, it will bring you to the next step. Alright, so now here again they say do you accept the terms. You just say yes and then press enter, and here it will ask you a couple of questions, and pretty much you need to just go for the default version. Press enter to confirm. You just say press enter, and this is primarily when it will pretty much start the installation process of Anaconda. This might take a little while depending again on your internet speed, so you need to have some patience. We will also probably come back once this installation is done, or if it asks for any further questions. Alright, so here you'll get again one more question. Do you wish the installer to prepend? So you just say yes for this question and keep going. Now the last question, I think we are pretty much at the end, and that is about Microsoft VSS, I guess. Yeah, VS Code. So for this you can just say no, because we will not be using this, and that's it. You're done. So this is completion of installation of Anaconda. So it's always a good idea to exit and start a fresh terminal. Okay, so let's start again, a terminal. So we are done with the installation of Anaconda. The next step is to create a virtual environment with Python 3.4. So for that, this is the command conda create -n, and this is the name of your virtual environment. You can give any name, but for easy reference I have given as TensorFlow, and we have to specify the Python version. As I mentioned earlier, we will be using the combination of Python 3.4 and TensorFlow 1.5. Now this is not the latest version. Python has probably 3.6 at this point at the time of creation of this video, and even TensorFlow probably has the latest version as 1.7, but then these combinations sometimes may not work, and I found that after several trials and errors, 3.4 with 1.5 seems to be most reliable, and that's the reason I've chosen this. I would recommend you to try with this first if you're a beginner, and later on maybe you can try out the other permutations and combinations. All right, one step I just wanted to show you is before we do the installation or creation of the virtual environment, if you want to just clarify or confirm whether Anaconda has been installed or not, you can run what is known as Anaconda Navigator. So you just say Anaconda Navigator. Okay, we need to edit this part. Hold on one second. I guess it is. Alright, so you see here, when you start Anaconda Navigator, this Anaconda Navigator will open up. That is an indication that Anaconda has been installed properly. So that's just a quick check, and you don't have to do anything. Just you can go back and close it once this comes up. And then in the meanwhile, let me just open one more terminal for the creation of the virtual environment. And yeah, so this is your Anaconda Navigator, and you can just say okay, don't show me, and you just say okay, and then you can close this. You can say file, you can do a file exit, or you can click on the close button, whichever. Alright, so we will exit from here. We have a terminal open here. We will use this for our next steps. Alright, so what we have to do now is type in this piece of code or this command. For some reason copy paste is not working, so it's a small command, so it shouldn't be that big of an issue. So we say conda, and we say create. So this is the command for creating a new environment, /-n, and then we give the name of the environment. So we can give any name. For convenience, I'm just calling it TensorFlow, but you can actually name it anything. And then we need to specify with which version of Python. So we say pip Python, and then that is equal 3.4. Okay, so it will create an environment. This will take a little while. It'll ask you a question, just say yes, and then it will be done. So this is just a warning. You can simply ignore that, and for the question that it asks, you just say yes, and I think you should be good. Alright, so it says do you want to proceed? You say yes, and then enter. This will again take a little time, so we will probably move forward and then come back once this is done. Alright, so the environment has been created. Now it's always a good idea to, whenever some of these steps get over, or each step gets over, you just exit the terminal and start afresh with a new terminal. For some reason, sometimes it causes problem if you continue. So I found that it is a safe practice to each time exit the terminal and start afresh. Now that we have an environment created, we can, by the name TensorFlow, you can enter that environment by calling the command source activate TensorFlow, or the name, whatever name you have given. So you'll see here, once you do that, you will get this, the name of the environment will be shown here. So it is like your own, again, a special environment within the system. And from here onwards, you can do other stuff like actually installing TensorFlow and so on. And you will see that it has installed Python 3 here, so 3.4, right? So it is installed. That's what we, during creation of this environment, we wanted Python 3.4, so that is what it is showing. But we are not yet done, so we need to still install TensorFlow. So in this environment, you need to run a command which will actually install the correct combination of TensorFlow. Now this is, as you can see, it's a slightly complicated command. Pip install -- ignore instance. So what we can do is from within here we can go and go to TensorFlow install page, and there is a sample code there. You can pick up from there so that you don't have to type in so much. So we say TensorFlow.org, and I'll also open up probably a notepad here so that we can construct that command and go here. We say Ubuntu. If you come further down, there will be, by the way, we are doing CPU installation. I think that is clear. We are not, there is a possibility to do GPU as well. We will probably create a separate video for that. And if we go here, yeah, so again, you probably, if you follow the entire document out here, it may still not work. So I do not recommend that for now, at least for beginners. But just to copy this command, because this is a fairly complicated command, so this is much easier to copy it from here. That's the reason I'm on this page. And we will then modify it according to, yes, okay. Let's say copy. And don't do it directly here because that is probably not yet the right command. Let us go and create a notepad page, empty document. I'll just say tf.txt. Okay, this is just a temporary file. What we need to do here is we need to adjust this command to suit the versions that we are installing here. So let me just explain what it is, what you need to do. So first thing, you can get rid of this one. Yes, okay. Now here, these parts you can simply ignore. Here you need to go and change it to version 1.5, and I think we are good with that. Okay, so the CP34 indicates your Python 3.4. So later on, when you're trying to experiment and if you want to do other combinations of TensorFlow and Python version, then you can change this. For example, you can change this to 3.6. Both these places you need to change this to 3.6 if you're using with Python 3.6. And similarly, if you want the latest version, which is of TensorFlow, which is 1.7, you need to change this to 1.7 and so on. But at this point, to start with, if you're a beginner, I would recommend that you stick to this TensorFlow 1.5 with Python 3.4. This is tried and tested and it works. Okay. Just a word of caution that just by changing these versions, the whole thing will not work. There may be other places where you may have to, some of the steps may change. So just a word of caution that just by changing this, if you want to try out with a different version, some of the steps may also change. So you don't think that just by changing this, just one particular command, you will be fine. Okay. So that's been my experience. So to start with, I would recommend use this particular combination. All right. So it looks good. TensorFlow 1.5, and let me just reconfirm with my notes, and I think it looks good. So this is install, ignore, 1.5, CP34, and so on. Okay. Okay, so let's hit enter. So it started the process. Again, this might take a little while, so we will pause the recording and then get back when the installation is done. Okay, so looks like this installation is done, and as always, let us exit and then come back. Now, you're currently in the environment, virtual environment, and it's a good practice before you exit out of the terminal to come out of the virtual environment. So just like you did source activate, you need to do source deactivate and the name TensorFlow. Okay, you will come back to the original command prompt, and then from here you can do an exit. Now we need to validate whether the TensorFlow installation has gone through properly or not. So the way to validate is to first start Python and then import TensorFlow library, see if it imports without error. So that's the best way to validate. So we'll open a terminal And whenever you want to get into the environment, this is how you have to do. Come to environment and then say source, and obviously you can also use existing. So source activate TensorFlow. Okay, so we do this, and you need to run Python from here. And remember, you should say Python 3 because you have installed Python 3.4. Now here, when you say import TensorFlow as TF, when you get back a prompt like this without any errors, that means TensorFlow installation has been successful. If TensorFlow was not installed properly, you will get an error saying TensorFlow is not available or module doesn't exist or something like that. So TensorFlow installation is done, but now we will go through the process of installing Jupyter Notebook so that you can do your development. So let me just exit, and in order to install your Jupyter Notebook, which is going to be your development environment, we will first install IPython using conda. So conda install IPython, and then pip install Jupyter. So let's first do the IPython. Conda install IPython. Again, it will ask you a question saying these are the components. Do you want to install? You just say yes. All right, you say yes. And then once again, it will take a little while, so we might pause the recording and come back once it is done. Great, so that did not take much time anyways. So we will, as usual, we will exit, which is source deactivate TensorFlow, exit, and then we will start a fresh terminal in order to install Jupyter. Now, in some places, they may say install Jupyter using pip3, but in my experience, it did not work with pip3, and that's the reason we will use pip. However, just keep in mind, you need to first go to the environment. So source activate TensorFlow, and you need to use this command, which is pip install Jupyter. Usually when you're on Python 3, you use pip3. But as I said, it did not work, so in my experience it works with pip install and not pip3. So pip install Jupyter. I hope you already noticed that it is JUPYPER and not JUPI. So again, it's probably taking a little while. We will pause the recording and come back once it is done. Okay, so Jupyter installation is also done. Once again, you need to, it's a good idea, not you need to, but it's a good idea to come out of this terminal session and then start afresh. So we exit, and we have a fresh terminal already available here, and we will once again go to TensorFlow, and we say Jupyter Notebook. That's how you start your Jupyter Notebook. So this looks good. Now, only thing is, since we are running for the first time, what you need to do is, if you come back to your command prompt, it will show you that if you are running it for the first time, it will say that you need to copy paste this link. So you can just, for the first time, only once, you need to do this, copy this and paste it in your browser. And remember, this is only the first time when you're running Jupyter. You need to do this. Subsequently, you don't have to. It will automatically open up. Alright, so now that we have Jupyter installed and it starts up, we need to test whether TensorFlow is working fine or not. And in order to do that, you can create a new notebook, and you say import TensorFlow as TF and shift enter. If everything is fine, TensorFlow is installed properly, you don't get any errors, and then it works fine. This is an indication that TensorFlow got installed successfully, and that's about it. So that's all about installing TensorFlow with Python 3.4. So remember, this is installation of TensorFlow 1.5 with Python 3.4 on Ubuntu. So let's go and check our lab.
Okay, so I'm in the Jupyter Notebook environment, and this is one of the development environments we can use. This is regular Python. Anytime you do Python programming, we use Jupyter Notebook, or there are other ways of using other tools like PyCharm and so on. But for this particular tutorial, I'm comfortable using Jupyter Notebook, so I will show you in Jupyter Notebook. So this is the very basic example to demonstrate how to create variables and constants and placeholders, and what is the difference between them, how they behave, and so on. And as I mentioned, the assumption here is that you know at least some basic Python programming or some programming language, so at least you understand the code here. And first two pieces of code, you will not need machine learning background, but when we do the use case or the case study, there it is expected that you know at least some basic machine learning concepts. So in case you need to brush up the machine learning part, you may have to do that before you go to the third one. But here, just at least some idea of programming will be sufficient. So what are we doing here in this particular line or in this particular cell? We are importing TensorFlow. It is, as I mentioned, it is a library. So we are importing TensorFlow and we are calling it TF. So this is just a name. You can give it any name, but it is very common, and everywhere wherever TensorFlow programming is done, it is always named as TF, but you can name anything actually. Okay, so this will import the TensorFlow into my session. Now this is the way to create a variable. So let's start by creating a variable, and this is the name of my variable. I'm starting by giving a name called 0, and I say 0 is equal to tf dot variable, and then I'm giving the value of the variable here. So this is the very basic way and the simplest way to create a variable. We will see a little later there are other formats as well, but the bare minimum way of creating a variable is this. So I'm creating a variable by the name 0, and as I mentioned, you need to pay attention to the capital V here. In case of variable, it is a capital V, uppercase. Constant and placeholders are lowercase. Now I'm creating a constant, and the constant I'm naming it as 1, and the way to create a constant is tf dot constant, and then you give the value of the constant. So the value of the variable here is 0, and the value of constant here is 1. And again, constant, you can also have additional parameters like a name and so on. Probably you must have seen in other tutorials or in other places where the code is written, but the basic format to construct to create a constant is this. This is sufficient to create a constant. So I created one variable and one constant. Now what else can we do? Again, here there is no real execution happening. We are just building a graph. We have not yet executed any TensorFlow code. We are building a graph, and I will show you how the graph looks as well. First, let us understand the constants and variables and so on, and then I will show you how the graph is generated and so on. So what I want to do here is I want to add 0 and 1 and put it into a new variable called new value. So what I do here, TensorFlow offers these methods like add, assign, multiply, or you have matrix multiplication, matmul, and so on, right? So I will use one of those methods, which is tf.add, and then pass these two as parameters. So we can add a variable and a constant. There are no restrictions on that. So this is a variable and this is a constant. So if I do this, it will be okay. I did not execute this code, so it is giving an error. Now we are good. Okay, so what it has done is new value will be equal to tf dot add 0 1. So then we have one variable and one constant. Now let's say I want to change the value of the variable, because that is possible, right? So we want to change the value of the variable to something, some new value. So we have, in this case, new value has 1 because we added a 0 and a 1. So new value has 1. Now I want to assign this to this originally what we called as 0. So I will call that as update is equal to tf dot assign. So assign is basically changing the value. So that's what we are going to do here. Now it has not complained. We'll just say fine, right? There are no issues. Now let us try this something similar with this 1 as well. So 0 is a variable, so we were able to change the value, and we will, in a little while, we will see what exactly those values are. But before doing that, now let's say I will uncomment this part and I want to do something similar for my constant, right? 1 is a constant. Now I want to, let's say, change the value of the constant and make that also something different. Okay, so if I execute this piece of code, it will give an error. Now again, the error message may not be very intuitive. This doesn't say that you cannot do this for a constant. It will just say tensor object has no attribute assigned. Now that sometimes may be confusing, especially when you're starting. But the meaning here is that 1 is a constant and you're trying to modify the constant, so it will not allow. That's the reason it is complaining. So let's put that back in the comment, and okay, so that is done. So only variables you can modify. Now what do you have to do? Let's skip this piece of code. I'll come back to this in a bit. But let's say we start by creating, you remember I told you we need to create a session. So the way to create a session, there are a couple of ways of creating a session, but this is for beginners, this is the easiest way. All you need to do is assign a variable called ses, or you can give any name, and that is equal to tf.session. That is the session method here, and you create a session object by the name ses. Now what I'll do is I'll skip this as well. There is a purpose behind that. Now let's go ahead and run this piece of particular operation. Remember I mentioned that everything you need to run. So as of now the code has not really got executed. TensorFlow code has not got executed. You only created the graph. So only when you run through the session is when actually the program gets executed. So when you do this, now you see, observe that it is giving an error. Okay, the reason behind that is, remember we skipped these 2 lines of code for variables. Okay, this and then this. Now this is something very, very important to observe. If you have variables in your code, what I mean by that is, let's say you are not using variables but you have only constants and placeholders, then this will not complain and you will not get this error. But in our case, we also have variables. So whenever you have variables, in that case, you need to do an initialization. And this is just a standard code. There is nothing that we need to add or modify or anything like that. This is a standard piece of code. You create this name, of course, can be anything. You can give us any name, but this global variables initializer is what you need to call tf.global variables initializer. This will kind of initialize all the variables that you may be using. And then again, remember, this doesn't execute anything, right? So all you're doing here is you're creating an operation. But in order to run that operation, you need to also run this known as run init_op. So this operation you need to run after creating the session. All right. So we executed this. Now let us execute this. And now when I run this piece of code, it will run successfully. Okay, I hope you observed that. So it is whenever you use variables, these 2 lines of code, one is the operation, you need to create an operation for saying global variables initializer, and then you need to run, before running anything else, you need to do a session.run this operation. Okay, again, only if you're using variables. Of course, you invariably in all your programs you will use variables. You cannot just write a program with constants and placeholders. So you can pretty much assume that this has to be there in pretty much all the programs. Now again, why this has not been taken care of in the library, that's a different question, but you need to keep in mind. And always remember, if you don't do this for whatever reason, if you've forgotten, you will get an error and the error won't be intuitive. So you need to remember this, that this could be because of the variables. Okay, good. So we have seen how to create a constant, and we have seen how to create a variable, and we have seen that you cannot modify or update a constant, and we have also seen if you have variables that you need to execute or have these 2 lines of code to initialize the variables. And then we have seen that after creating a graph, how to run the graph in a session. And I will show you a little bit more in detail how exactly the graph gets created and how it gets executed. But this was the first very quick code on creating variables and constants. Now we will keep going, and we will also show you, or I will show you the placeholders. But before that, one more small piece of code. So this is how you write a for loop. Okay, so we are saying 5 times you run this piece of code. Now like any Python program, this is nothing different. So you have a for loop and this is indented, that's the reason. And therefore you say session.run update. So this will run 5 times and it will get printed. That's all. So update will run for 5 times. Each time it will come and do this particular operation. That's all we are asking the system to do. So let me just run that and show you. So it will, okay. So it has done 5 times
1, that's 4. It is basically adding, if you recall, it starts from 0, it adds 1 to 0, then 1 to 1, 1 to 2, and so on. So it's nothing but it is generating 5 numbers, 1, 2, 3, 4, 5. That's it. Okay. So then you can also have your constants as strings, for example. So you can also work in a similar way. You can work with strings. So most of the computation happens mainly on numerical values. So we normally handle numbers, but there will be situations where you may have to handle strings as well, or text as well. So this is an example of text operations. So you can, similar to numbers, you just create strings or store in constants. Instead of a number, you say hello is equal to tf.constant, and then you assign the string that you want it to be assigned, and then the next one is one more string which is for world, and then you say add these two. So it is nothing but concatenation of these two words, hello and world. So we will do that, and remember, this is only creation of the graph, right? So in order to actually execute this graph, you need to run the session. Now you need to keep in mind, we don't have to create the session once again, because once you create a session, till you close the session, it remains valid. Okay, so we have created this session here. Now till you say ses.close, it will remain for you. So that's why we did not create one more. So we are just reusing that session, ses.run hello world. So in this hello world, what is the operation that we are doing here? The operation is add these two, concatenate these two. So if I run this, it will print hello world. Okay, now that's string operation. Now we will take a look at placeholders. So this is slightly more complicated and something new even for people who have been writing programs. So, but I'll just explain it with a quick example. First of all, how do you declare or create a placeholder? You just do tf.placeholder, and the p is lowercase. Only in case of variables, the v is uppercase, but otherwise constant and placeholders, it is lowercase. And you just say, because as I mentioned, this is a placeholder that doesn't have any value. So you, unlike a constant or your variable, you will not specify any value. You just say what type of placeholder you want. And very often, most of the cases, it is a floating point. So we just say placeholder of type float32. So this tf.float32 tells the system that it is a floating point. Okay, and then, so let me just run this, and then you can do some or define some computation, like for example, b is equal to a into 2. Now remember, here right now a has no value, but what we are saying here is at any point later on when a gets some value, then b should be equal to twice the value of a. That's all we are saying here. Okay, and also, as I mentioned earlier, we are not yet executing anything. We are just creating the graph here. Okay, so now you have that. Now how do you feed the value or populate the placeholder? There is a certain syntax in which you can populate the placeholder, and you do that using what is known as a dictionary. You're all probably familiar, those with Python especially must be familiar with the dictionaries. So you need to create a dictionary and then pass that in order to feed the placeholder. So in this particular example, if I want to run something, if I want to calculate or compute b, obviously I need to feed the value of a. So the value of a I'm feeding using this dictionary, and I'm saying that a is equal to 3. Now there are multiple ways of populating the value of a, because typically this won't be just a scalar value like in this case, right? Remember scalar, so it's just one value, one number. Typically it would be a vector or a tensor. Very often it is a tensor. So we will see step by step. So we can start with the very basic example where a can be a scalar. So in this case, a is equal to 3. That's what we are saying. Feed underscore dict. In this case, feed underscore dict is the name of a variable, by the way. So you can't give anything else here. So if you just say feed is equal to this, it will give you an error. All right, so keep that in mind. Either you specify feed underscore dict is equal to and give the dictionary, pass the dictionary, or you straight away, like in this case, this is another format. So let's see. First, let me execute this. It has given 6. Okay, I think let me see if I can clear out this particular cell so it becomes easier to understand. Okay, so it is giving you 6. Let me do that once again. Clear out this and then okay, and let me change the format. So this is one way of doing it. Another way is you don't even have to specify the name of this parameter feed underscore dict. You just pass the dictionary and it will execute.
Okay, but typically this makes the code readable. So that's the reason most of the places whenever you find TensorFlow code, you will see that they explicitly mention feed_date so that the code is readable. Otherwise it can get confusing. So I will also comment this and retain the other format. Okay, so I hope it's clear. So what we are doing here, we are running the operation B, and what exactly is B? B is twice A into 2. So therefore what we are doing, and A has not been, doesn't have any value out here, right? So that's why we are feeding the value of A, and then the operation gets completed. So A gets a value of 3, and then it gets multiplied by 2 because that's what we said here. Therefore B gets a value of 6, and that's what is being fed into result, and that's what is getting printed here. Okay, now as I mentioned, A need not be just a scalar value. It can be a vector with a multi-dimension array and so on and so forth. So let's start showing you examples of that. Again, let me just clear out the outputs. Let me clear this, and let me also clear this for now. Okay, you can also do, before running this, we could also do clear all output clear. It will clear everything, but that we'll have to start all over again. So I'm just doing individually. All right, so in this example we are taking a one-dimension array where rank is equal to 1, and I'm feeding 3, 4, 5. Now let us see what happens if I run this, right? As you can imagine, it gets multiplied, each number gets multiplied, so the result is 6, 8, 10. Okay, now as I said, it can get more complicated. Now let's say this is a multi-dimensional vector. So what happens if you feed this? Okay, so as you can see, this is pretty complicated now, but if you feed this, again, all you're doing is there is a slight change here. Again, you can also create your dictionary outside and feed that here. You don't have to directly do it here, like in this case. You see, there are variations of the exact syntax in the way you write it, right? So there is a slight variation. So in this case, you are creating the dictionary straight away here, kind of inline, but here you created the dictionary separately because it's more complicated, and then you are passing that dictionary here. So I said dictionary is equal to A, and then I'm saying this is what should be the value of A, and I'm feeding that, and then I'm using directly that dictionary here. Okay, so this is equivalent to putting this code here, right? So if we execute this, what happens? Same. So you get, because A was let's say this is a 3 by 4 by 2, right? So that is 3 by 4 by 2, right? So you see here, this is a multi-dimensional array. So you feed that, and the values you see here, it is 1, 2, 3. It became 2, 4, 6. 4, 5, 6 became 8, 10, 12. 7, 8, 9 became 14, 16, 18, and so on and so forth. Okay, I hope now you got an idea about placeholders. And in real life, what happens is you typically won't create these dictionaries manually. Since this is a quick demo, we did this. You will actually read the data into this dictionary, and then you feed that when you're doing the computation. Okay, so it could be a CSV file, or it could be an image file. So the input is basically read and fed in. Usually it is also done in batches, so you don't read the entire thing because there can be a large amount of data. So that is the idea behind having these placeholders, and the way we feed these placeholders, there is a provision, deliberately there has been made a provision for this kind of getting data into the program in chunks. Okay, now in this particular example, we will close the session here, and then I will show you what is the other way of creating a session, right? So now if I close the session here, now if I try to do anything with the session, it will give us an error. So I will probably not do that right now. Now there is another way or another format, and this is a very common way of using the session, but I didn't want to start off with this because this could get a little confusing. A simpler way was to create session saying ses is equal to tf.session, but typically you will do it in what is known as a with block. This is a very common way of creating session. So once you have the graph, you would execute the graph in a session using a with block, and this is the syntax. So you say with tf.session as ses, all right, and then you put all your code here. So what will happen is you don't have to explicitly close the session. The moment this with block gets completed, the session gets closed. Okay, so let's just take a quick look at this example. Now, if we let me clear this current output, be clear. Okay, so this is the hello world example. A little bit earlier we did that. So I'm doing with tf.session as session result is equal to ses.run hello plus world, and then I say print result. Okay, so within this with block I'm doing all my computation and this gets executed. Now let's say I try to run, remember I created a session here. Now if I want to, let's say, do something like run sesh.run a, it is giving an error because the session is no longer valid, right? So you cannot, either you have to run this, if you want to run this, you have to run this in this with block, or you shouldn't have closed the session here, right? You remember this, we said session.close. So since we have closed the session, there is no active session, therefore it is giving an error. Okay, now there is a third way of creating a session, but for now I will skip it because that is very, very specific to notebooks and so on, so we will just avoid it. You start with, for beginners, I think the best way is to start with creating a separate session and then writing your code and then closing your session. Now of course, remember, if you don't do this part, ses.close, it will not give any error or anything like that. Only thing is that it's a good practice and your resources will get released. Otherwise, if you do multiple of these programs, if they are running, then your resources will get blocked. That's the only thing. And to start with, it is simpler to do it this way. So initially when you're doing, you start with this. But as you move forward, as you become familiar with TensorFlow programming, I would recommend all of you to get into this model. Most of the programming, TensorFlow programming, is done like this with tf.session as says. Okay. All right. So that was one book or one page of code that we have done explaining about variables, constants, and placeholders. Now let me explain how the graph works. So in this example, we are going to see how the graph is created, how the graph gets executed, and so on. Okay, now that we got a understanding of constants and variables and placeholders. Okay, so we will start as usual by importing our library, and as I said, whenever you create a TF or TensorFlow object, there will be what is known as a default graph, and you can get a handle of that by saying get default graph. So let's do that, and you can display the operations. Remember, every node in the graph is considered as an operation, right? So as of now, as you can see, we have not done anything. We have not created a constant or variable or nothing, right? So there is no operation. So by the way, let's do one thing. Let's start with all output clear so that I don't have to again do individually. So I'll just run these two lines of code. Okay. Now, so we have the default graph. And as of now, there are no operations. So there is a method called get_operations, which will kind of display or show what are the various operations that have been performed on the graph. So as I said, to start with, there have no operations been performed. So when I try to display, it's empty. There are nothing is there, no operations. Okay. Now let's see what happens when we slowly, step by step, start writing or building the graph. So my first step may be to create a constant. Okay. Remember, in the previous example, I have shown you how to create a constant in the most simple or the simplest way, which is like constant and then the number, right? Now, a small extension of that is you can actually give a name to your constant. Now again, this need not be the same. I can say a is equal to name and xyz. I can give anything here. Okay, this is just for your reference, but here for simplicity, because there is a purpose why I'm using the same name as the name of the variable, and there are other reasons as well why you would give a name again to a constant or a variable. This is again useful when we are using what is known as tensor board. Otherwise it doesn't have much value. This additional name doesn't have much value. In this our case also, we will be seeing the graph, and that's why I'm using this, but otherwise this having additionally a name usually doesn't add much value. All right, so let's create a constant. I created a constant. Now let us see what's going on in the graph. So I will just say operations is equal to get operations, and if you see here, now you remember here it was blank. Now you see the first operation is showing up, and this a, that's the reason I put here, so it is showing as a, and it says that okay, you have performed an operation and there is a constant. You have created a constant. Okay, all right, so let's move on.
let's say we want to create a second constant, and this is b. So if I see what are the operations, list of operations that have been performed, you see here there are two of them. So you have operation a, which is a constant, then you have an operation b, another constant. You recall, in the term operation here is not very intuitive, right? So we are just creating constants or numbers or variables, and it is saying it's an operation. But that's a terminology in TensorFlow. Everything is an operation here. Okay. All right. So then what else? Let's say I want to create a third operation, and that is basically adding, this is a real operation in normal sense as well. So let's say I'm creating C, which is adding A and B, and the C value obviously will be A plus B. Okay. Now, if we want to see what is in C, and we say C, you see here, it is not showing 30. It just says it is a tensor and it is of type int32, right? Because we have not executed the graph. We are still only building the graph. I hope this makes it easy to understand. Okay. So we are just building the graph. We have, till we do a session and run a particular operation, you're not actually executing anything. Okay, you're just building the graph. All right. So now let us see what are the operations. We have done A, B, and now C. So you will see there are three of them, A, B, and C. Okay. Now let's do one more operation, which is D. And here I am doing multiplication. Remember we did a tf.add. Now I'll do tf.multiply. And I'm multiplying A and B, and I'm calling this operation as D. So A has, I think, 10 and B has 20. So D will be actually 200 when we execute it. Right now it is just a tensor and it is of shape int32. Okay. And once again we can see what are the operations, A, B, C, D. And let's do one last operation here, which is E, which is once again multiplication of C and D. Now that C has 30, which is A plus B, and D has 200, which is A into B. So now C into D will be 30 into 200, which is equal to 6000. But as we have seen earlier, that multiplication will not happen right now. So now you have built a fairly simple but operation graph, which consists of A, B, C, D, E, 1, 2, 3, 4, 5 operations. Okay, so you built a small, it's not a very complicated one, but a simple graph. Now you need to execute these operations. So what you need to do, you need to create a session. Okay, so ses.tf is equal to session, and then you can run these session, print ses.run e. Now, am I missing something? Do I have to initialize the variables? That's a question for you. Think and tell me. Do I have to initialize the variables? Then remember, I ran one piece of code. I think you must have got the answer. I don't have to, because I'm just using all constants here. I have not used any variable here, right? So I don't have to execute that piece of code to initialize the variables. So I can just create a session and run any of the operations that I want to run. So in this case, I'm running session E, operation E, right? This operation E. Now I can actually run individually. Instead of doing directly E, I could have run only A, or I could have run B, and so on and so forth. But in this case, I have run E, which in turn will do all the required computations, which is, for example, assigning the value to A and B and C, doing the multiplication and so on. All those operations will be performed, which are required to do the computation of E. Okay. Now, there is a small piece of code that you can use to find out what are the various operations that are there in this particular graph. In this case, of course, it was very easy, very straightforward. I have created A, B, C, D, E. But in normal programming, in real life, this can sometimes help to see what is there in your graph, what kind of operations are going on in your graph. So you can write this piece of code, and it may sometimes help debugging as well. Okay. All right. So I finished my session. What do we have to do? We need to close the session, right? Because I did not use the with block. So I need to close the session as a good practice. So I close the session. Good. So that's how the graph works. I hope it was helpful in understanding how variables and constants and placeholders are created in the previous example we saw, and how exactly you create a graph and then you actually execute that graph. That's the way
TensorFlow program works. That's the structure of TensorFlow program. Okay, so now that we understood the structure of TensorFlow programming, let's take an example and a classification example and take some real data from outside, external data, CSV file, and try to solve a classification problem. For that, let's first go back to the slides and understand what is the problem statement, and then we will come back. Okay, so what is the case here? We have some census data and which has all these features or variables like the age of a person, what class, work class, what is his education, what is his marital status, gender, and so on and so forth. So there are a bunch of features that are available, and we have to basically classify, or not classify, we have to build a model for classifying whether the income of this person is above 50K or below 50K. Okay, so there is actually a label data available. We will then try to build a model and then see what is the accuracy. So that this is a typical machine learning problem actually, but as I said, TensorFlow can be used for doing machine learning as well. So we will, as a simple example, we will take machine learning. So this is how the high level the code looks, and in TensorFlow programming we also take help of regular Python libraries, like for example it could be NumPy, or it could be Scikit-learn, or it could be Pandas in this case. And because before you actually develop or before you train your model, create your model, you need to prepare the data into a certain format. And sometimes if you're doing machine learning activity, you all are familiar, those familiar with machine learning will know, you need to split your data into training and test data sets. So all that can be done using regular non-TensorFlow libraries, right? So these are like regular Python libraries, Pandas, Scikit-learn, and so on. So we use that and then prepare the data and then use TensorFlow for performing either the machine learning or deep learning activity. Now, so what is the advantage of using TensorFlow? The main advantage is that TensorFlow offers high-level APIs, right? We talked about that. So in this case, we will be using, I'll explain what is in the slide, but before that I wanted to just show you what is the API that we will be using. So we will be using the estimator API. We will be using the estimator API to create a classifier, what is known as a linear classifier. Now, in order to do that, you need to prepare the data, and you need to prepare the data into a certain structure or format, and the API itself needs to be fed in a certain way. So that is exactly what we are doing before we get into the regular TensorFlow code. Okay, so these slides will quickly show you what exactly is happening, but I will take you into Jupyter Notebook and run that code and show you. So here we are importing the data. The data is, the name of the file is census_data.csv. It's a CSV file, and then there is income bracket is one of the columns, which basically is our target. That is what is used. That is the label rather. But this doesn't have numeric values, so it has the income. So we need to convert that into binary values, either 0 or 1. So that's what we are doing here. And then we are splitting using Scikit-learn. We are doing splitting of the data into test and training, right? So this is a standard Scikit-learn. People, some of you who are familiar with traditional machine learning, and you have done machine learning in Python using Scikit-learn, will immediately recognize this. This is a sklearn is Scikit-learn, and there is a readily available method to split the data into training and test. That's what we are doing here. And then you need to create what is known as feature columns and input functions before you can call the API, estimator API. That's what we are doing here. And there are different ways of creating the feature columns for numeric values and for categorical values, or rather for continuous values and categorical values. Okay, so that's what is been two types we are doing here. We will see again in the code as well. And then you create your model. So this is basically model is equal to tf.estimator linear classifier, and then you're feeding the feature columns, and also subsequently you will call the training by passing the input function, and you specify how many iterations to be done for the training process. And again, this is all typical machine learning process, so there is nothing specific for TensorFlow here. And then you evaluate your model, because this is classification model, so you can again take help of the scikit-learn to test the accuracy and get the reports evaluation, perform the evaluation and get the report like this one, right? So this is the classification report, and you will see what is the precision, recall, F1 score, and so on. Again, this is a standard machine learning process. All right, so that's pretty much as far as the code here is concerned. Once again, let me take you into our lab, and we will get started with this particular code. Now let me clear out the outputs so that you can step by step you can see the output. So this is our data, and we will actually this is just a display here. The code starts from here. So before even we start with our TensorFlow part of it, as I mentioned, we now remember in the previous examples the data was kind of cooked up. Internally we created some data and we were using it, right? The constants, variables, and so on. Here is a real life example. So you are actually getting data from outside. So before we get into TensorFlow, this is actually regular Python code. So we are using pandas, for example, to create our data frame. So we will import pandas, and then we will basically read our file into a pandas data frame, and this is how the data looks, right? And if you do ahead, it will give you about 6 readings or observations, 5 or 6 observations, and then you can take a look at how your data is looking. So for example, you have age, work class, education, and so on and so forth. Okay, and you see here this last column, income underscore bracket, it says whether the income is greater than 50k or less than 50k. So this cannot be understood, or this cannot be fed into our model, or so that's the reason we need to convert this. This will not be understood, right? So this needs to be converted, saying okay, maybe less than 50k is 0 and greater than 50k is 1. So that conversion needs to be done before we feed it into our model. So that's what we are going to do as we move forward. So this is the code for doing that. Okay, so we take this and then we define a function, and then we run that function. So now we have, wherever it is less than 50k, it will have 0, and greater than 50k, it will have 1. So we have now updated the data. Then the next part is to split our data into training and test data set. So how are we going to do that? We again will take the standard Python library, which is scikit-learn, sklearn library, and we use an existing function there, which is train test split. And what we are doing here is basically splitting the data into, I'm sorry, I need to run this and then this. Okay, sorry about that. So once I run this, what are we doing here? Again, those who are familiar with scikit-learn will immediately recognize I'm splitting this into test and train. I'm saying test size is 30%, so 30% of the data should go into test, and training should have 70%. Okay, so that's all we are doing. 0.3 indicates 30%. So you can, again, this can be individual preferences. Some people do it like 50-50, some people 20-80, and in our case we are doing 70-30. So training is 70 and test is 30. Okay, all right. So so far we've been doing regular non-TensorFlow stuff. So preparing the data so that we can now use for TensorFlow. And in TensorFlow, what we are doing is we will be using the API called estimator. Now estimator, in order to call estimator, you need to prepare what is known as feature columns. So feature columns have to be in a certain format. Basically, it is nothing but the columns. We have to put them in a certain format. And then when we are calling the training, we need to pass what is known as an input function. Again, a certain way in which you need to pass that function. So that is what we need to do before we create the model and run the model for training. So the next few lines will be doing that. Quick look at, before we even get in once again into the TensorFlow code. So this is just showing us what are the various columns, names of the columns of this data. Okay, so that is what is shown here, and this is more for when I was writing the code, I could copy paste from here. That's the reason this line of code is there instead of typing in these values. Okay, good. So now is where the actual TensorFlow action starts. So I import TensorFlow.
and now I will use this feature column functionality to create my feature columns. And there is a certain construct how you create the feature columns. Again, probably the details of that is out of scope here, but just that you need to know that we need to create feature columns, and the way you create feature columns for continuous values and for categorical values is slightly different, and that's the reason you have two different blocks. Okay, so for categorical values you need to use what is known as tf.featureColumn.categorical column with vocabulary list. And again, within this, again, there are two ways in which you can create for categorical values. One is a vocabulary list where you know how many types are there. So for example, gender column can have only male and female. So in such a case, if there are, let's say, a finite number of values for a given column, then you use a column with vocabulary list. Okay, so and then you say what is the name of the column and what are the possible values. So in this case, male and female. Now there will be situations where the values that this column can have, okay, first of all, it is a categorical column. That means it can have names or some non-numerical values, but the number of values is probably unknown or undefined. So for example, occupation. Now occupation can have any value. It can be self-employed, it can be a software professional, banker, a teacher, doctor. So many possibilities are there, and we don't know in the given data how many occupations have been listed, right? So that is where you use what is known as categorical column with hash bucket, and you specify the hash bucket size. So what this says is there can be a maximum of 1,000 such values. So typically you give a safe number, safely large number, so that you don't run out of these number of occupations. So I think 1,000 is a safe number. I don't think there will be more than 1,000 occupations in a given data. So that's the idea behind it, but that's a judgment call we need to take. What should be the size of this bucket size, right? Hash bucket size. So these are two different types for categorical values for creating the feature column. So we will execute this for all the categorical columns. Obviously you need to know the type of the columns, and that is where, if you see right at the beginning, this information was provided. What is the data type, and you see here the column name and whether it is continuous or categorical. This information is provided in the census data wherever we pick this census data from. By the way, this was picked from online from a government website and we stored locally. So on that website it is mentioned, the details of this data were mentioned, and they have mentioned whether each of these columns is categorical or continuous. So that information we have to use, and we have to create feature columns using this categorical method for the categorical type of columns. And then for numeric or continuous values, you just use what is known as feature column dot numeric column. Okay, so these are all continuous or numeric values like age, education number, capital gain, capital loss, hours per work. These are all numerical values or continuous values, right? So you just say tf.feature_column.numeric_column and then give the name of the column. So once you do that, I think I have executed the previous one. Yeah, this one. Now, so your feature columns are ready, and you need to basically create a vector of all these columns, and we call that as feat_calls, which is like a short form for feature columns. Now, as you have seen, I've mentioned earlier also, there are two things that are needed. One is the feature columns and the another is the input function. So feature columns to first create the model, and then to train the model you need to create an input function. So now we have the feature columns ready. Next is to create an input function, and there is a certain way in which you need to, this construct is pretty much a very common construct, so we will use that. So the input function takes these x and y values for training and tests. You remember these are, the x train is the x values of the training data set, and y train is the labels of the training data set. So that's what we are using here, x train, y train, and then we specify what is the batch size. Batch size, you remember I mentioned, this is what will say how many records need to be read each time, right? So typically when we are doing the training process, we don't get the entire data in one shot. We do it in batches. So what size you specify here.
Number of epochs, in this case we just say none, but number of epochs is again probably the definition is not required here, but at a very high level, how many times the entire data has to be passed through the model, right? So if you have 1000 records and you pass all the 1000 records 3 times for training purpose, then you call that as 3 epochs, right? So there is a difference between the batch size and epochs. So when, let's say we have 1000 records and you're saying batch size is 100, that means there will be 10 batches, right? So if you take 10 batches, then that is 1 epoch gets completed, okay? Then the training obviously doesn't get completed in one round, okay? So you need to pass this data again, maybe a second time or a third time till you get the right accuracy. That is known as epochs, okay? Again, if you need more details about this, you may have to go through the machine learning tutorial. I think it becomes much clearer, okay? So you have your input function as well. Let's execute that, okay? And now we are ready to use the API, right? So what will we do? We will create the linear classifier using tf.estimator.linear classifier, and this guy needs feature columns, right? So that's why we did all that, so much of manipulations to create this feature columns. So we have feature columns, so we pass that and we create our model. There may be a few warnings, don't worry about that. So we will just ignore that. And now we use that model, and what we did is we created an instance of the model. We have not really run anything. We just created an instance of the model. Now we will create the node for training. So model.train, and this needs the input function. Remember, we created the input function, so we need to pass the input function, and then we say this steps is now telling how many iterations this training has to be run. So we are saying 5000, and it will probably take a little long, so we will, okay, but that's fine. I think we will leave it 5000. Sometimes if you have probably a less powerful machine, you can cut it down to maybe 1000 or something like that. But in this case, I have a fairly powerful system, so I think it shouldn't take much long. Let's go ahead and give a couple of minutes for it to get over. Okay, so let us go back. Yeah, I think this is done. You see here the hourglass has disappeared. That means this computation is done. Yes, okay, this is done, right? Saving checkpoint for 5000. That means it is done. So training is done. So now what we have to do? We need to do the evaluation. So again, this is a standard machine learning method. So methodology rather. So training has been done with the training data set. Now you need to evaluate using your test data set. So that's what we are doing here. For example, you see here x_test is the test data set. Remember, we used scikit-learn to split the data into training and test data set. So x_test. And a quick question, why are we not using y_test here like we did in case of training? Obviously, we are expecting the model to predict the values, y values, right? So that's why we don't pass the y values here. All right. So let's execute this for doing the evaluation. All right. And then we put them in a proper format because the output doesn't come out in a proper format. So we put it in a list format, and then we can just check. Yeah, so this is done, and we can check what is the first element in this, what is the probabilities, and so on. So it's just a quick way to see if the values are there or not. You can take any value here, right? Any element here. All right, now that the testing is done, what we need to do, again, we will probably put them in some kind of this is more of a formatting thing. We will just run through quickly, and then we will use once again scikit-learn for finding out the accuracy and so on, because scikit-learn offers what is known as a classification report functionality. So we will use that and find out how well our model has performed. So you see here again, people with machine learning background will be immediately able to recognize this. So it gives us what is the precision, what is the recall, and F1 score. This is pretty much like you're getting like almost 85% accuracy, which is pretty okay. And there are other ways to increase the accuracy. For example, you can run the training for more iterations. That is one way, get more data and so on and so forth, or use a
this is a linear classifier. We could have used a non-linear classifier and so on. So again, multiple ways of doing it to increase the accuracy, but the idea here was to quickly show you a piece of TensorFlow code, and that's what we have done here. Diabetic retinopathy is a condition which can lead to blindness, and it is caused, as the name suggests, due to diabetes. And there are ways to detect this early on and maybe cure it and prevent blindness. So how can we do something like that? There is research going on, and one of the techniques used is deep learning, which is a part of neural networks and which is a part of artificial intelligence. The way it works is hundreds of thousands of images known as fundus images are sent to the neural network, and the neural network is trained with this labeled information. Now these images, we know whether they are good or they are defective, or there is a disease in this eye or there is no disease. So that labeling is done. This labeled information is fed to the neural network. The neural network uses deep learning, and it will learn to detect if this from the image to find out if this disease exists, so that when a new image is fed, it will be able to identify whether the eye is healthy or diseased. Now let's take a simple example of a linear regression, how it works in TensorFlow. This is a small code example. So if you want to perform a linear regression where obviously the model will be y is equal to mx plus b, and with the given data you want to obviously come up with the values of m and b, which are the coefficients, right? So let's say we want to do something like this. To start with, you can use, again, we use Python here. So the traditional Python libraries like NumPy and Pandas, all of that is available to us. We can use them along with our TensorFlow library, because TensorFlow is nothing but one of the libraries. Okay, let's say we create some random data, test data or artificial data, and this is how you create linearly separated or evenly separated random values, right? Lid space is basically you create random values between 0 and 10 and 10 random values, and they are linearly or evenly distributed. That's what we are doing here. And we are adding some, to give it a little flavor of realness, we are adding some random values as well. Okay, so that is what we are doing here. So this is how the data looks, x underscore data, which is our independent variables, and similarly we are creating some random values of dependent variable as well, right? Y underscore label is our dependent variable. So if we do this and then if we plot, this is how our data looks, right? So if we did not add these randomness, then you would have actually got all the dots in a straight line. So we don't want that. So that's the reason we are adding the randomness as well. So this is how it looks. Now we want to find the best fit for this. All right. And again, some of you are not familiar with machine learning concepts of linear regression and so on. You may want to watch some of our other videos where we have created basics of machine learning and so on. The concept of linear regression, all the algorithms are explained there in detail. But very briefly here, what is a linear regression? Linear regression is the best fit. So you need to come up with an equation of a line which will basically, let's say, pass through these data points in such a way that the error is very minimal, right? So the line obviously will not pass through all the data points, but it will lie somewhere in between, and when you calculate error, it will be minimal. That's the idea of training this. Okay, so how do we do it in using TensorFlow? So we assign some variables. So m is a variable and b is another variable. Remember, this is how we create these variables, right? So tf dot variable tf, because we are creating variables, by the way, because they cannot be constants. The values cannot be fixed. And why are these values 0.39 and 0.2? Again, these are randomly generated. We just use an NumPy random function and we generated this. It can be anything. Initially you can give anything. 0 also can be given, but just to keep it realistic, we actually create some random numbers and assign them those values. Okay, then we find out what is known as the cost function. What is the cost function? Cost function is nothing but the error between the actual value and the calculated value. So with the given values of x, if we feed to this model, it will calculate based on the value of m at any given point in time. It will create what is known as the predicted value, which is y underscore hat. So in this case, when the first run, it will be 0.39 into whatever is the value of x plus 0.2. Okay, and remember, these values will change. That's why I have given as variable. They will not be constant. And the whole training process is to change these values and then come up at the end with some set of values of m and b, such that if you use that in this equation of mx plus b, then the errors will be minimum. That is the idea behind linear regression. Again, this is a little difficult to explain here, but if you actually watch our video on linear regression, it will probably become more clear. So here the assumption is that you are familiar with linear regression. Okay, so the error obviously will be the difference between the calculated value and the actual value. As we all know, we square that. So this indicates a squaring of that so that the negative values don't come into play. All right. Then for training purpose, you need to use an optimizer. So what is optimizer? In our case, it is a gradient descent optimizer, and we need to specify the learning rate. So you give the learning rate as, in this case, we are giving as 0.001. Remember what we are doing here. We are just creating a node. None of these are being executed as of now. We are just creating the graph consisting of nodes. So let me go back. Here what I have done is M is created as a node, B is created as a node, and similarly here optimizer is created as a node, which I will show you a little later. And then when we say train, that is again another node, it will call this optimizer function and so on, right? So this is not directly running, but we are just creating the graph, and then this is where we will actually run that graph, and that is where the code will actually get executed. Now before that, one important thing to be remembered: in TensorFlow, whenever you create variables, you need to create a node for initializing the variables, which will be executed in this session. Okay, whatever you can call anything here, this is just a name, but typically it would be called init, and we say tf dot global underscore variables underscore initializer. So all the variables that you would have created anywhere, they get initialized, and it is very important, and it is only for variables. Let's say in your code you only have constants and placeholders, then this line of code is not required. But if the moment you have variables, you have to include this line. Basically, what are you doing here? You're creating a node or an operation. You're not executing anything. You need to create an operation and then execute the operation within your session here. Okay, so this is something you need to remember. So you need to initialize the variables. So this is like you can write once and keep copying and pasting. That's it, right? Because you have this anytime you have variables. Now, all programs may not have variables. So there may be some in your test when you're doing some initial development. You may only do with constants and placeholders. Then you will not need it. But anytime you have variables, you need to do. Okay. All right. Good. So then the next step is to create a session. How do you create a session? This is kind of very, in a way, unique to TensorFlow. You use what is known as a with block. So we say with tf.session as ses, right? So in other words, it is somewhat saying like ses is equal to tf.session. You remember there are a couple of constructs for creating session. Like in the previous example we saw, let me go back here. So here we just directly said ses is equal to tf.session. This is one way of creating a session. But here what we need to remember is at some point, once you're finished with all the code, you need to close the session. Okay. So whereas if you're using something like this with block, you don't have to close the session, because the moment the with block gets completed, right, the session will automatically get closed. So that is the difference and the advantages and disadvantages of using a with block or not a with block. Okay. So here what we are saying is with tf.session as ses. That means it is indirectly we are saying create a session by the name SESS, and as long as this with block is running, keep it active. The moment it gets, I exit this with block, you close the session, right? So you don't have to explicitly close the session. Okay. Anyway, so to start with, for beginners, just remember you just have to create a with block and then put the code within that with block and you're good. That's it. Okay. All right. So first thing is to start with the initial with block like this. This is the syntax. Then the first line of code will be to initialize the variables. Again, only if you have variables. If you don't have variables, you don't have to write these two lines of code. Okay. Then the next is you need to run this training method, right? So remember, as I said, we have created all the nodes and pretty much train was our last node, and there are all other nodes which are dependent, or rather the prerequisites, right, for train. Train is my kind of the last part of the node. So that is what I will do a run on, because that will give me the results, right? This in turn will execute the rest of the graph. So this train will go back and it will say, oh, okay, I need to do optimizer.minimize. And what is optimizer? Optimizer is gradient descent with a learning rate of 0.001. And then for doing this gradient descent, I have to use this model, which is mx plus b. So I need to calculate and keep changing the values of m and b and feed the values of x and y and so on. So it's like a chain reaction that that happens, and ultimately the training gets over, and then you have the values of M and B. Remember, the whole exercise of actually training this is to come up with the right values of M and B. Initially we start with some random values, which is in this case 0.39 and 0.2 for M and B, but the training process, if you have done the machine learning module, you will see that training process basically involves changing these values of M and B so that the error is minimum. So at the end of this part, which is the running of the training session, you will end up with certain values of M and B. Now how do you get those values of M and B? Again, you need to run the session, and this is just a one time, and you say, okay, give me the values of M and B. Okay, so this is all, by the way, this is all within the with block. So the session is still active. Here you're saying run the training method, so it will run the training method, and the training method in turn will keep changing the M and B values based on the error that it is generating, the model is generating. And once the training is completed, and how does the system know the training is completed? We are specifying the epochs. Again, you must have done the machine learning module, so you will be familiar with epochs. Epochs are nothing but how many iterations you need to do. If you pass all the 1000 observations through the model for training, that is called one epoch. And so if you take this 1000 observations and pass it through the training model 100 times, that is 100 epochs. So that is what we are saying here. We are asking epochs is equal to 100. That means you pass this training data through our model 100 times. Once 100 times are over, it will exit. And remember, every epoch, the values of M and B will keep changing so that it is the error gets optimized or error gets reduced. So at the end of the training session, M and B values will have something different from what it has started off with. So those are the values that we will need here, which is basically M is the slope and B is the intercept. So that is the end of the training process. So we can basically display those details. And now you can use this to plot your model, the line that you got, the best fit line that you got. You can use the plot method to plot the line, best fit line. And you will see here, typically this is how it would be, right? So it is passing kind of in between all the data points, so that any point you take, if you calculate the error, it is minimal compared to, let's say, if the line was here, obviously many of them or most of them would have been errors and the error value would have been huge. So that's how you evaluate the results. All right, so this is my Jupyter notebook, and whatever I've shown you in the slide about the linear regression, I will just quickly show you in the actual code as a demo. So we have seen that what we are trying to do is create a model, which is a linear regression model, and train it and then test it. So this is the first section, which is importing the required libraries. And what we're doing here, as you can see, is we have regular NumPy, and we will be using that for doing some generation of data and so on. Then we have matplotlib to plot the results, and then of course we are importing the TensorFlow, which is what we are going to use for creating this linear regression model. So as a first step, we will create some artificial data, which is basically some kind of a dummy data, and we are just using NumPy to do that, and random number generator and a linspace to create some data. So this is how our x underscore data looks, which is our independent data, and the dependent data is y underscore label, which is the label data. In other words, we can also call it as label data, and we have created that, and this is how our data looks if we plot it, x and y. If we plot it, just a quick note, this randomness I also mentioned in the slides, this random form is just added so that the data doesn't look like it is artificial, right? So right now, if you see here, now it looks pretty much like some natural data. Okay, so what do we do now? Next step is to first create some variables, which are basically for our y is equal to mx plus b equation, m and b are the variables. Now there are two ways of doing it. You could have created variables with some 0 or something, both of them being 0, because you need to start with some random value. In our case, what we are doing is we are actually generating a couple of random values, random numbers, using the NumPy random function, and we are assigning these two variables, right? So we created one value is 0.25 and another is 0.3, and since this is random, I can change this, but I will not change. Let's assume that this is 0.39, and I can actually, no, let us just change it so you are not confused, because every time you generate a random number, it can be any value. So it is 0.30 and 0.256. Alright, so I will now assign these two. I am creating these as TensorFlow variables. I hope you remember that in the slide I have shown you. These are the two variables. Then we need to create what is known as the cost function. And cost function is nothing but the difference between the generated value or the predicted value or the value created by the model and the actual value. So that is the error, that is the difference between that. And to avoid negative value, we do a square of that. So that's what I have shown in the slides as well. Then we have to define an optimizer. In our case, we will go for a gradient descent optimizer and with the learning rate of 0.001. All right. So remember, all this, what we are doing is we are creating a graph. This is not yet executed in TensorFlow. We are executing in Python, of course, but from a TensorFlow perspective, it is not yet executed. Only in session it will get executed. Right now we are creating a graph. So we created the graph for the training, for optimizer, for the initialize operation. We are creating an operation or a node. Okay, now that's all. It's all done. Now we created all the nodes. We created the graph. Now we have to execute the graph. So this is how we execute the graph. We create a session using tf.session, and then we specify how many iterations or epochs, which is 100, and then we run this. We run the train node. You remember there is the node for train we created, which in turn will go back and assign all the variables and all that stuff. Okay, so once the training is done, it runs for 100 epochs. Then we have certain values of m and b, right? That's the whole process of training. You start off with some random values of m and b, and the training will actually change those values and come up with a particular value of m and b such that the error is minimum. So we are done with that. And now we can check the values of, okay, I think we did not run this, sorry. So we have to run this. So this is run now. So the training is done. So now we will have a value in final underscore slope, which is equal to 0.87. And then in the intercept as well, 0.83. Okay. So we got m and b that we wanted. Now we want to evaluate the result. So we want to see using our test data whether this is doing, how this is doing. So we just generate some test data as well. And this is our test data looks. And if we draw the plot of our model, this is how it looks. So pretty much expected. The line lies in between all the data points. And this is the best fit line such that the error is minimal. All right, so let's go back to the presentation. Now let's talk a little bit about recurrent neural networks. So neural networks are of different types. We have CNN, we have RNN, ANN, so on. Now RNN is one type of neural network. RNN stands for recurrent neural network. The networks like CNN and ANN are feed-forward network, which means that the information pretty much only goes from left to right or from front to back, whichever way you call it. Whereas in case of recurrent neural network, there will be some information traveling backwards as well. So that is why it is known as a recurrent neural network. And each of these types have a specific application. So for example, convolutional neural networks or CNN are very good for doing image processing and object detection using for video and images. Whereas recurrent neural networks are pretty good for doing NLP or speech recognition and so on. Okay. So for the next few minutes, we will kind of focus on recurrent neural networks, and we will see an example of how we can use RNN to do a time series analysis. So in a typical neural network, this is how it looks, right? So where you have a neuron and then the inputs are coming to the neuron, and then you have an output which goes to other neurons in the other layers. In case of recurrent neural network, what happens is you have the inputs, let's say at a given point in time, but then a part of the previous output also gets fed in along with the inputs for the given time. Now this can be a little confusing. So let's see if we can take a little expanded view of this. So this is another view of one single neuron, which is what is known as in an unfolded manner. Okay. So if we are getting inputs or data over a period of time, then this is how the neuron will look. Remember, these are not three neurons. This is one neuron, and it is what is known as, it is shown in a unfolded way. Okay. We have unfolded this single neuron over a period of time. So at a given time, let's say t minus 1, an input of xt minus 1 is fed to the neuron, and it gets an output of yt minus 1. Then the next instant, which is xt at a time t, right? There is an input of xt, and then there is an output of yt. So this is a single neuron, but is displayed in an unfolded way. So this is like expanding it over a period of time. So let's start with this part here. This particular neuron gets an an input at an instant t minus 1, let's say time is equal to t minus 1, it gets an input of xt minus 1 and it gives an output of yt minus 1. Then when we go to the instant t, here it gets an input of xt and it also additionally gets an input from this previous time frame t minus 1. So this yt minus 1 gets fed here and that results in yt. Alright, then when we go to the time t plus 1, there is an input of xt minus 1 at that given time plus the input from the previous time frame, which is a time frame of t, that also gets fed in here, and then we get an output of yt plus 1. Okay, so let me explain once again. This is a single neuron. These are not three different neurons. A single neuron seen over a period of time from t minus 1 to t plus 1. And unlike a regular feed forward neuron which only gets x, in this case the input is x and also another input which is coming from the previous time frame, and that is what this loop is. In this, on the left hand side diagram, this loop is indicating that. Okay, so on the right hand side it is represented in an unfolded way. Okay, so the input, if we take a time frame t for example, is not only xt, which is the input, which is the normal input at the time frame t, but it is also getting an input from the previous time frame, which is this yt minus 1 is also being fed as an input. That is the key differentiator here. Okay, similarly at the instant t plus 1, it is getting a normal input of xt plus 1 plus this yt is actually being fed here, and then the output comes as yt plus 1. Okay, so this is the construct of a recurrent neural network. Now recurrent neural networks again can be of different subtypes. It can be one-to-one, one-to-many, many-to-one, and many-to-many, depending on what kind of application we want to use. One of the examples is like the stock price. So you're feeding, so there is only one input. Only thing is it is spread over a period of time. So you're feeding the stock price input. That is what comes here as an input. And you get an output, which is again the stock price, which is probably predicted over the next 2 days, or 3 days, or 10 days, or whatever. So the number of outputs and inputs is the same. There is only one input, there is only one output. Only thing is it is spread over a time. So variables are not many. Then you have one-to-many. So there is one input, but you're expecting multiple outputs. What is an example of this? Let's say you want to caption an image. So how do you want to do that? What is the input that will go here? It's just an image, which is one input. But what is the output you're looking for? You're looking for a phrase maybe, right? Not just a word, but a phrase. So it's like cat is sitting on a mat, right? So the image is, there is only one image which consists of the cat sitting on a mat, but the output are like maybe 3 or 4 words, which is saying the cat is sitting on a mat. So this is one-to-many, right? Then you can have many-to-one. Examples of this are like you're feeding some text and you want to know the output, whether the text is, what kind of sentiment is expressed by the text. It could be positive, it could be negative. So that's the output you're looking for. So you feed a large number of words, maybe the text may consist of words or lines or whatever. So that is what is the multiple inputs. But the output, all it says is the sentiment is positive. So it is just one output, or the sentiment is negative, just one output, right? So this is many-to-one. Then we have many-to-many. So what is an example of this? Let's say you want to do some translation. So how do you do a translation? You feed in a sentence maybe in a particular language, English, and then you want a sentence actually in another language. So that is like there are multiple inputs. One sentence can consist of multiple words, and the output also is a sentence consisting of multiple words. All right. So how do we implement RNN? This is an example of implementing an RNN for a particular use case. So in our particular example, we have the data about milk production over a few months, and using RNN, we want to predict, because this is time series analysis. So RNN is good to do time series analysis. So using RNN, we want to predict what will be the milk production in the future. So let us see how we can do that. I will first take you quickly through the slides, and then I will actually run this in a Jupyter notebook. The code, I will run it in the Jupyter notebook. So this is how it looks, the code looks. So while this is TensorFlow, you still use the standard Python libraries like NumPy and Pandas and even Matplotlib to do some initial processing, getting the data, processing it, cleaning it, whatever. All that can be still done within the same program. So that's what we're doing here. We're importing some libraries like NumPy and Pandas, and then we read the data file. And if we plot the data, we see here it is the data for the years 1962 to 75, and we can see that there is a certain trend, right? So this is how a typical time series data would look. Again, some of you, if you're not familiar with time series and time series analysis and so on, I would recommend you to go through some videos around that, which will make it easy to understand this. So this is how a typical time series data would look. In this case, it is nothing but there is only one variable, which is milk production, and it is spread across several years. So it's going from 1962 to 75, and that value has been plotted. So if you see, there is a certain kind of a trend here, which is basically going upwards, and there will be some seasonality. So time series data has these three components, right? So it will have a trend, it will have a seasonality, and then it will have some randomness. So that's what this graph is showing. And now if we want to perform analysis on this, time series analysis on this, first thing we need to do is split the data into train and test. And in this case, we will just use a straightforward method, which is taking the data for the first 13 years. So the idea here is we need to train our model, right? This is time series data. So and we want to predict for the future. So the way we need to use this is we have to take the data for a certain period of time and train our model. And then we use a part of the known data so that we can then ask our model to predict for that duration and compare it with the known information. So what do we mean by that? So here, if you see this data, I will show you in the notebook as well, Jupyter notebook as well. This has 13 years of data. So what we are doing is we are taking the first 12 years and using that as our training set, right? So 12 years we are doing, and this has about, I think, 14 years of data. So we are taking 13 years of data for training purpose, and then we are using the last 1 year, remaining 1 year of data for testing purpose. Because here what we can do is this 1 year data, we know the values, right? Because if we want to compare the accuracy or anything like that, we need to know the values. So in this case, we know the values of this one particular year. So we will use that. But at the same time, we train the model for 13 years of data. And for the 14th year, we will ask our model to predict and then compare it with this known value so that we know how accurate our model is. I hope that makes sense. Okay. So that's what we are doing here. 156 is nothing but 12 into 13. On a monthly basis, we get the data. The next step is to scale the data. This is all regular data manipulation, data munching activity. And then you split it. You are basically assigning the train and test data to the scaled variables. And then you need to read the data in batches. So it is very important, as I mentioned earlier also, that instead of reading the entire data in one shot, you feed the data in batches. So in order to do that, we are writing a function for that. That's all we are doing here. So that is still here. What we have done is regular Python programming. There is no TensorFlow as of now here. Okay, so far what we have done is preparation, data munching. Now what we are doing is actually training our model. So this is where TensorFlow now comes into picture. So we are importing, first step is to import the TensorFlow library. So this is how you do it, import TensorFlow STF. And then you can define some variables or constants, whichever way. Now here, of course, there are a couple of ways of doing it. You can create them as TensorFlow nodes, but that is a little bit of an overhead. We will just use the regular Python variables or constants. So here I am creating regular Python variables and I'm saying number of inputs is 1. So instead of hard coding, I'm just storing them as variables. So this is number of inputs is 1, number of time steps is 12, number of neurons is 100, and so on, right? And then learning rate is 0.03 and number of iterations we are saying is 4000. Then we create placeholders. Now we will be storing the independent variables in X and the dependent variables in Y, and this we will read from an external file. Remember, I told you placeholders are used for getting data from outside and then feeding it to our model. So that's the reason we have two placeholders, one for reading the X values and another for reading the Y values. In this step, we are only just creating the nodes, right? So this is just creating the graph. And similarly, we are mentioning what is the loss function and what is the optimizer and how to run the optimizer. And once that is done, you are initializing the variables and then you're creating a saver variable or a saver instance. So saver is basically nothing but in machine learning, you can train your model and you can save it for later use. So that's where the saving comes into play. We will see how to use that as well. And then the last step is to create your session and run this graph. right? So we are initializing the variables. Remember this, we run init, so which is nothing but this one. So we are initializing the variables, whatever are there. Instead of hard coding, remember in earlier case we were hard coding how many iterations. So here we are saying for the given number of iterations which are stored in this, maybe how many iterations we said is, what is the value of iterations? This is training iterations is 4000. So we specify that based on the number of training iterations. Next batch will basically fetch the data and then we run the session. We are basically saying train is the node which we will run in the session, and this will basically train our model, and this is more for printing. Every 100 times you print it. That's all. There's nothing more to it. So for example, the output would look somewhat like this. This is for 0, this for 100, next for 200 and so on. Okay. And then you save the model. You remember saver we created. So you save the model for later use. So this is our test data. Remember, we are doing this on training data, right? So once the training is done, we then try to create the inference on the test data so that we can compare how accurate this is. Right. So this is how the test set would look, and then we will basically restore this model, okay, because in the previous slide we created the model and we stored it. So now we have to restore the model and then run our test data against it and see what are the values that are predicted, what are the y values, and then compare with x to see the accuracy. So train seed is what we are seeing here. So that is what will have the predicted values, and these predicted values, what we want to do is we want to create an additional column, because remember we need to compare, because we want to find out the accuracy of this model. So we need to compare the predicted values with the actual value. So what we are doing here is adding another column called generated and assign a value to that. All right, so this is the result of the prediction, and then if we need to reshape, because we have to show this in the form of monthly results. So that's what we are doing here, and once we generate the results and then display it, we can actually see it month wise here, and the actual and the generated values. Okay, so we create a data frame which is a combination of the actual values and the predicted values from the test set. And then we can plot to see how the trend is. As you can see, pretty much the actual value is in blue color and the generated or predicted value, the curve is in yellow color. The trend is maintained. So it will probably, it's not 100% accurate, but the trend is maintained. All right, so let's do one thing. Let's go into the Jupyter notebook and take a look at how this works in TensorFlow environment. Actually, the code, I will walk you through the code. This is my Jupyter notebook, and the data is taken from this particular link. In case you're interested, you can download it from there. And this is the data for the years 1962 to 75. The first thing we do is import these libraries, because before we start with the actual TensorFlow activity, we need to prepare the data and so on. So for that, you can use your regular Python libraries, which are like NumPy, Pandas, and so on. So that's what we are doing here. And then we read the data using Pandas into a data frame. So this is a data frame, milk is a data frame, and we will do some quick exploratory analysis just to see how our data is looking. Initial 5 records that we'll get, 1, 2, 3, 4, 5, that is the head. So it goes from 1962 January to 1962 May. Once we rechange, or basically we need to split this into month specifically separately. So that's what we are doing here, date to time. So we kind of do a little bit of a reindexing, and then if we plot this, this is how the data look. As you can see, there is a clear upward trend, and there is some seasonality and so on, but anyway, we will not break that up into those components. We will just use RNN to predict and test. Okay, so the next thing is to check some, if we can do run like an info, it will tell us what is the information about this data set. So let us just run that. Okay, so it is just telling us how many total columns and what is the size of the file and so on and so forth. Again, in case you're interested in doing some exploratory analysis. So what we'll do next is we will take the 13 years of data for our training data set. So what are we going to do now? Let me step back. So what have we seen here? We have seen that there are 168 records, so which is nothing but 14 years of data. We now have to split this into our training and test data set. So how do we do that? I think in case of time series, we cannot do it like 80-20 like we do in normal splitting in normal machine learning process. Here it is time series data.
So what we are going to do is we will take out of this 14 years, we will take the first 13 years of data and we will use that for training, and then we will test it with the last, which is the 14th year data. We will use it for testing. Okay, so that's what we are going to do here. So let's split that. So training set will consist of my 156 records, which is nothing but 13 into 12, right? My 13 years of data I'm taking for training, and then my test set will consist of the bottom 12 observations, which is last 1 year of data, which is the 14th year. Okay, so that's now done. Training and test splitting is done. The next step is to do some normalizing, which is basically we'll use our scaling, rather we will use min-max scaler, and we will just scale the data. And now we do it for both test as well as train. Now we are ready to create our RNN model. But before that, one quick thing: in order to fetch the data, we have to create a function. So that's what we are doing here. We create a function called next batch, and how you want to fetch the steps, they are all defined as our constants, if you remember, and that's what this function is all about. So we define that function. We will be calling that in our training method. All right, so from here onwards up to there, we are done with the preparation of the data and whatever functions or whatever are required. From here onwards is where the TensorFlow part starts. So the first thing we do is import the TensorFlow library. Typically, this is a very standard way of importing the library. We say import TensorFlow as TF. Now TF is nothing but a name, so you can change it to TF1 or ABC or XYZ, whatever. So this part you can change, but by and large everybody uses this, so I would rather recommend you also use the same syntax. So you say import TensorFlow as TF, so it's very easy for others to understand as well. And then you declare or define a bunch of constants. That's what we are doing here. Like for example, the number of time steps, in this case it is 12, number of neurons, there are 100, number of outputs, it is only 1, and so on, right? And then the learning rate and all that, we are declaring or defining those variables in this particular block. Next is to create placeholders. You remember the placeholders are used for feeding the data. So we have X and Y. X is for the input, which is the independent variable, and Y is the output, which is the dependent variable. And in our case, these are not different characteristics or features, but it is the same one feature or one variable, but it is over a period of time. So that's the only difference. So that's what we are doing here. And now we need to create our network, right? The neural network. So in our case, we said we will create a RNN layer. Now there are different ways or different formats of RNN, which is probably not in scope of this module. So for now, we will just assume we are creating one RNN layer, and one type of RNN is GRU cell. So we will use GRU cell, and we use this APIs for creating our layer. So each cell will be with an output projection wrapper. There is a need for doing that. And again, the details of this we will probably do in another video where we talk in detail about RNN. So for now, we are creating a GRU cell with the wrapper, and the syntax for creating the GRU cell is like this: the number of units, which we said there should be 100 neurons. What will be the activation function? In this case, it is ReLU, and then number of outputs. In our case, it is only 1. Okay, so we create the cell here. Okay, then we got the GRU cell, and then we say what is our output, which is nothing but we get the outputs and the states and their states, and which is the way we get that is tf.nnn.dynamic_rnn. So if we call this and we pass the cell and the data, which is basically in placeholder. So again, remember, all we are doing here is we are creating just the nodes for the graph. So nothing is actually getting executed from a TensorFlow perspective. Okay. All right. So once that is done, now we need to pass this, calculate the outputs and the states using the dynamic_rnn method, and we pass the cell as a parameter and then the x values as a parameter. And if we run that, we will have the outputs and the states. And this is where we actually run the training method. So, or create, not really run the training method, but we create the nodes for the training and the optimizer. Then we have the initialization of the variables, and we save this
model. We create a saver object just to save the model because we will then restore it and run it to do our predictions. So this is what we will do here. So that is another node, and this is where we actually create a session and run the training. Okay, so let's go ahead and do that. That will take a little while because we said 4,000 iterations. So we will allow it to finish. We will probably come back once the training is completed. Alright, so the training is done. Now let's go and run this on the test data. So let's just quickly take a look at the test data set. So this is our 1 year data for the year of 1975. So if we see this is from January, February and so on. And we will pass this to our model. So what are we doing here? We are restoring the model here, for example. Right? This is the path that we have given when we were saving the model. Let's go back once and show you. Let me show you where we did the saving of the model. Yes, so we saved the model here. So that again we will restore that and we will use that to run it on our test data and see how well it predicts. So let's go ahead and run this, and this is just 12 records, so this will not take time. Remember I told you training is what takes a lot of time. The regular inference, this is called inference, doesn't take much time, right? So it just depends on how much data. There were only 12 records here, so it was very quick. But in training, what we do, we pass this multiple times. There are iterations, 4,000 iterations we did, for example. So that takes longer. And in general, in machine learning, deep learning, training is what takes the maximum amount of time. All right, so let's go ahead and see the results. We will, in order to plot it, we will have to kind of adjust the format of the results. Otherwise, we will not be able to see it in a proper way. And then we will, so this is our, so what we have done is we created a data frame which consists of the predicted value and the actual value. So this is the data frame. So this is the actual value, this 834, 782 and so on. This is what our model has predicted. So it may not be so easy to see in a tabular format. So let's go ahead and plot it so that we can compare these two. So when we plot it, you will see that the trend is more or less maintained, right? So we go from the blue color is the actual values and the yellow color or the orange color, whatever is it, is the one which is generated by our model. So it pretty much is following the actual trend. So not bad for such a quick iteration and training. So that is basically it.
Although deep learning is been around for a while, it is just in its infant stages of development as far as exploding on the market. I mean, it is. Right now, they're building robots with it. Deep learning is used to train robots to perform human tasks. Music composition. Deep neural nets can be used to produce music by making computers learn the patterns involved in composing music. Image colorization. Neural network recognizes objects and uses information from the images to color them. Machine translation. Given a word, phrase, or a sentence in one language, neural networks automatically translate them into another language. Google Translate is one such popular machine translator you may have come across. And you'll notice in here we didn't show any examples of straight numbers like projective cells in a business, tracking your favorite stock. You can certainly do those with machine languages, but this is the next level. Save that for your regression models, your linear regression, where you're actually processing and crunching just straight numbers. With machine learning and deep learning, we're going to a whole new level as far as what we can figure out on the computer. What's in it for you? We're going to cover what is deep learning. We're going to take a look at the biological versus artificial intelligence. What is neural network, activation function in your neural network, and the cost function, and how do neural networks work? How do neural networks learn? So there's a little, you'll see a switch right there. We just went from how are they working in the math in the background to exactly how are they learning. We'll be implementing the neural network. We'll do a gradient descent, deep learning platforms, and we'll give an introduction to TensorFlow and implementation in TensorFlow. That's Google's platform that they open sourced recently, and it's probably one of the most cutting edges in deep learning. And even it is still in the infant stage, which is one of the reasons they released it to open source. What is deep learning? Deep learning is a subfield of machine learning that deals with algorithms inspired by the structure and function of the brain. And you can see we have a nice picture here. We have artificial intelligence, which is kind of the big bubble that encompasses all these different things we're talking about. This is the ability of a machine to imitate intelligent human behavior. And in there we have machine learning, application of AI that allows a system to automatically learn and improve from experience. And if you looked at any of our other videos, you'll know that machine learning covers a lot. So deep learning is a subcategory of that, but don't forget machine learning has all kinds of other tools that people use to do very basic descriptive and predictive and postscriptive analytics. And then you have deep learning, application of machine learning that uses complex algorithms and deep neural nets to train a model. Let's take a look at the biological neuron versus the artificial neuron. Now remember, in the human brain, and this is true for most animals, there are a lot of different neurons going on. So this is the very basic one. I mean, there's hundreds of different cells involved. So when we talk about neural networks, and this is why I say it's in a very infant stage, they're really basing it on just the most basic thing that we're able to figure out going on in the neural networks. And you can see right here we have dendrites fetch information from an adjacent neurons and pass them on as inputs. So you have your data coming in and your data going out. Any computer model should be looking at that. What's coming in, what's going out. The data is fed as an input to the neuron. So when we look at the artificial neuron, you can see we have our inputs. They come in, each one is specially weighted into the neuron, and then the neuron has an output. The cell nucleus processes the information received from the dendrites, and the neuron processes the information provided as inputs. Axons are the cables over which the information is transmitted, and the information is transferred over weighted channels. So you can look at that. I mentioned weights briefly, but you alter the data coming in. So those weights are what causes different information coming in to be weighted differently and processed differently. And the synapses receive the information from the axons and transmit it to the adjacent neurons. That's in your biological model. And then when we look at the artificial neuron, the output is a final value predicted by the artificial neuron. So as we dig deeper into looking at the theory behind the neural network, and we kind of flip back and forth between these because there's two huge aspects of it. One is from the outside, what are you seeing, and what's going on from the inside, so you can find to do what you need to do and give the best results you can. And we start off with what do we feed? We feed an unlabeled image to a machine which identifies it without any human intervention. And so you can see here we have a circle that comes in at 784 pixels, and it comes in by 28 by 28. And you can see how it colors in the circle on there. And then we put a triangle in. The triangle in also comes in as 28 by 28, and it has 784 pixels. So you'll see between these two, both of them are 784 pixels. This machine is intelligent enough to differentiate between the various shapes. So that's what we want to use our neural network to do, is to say, hey, this is a circle, this is a triangle. And that's more of a categorical. You can also do a regression model where you're actually putting out a float value or a numerical value. We'll be looking at the true-false or the categorical model mostly, because that's where you usually start at. There is no real difference when you, as far as the way the internal functioning goes, when you start flipping between them, other than, well, we'll talk about that in just a minute. So you can actually go between the two quite easily. And the neural network provides this capability. So we're going to use this capability to look between those two. One of the things I want you to note in here is that we're looking at 784 pixels. We're looking at 784 inputs. That's very different than stock with a high-low or last year's cells based on date, where we're looking at just a couple of numbers, and they're very clear. They're numbers. They're very clear what they are, which is something you'd put into a machine learning linear regression model. This is a step up from that in that we're looking at complex patterns, and how do you figure those complex patterns out? So a neural network is a system modeled on the human brain. And we looked at that, comparing the two. Let's go ahead and look deeper into the neural network itself. We have our inputs coming in. So the inputs are fed to a neuron that processes the data and gives us an output. Input and output. This is the most basic structure of a neural network known as a perceptron. So if you see the term perceptron, that's what we're talking about. We're talking about this single node that has inputs and an output. However, neural networks are usually much more complex. Let's start with visualizing a neural network as a black box. And I always love that symbol. It's a black box. It's kind of magical. We have our inputs coming in, and we want certain outputs. The box takes inputs, processes them, and gives an output. Let's have a look at what happens within this box. And you can see me there in my secret agent getup. I got my hidden hood and everything. I guess I'm part of the Black Skull or something like that group. So let's take a look at what happens within this magic box. And remember, we're skipping back and forth between the theory of what's going on in the box, which you have to know how to fine tune and how to build, versus looking at it from the outside. We're programming this box and we have an input and an output to the box as a whole. Within the box exists a network that is a core of deep learning. And you can see here we're showing one layer and we have our grid coming in. The network consists of layers of neurons. Each neuron is associated with a number called the bias. And you can think of the bias, if you overly simplify this and we're doing a linear regression model, this is your y-intercept in your Euclidean geometry. You have to have something that offsets it. And so you always have a bias in these cells. Neurons of each layer transmit information to neurons of the next layer over channels. And so you can see each of our layers going through from left to right. These channels are associated with numbers called weights. These weights, along with the biases, determine the information that is passed over from the neuron to neuron. So just like the bias is your y-intercept in Euclidean geometry, you could look at the one weight. Remember, this is very complicated, so we're not looking at just one weight. You could look at the weight as your slope of the line. Or if you're doing x equals my plus c, it would be the m value. Neurons of each layer transmit information to neurons of the next layer. And you can see here as they light up going across into the final layer, and then to the output. And in this case, the output is going to be either a square in this one, or it might light up the other one, which is a circle. The output layer emits a predicted output. So in this case, we're looking at a classification, true, false. Is it a circle? Is it a triangle? Is it a square? Let's now go deeper what happens within the neuron. So we're going to dig deeper and start getting a little bit closer to some of the math. Don't worry, you don't have to be a calculus expert or know your differential equations. Even though this is one giant differential equation, you don't need to understand those to understand what's going on. Within each neuron, the following operations are performed. The product of each input and the weight of the channel it's passed over is found. This is simply addition. We're going to sum up the weight times the output from the previous channel, and plus the bias. Sum of the weighted products is computed. This is called the weighted sum. Bias, unique to the neuron, is added to the weighted sum. The final sum is then subjected to the particular function. And we'll discuss that particular function. That part is really important because those functions have a huge impact on how well your model performs under different conditions. The final sum is then subjected to a particular function. This is the activation function. So if you ever hear the term activation function, that's what we're talking about. What activates this cell and what doesn't. As we dig deeper into activation function, an activation function takes the weighted sum of the input as its input, adds a bias, and provides an output. And a lot of times you'll actually see one formula for the sum of the weighted sum and the bias. You'll just see that as a single line of everything added together. And here we've broken it apart because it makes it clear that this bias is not computed the same as the weighted sums. Here are the most popular types of activation function. And I always find these interesting because at one point I was sitting at a table with a gentleman who was finishing his PhD. He was in his last year, and he said he went through all this stuff and he ended up just trying the 4 different activation functions on this particular problem he was working on. So knowing the math behind it doesn't necessarily mean you're going to know it right away. So even somebody who might have a PhD and be doing the calculations on this comes back out of it and ends up just trying the different activation functions to see what's going to make a difference. And a lot of times that's a final step. That's the kind of thing where you built your whole model, you've come back and you're like, wait a minute, can I do a better deal with a sigmoid function or the threshold or the rectifier? Knowing what they're doing is important so you can explain it to somebody else. And again, you probably do this on a small set of data. If you're working with big data, you don't want to take down the full server farm just to test out your 3 different series. You take a small portion of that data, test it, and then you put it through to the big data. So let's take a look at this. We have the sigmoid function, and it's used for models where we have to predict the probability as an output. It exists between 0 and 1. And you'll see that's true of all of our activation functions we're working with. Either the cell's on or off. It's true or false. And there might be a little variation in there, which as an output could be used to compute uncertainty in your solution. So if you're getting a 0.7 with this activation function, it might be, well, I'm not sure if that's really a square, or I'm not sure that's really a triangle. And that might be a flag for it to be looked at by a human observer, at least in today's models where we're at right now. And you can see here where we have the formula is simply equals 1 over 1 plus e to the minus x, where x is your value coming in, and it's going to give you a result that looks very similar to the graph on there, which is somewhere between 0 and 1, and right in the middle you can see that there's a huge you can go through all the different values and uncertainties involved. So the sigmoid function is probably the default on most of them. The next one is the threshold function. It is a threshold-based activation function. If x value is greater than a certain value, the function is activated and fired, else not. Pretty straightforward. Yes, no, true, false. I don't want to test for improbabilities. I just want a straight answer. I don't want to know if there's a partial value on there. It either is true or it's false. And the rectifier function, it is the most widely used activation function. I would debate that. Rectifier is a pretty common one, although I see the sigmoid function used to be the basic one, but it's up there. The rectifier function is very commonly used. It gives the output of x if x is positive and 0 otherwise, and you can see here again, just like it's either kind of get a value going up there, so max of x of 0. So it's like the threshold function. Yes, no, true, false. It's either 0 or it's some kind of progressive value. And then we have the rectifier function. I would argue with this because the sigmoid function used to be the most common one, but with the rectifier function, it now says it is the most commonly used or widely used activation function and gives an output of x if x is positive and 0 otherwise. This is kind of nice because it now says absolutely not, or it gives you a value of probability. Now when I say a value of probability, be very careful there. I'm not saying that it's going to tell you this is 75% chance of being a circle. I'm going to tell you that it says, hey, if this says 0.1, it probably needs to be looked at, or 0.2 or 0.3. It's going to depend on your data as to what that value means. In general, that just means it's flagging it that if it's not a 1, then chances are it needs to be looked at by a person and reevaluated. And there's a hyperbolic tangent function. This function is similar to sigmoid function, is bound to a range of -1 to 1. So you can see there's our 1 minus e to the minus 2x and 1 plus over 1 plus e to the minus 2x. Again, it's very similar to the sigmoid function. The bonus of the hyperbolic function is you have that variable coming through the middle. So again, you can look at it and you have a little bit more weight as far as you can process that down the line. That's a little bit more advanced than what we're looking at right now, and a lot of times it's not even necessary in a lot of our different uses for these activation functions. Now, we looked at activation functions, and I kind of said those are a little bit like a black box, because even if you know all the math, a lot of times you end up just playing with them to find out what works, and it also depends on what model you're working with, whether you need a flat yes, no, true, false, or you need to have something in the middle that says, hey, this isn't quite a 1, you might need to process this with the human intervention. And you can look at that. One example would be self-driving cars. You don't want a car to be yes, no, I'm going to go through the light. You want it to be like, okay, if it's almost yes, maybe we stop and have human intervention so we don't get an accident. Cost function is something you can really see and measure and is very important. The cost value is the difference between the neural net's predicted output and the actual output from a set of labeled training data. So we have our group of data that's a square, circle, and since we're looking at geometrical shapes, we've had somebody already labeled that data. They've already said this is a triangle, this is a square. And so if this is coming up and it's giving us and it's saying a square is a triangle and it's saying a triangle is a circle, the output is wrong. And so that output can then be measured versus the actual output, and that's the cost. You might also hear this as error, because that's the error value being returned. How far off is it? And what we're looking for is the least cost, or the least error value. And it's obtained by making adjustments to the weights and biases iteratively throughout the training process. And this is called back propagation. And we're going to look in that a little deeper as we look into an example. It's really hard to see when you're just looking at arrows without actual numbers and where that flow is coming from. But you can look at this as here's our inputs. They put out a prediction. The prediction comes out and says, hey, we've already labeled this data because we're in training mode and the training data is off. This is the cost. Can we send that error or that cost back and adjust those weights? And we do it in very small increments across large amounts of data so that those weights minimize that cost or that error. But what happens within these neurons? So let's look at a little example of this. Kind of helps if you have some kind of visual. Let's build a neural network that predict bike prices based on a few of its features. And we'll see here we have our CC, our mileage, and our ABS, and these are our 3 input layers. And then we have the bike price and the output layer. Now, it doesn't do us very good to just pump it in from the beginning and pump it out. And to be honest, I would use a machine learning linear regression model on this, since these are just straight numbers. But because we want a simple example, we're going to put this through and show you as a neural network what that looks like. And we got to put a hidden layer in there. The hidden layer helps in improving the output accuracy. And you could look at this as a bunch of ORs. So it might say, hey, when we compare these three values on the first hidden layer neuron, we're looking at one set of features, and then we might weight them in the second one. So these are a bunch of different ORs, kind of how the math comes out and behind the scenes. And then they go out, of course, to the bytetrace or the output layer. And each of the connections have a weight assigned with it. And you'll see here we have mileage CC with the weight 1 and weight 2 going into our first neuron. And you'd also have your ABS going in there. And so x1 times weight 1 plus x2 times weight 2 plus the bias of 1. And step 2 is our activation, the activation function coming in there. When does this fire? And the neuron takes a subset of the inputs and processes it. And then we go through and we do that with the second hidden layer neuron and the third one and so on. So you process each layer in order going forward. Now, when I told you this is in its infant stage, they now have neurons that fire into the same layer or back a layer, so that you now have a time series, and there's all kinds of wild things that they're experimenting with on these layers. This basic setup has been around since the mid-90s. It's only now, because of our technology, that it's open to almost everybody to play with it, and that's why I say this is in an infant stage in development. Is this basic math is here, but what we can do with it is amazing, and what they're actually doing with all these different things is amazing. And so we're just at the beginning of how to use all these different tools in our deep learning and our neural networks. And so once we have our hidden layer computed, the information reaching the neurons in the hidden layer is subjected to the respective activation function. And so each one of these fires an activation output, and then those are each weighted to the final output layer. So the processed information is now sent to the output layer, once again, over weighted channels. And you could look at this as each one of these is, I always look at this as like a group of people. They're all looking at the bulletin board, and the first person says, this is what I project sells for the company, and the second person, and the third, and so on. And then their perspectives are weighted based on their expertise. So your accountant might have a very high weight, where the maybe your janitor has a very low weight, because their expertise is not in accounting. And then that goes into the output layer. And once in the output layer, it goes, the output, which is the predicted value, is compared against the original value. So now we have our output layer, and since we have like already a list of bikes with the different setups and what their value is, we can now generate an error from this. The cost function determines the error in prediction and reports it back to the neural network. So this is the cost. This is how far off it is. This is your error coming back. And as you can see, this is back propagation going on. So now our error is going in reverse because we know we're not completely correct on this particular channel. The weights are adjusted in order to reduce the error. So each time we go back, we are changing those weights to reduce that error, and we change them in small increments. You don't want to fit one input. Remember, you might have a data pool with a terabyte of data. You don't want to solve for the first set of data that comes in and that be the main solution, because everything else will be off. This is going to confuse you. That's also called a bias. So we have the bias in the cell where we're adding a value, the kind of like the y-intercept, and we have a bias of the whole neural network, which means it is weighted towards one set of answers. So we want to make small changes in these weights so we don't create a bias. And the weights are adjusted in order to reduce the error, or the cost. The network is now trained using the new weights. Once again, the cost is determined and backpropagation is continued until the cost cannot be reduced any further. So let's go ahead and plug in values and see how our neural network works. So here we come in here, and initially our channels are assigned with random weights. This is important because if you assign them all with the same weight, you might be able to reproduce it, but it turns out that if I put all my weights as 1 or all my weights as 0, it takes longer to train. Where if you have random weights, they already have like a little bit of adjustment and ORs built in, and that will give us a better answer and train faster. Our first neuron takes a value of mileage and CC as inputs. So here comes our computation, whatever those inputs are, and we do that again with the second neuron with those values coming in. You can see here we have weight 3 and so on, and then our third neuron coming down, and of course our fourth neuron. So we're adding all these different values coming in here in our hidden layer. The processed value from each neuron is sent to the output output layer over weighted channels. So again, here's our weights coming in, and we have N1, N2, N3, and N4. Once again, the values are subjected to the activation function, and a single value is emitted as the output. On comparing the predicted value to the actual value, we clearly see that our network requires training. So here we have it that our bike price we thought it was worth $2,000 on our random weights, and the bike actually was $4,000 on there. I'm guessing that's not US dollars, because that'd be a very expensive bike, but maybe it is. There's some $2,000, $4,000 bikes out there. The cost function is calculated and backpropagation takes place. And this is pretty simple. You can look at that as we're subtracting one value from the other. We square it, and then we take half of that. And that is propagated back up, and each layer generates its own errors. Let's go back one, because you have your predicted Y and your actual Y. That goes back to the first layer. And then based on the value of the cost function, certain weights are changed. So when we look at the next layer, that error is not the original 4,000 minus 2,000 squared divided by 2. This error is based on the error of each cell generated. How far off is that cell as far as its weights? We're not going to show you. It's actually a very complicated differential equation, and you can probably write it out if you wanted to. You just write out each formula. That goes into the next level, and you add them all together, and you can write it out all the way through. Computers make it so you don't have to. And our neural network is considered trained when the value for the cost function is minimum. So when we get our error way down as low as we can, that's when our neural network is trained. And just recently they've come up with all kinds of different means for measuring that particular value. A little bit beyond the scope of today's neural network, but you can actually see it. How far do you do this until the neural network doesn't need to be trained anymore, and you can overtrain a neural network. Now the tools that we're looking at automatically let you know when to stop, which is really nice. And that is just, like I said, we're at the beginning stages in neural networks, and it's just really cool what they can do now, and how much of it's automated, and how much of it is experimental right now. Let's take a look at gradient descent. But what approach do we take to minimize the cost function? So here we have a nice error thing coming in. This is our cost or our error. Let's start with plotting the cost function against the predicted value. And so you can see they fed in multiple y's, and these are the errors coming in and the cost of each of these inputs and changes going on. Note, we start at a random point on the curve. So usually you put in, you pick up your data and you randomly pick where to start in your data. A lot of times you just run it from the beginning because you're going through so much data, it's not that big of a deal, but you start with one point going in. So your forward propagation goes through, you're going to go ahead and find your cost or your error. It points that on the curve, and you can see how we're plotting it right here. Since the gradient at this point is positive, we may move right. So we're going to move a little bit to the right on here. And this time the gradient is negative, we move a little bit to the left. Eventually we try out the point where the gradient is 0. This is the least value of cost function. You have to be a little careful with this because this particular, they make it look nice and simple in this graph. Sometimes these curves look like stair steps, and so there is global minimums and then there is local. There might be a local point where the gradient is 0, but it's not the global one. So it might be way off to the left where it just happens to step down a little bit and you think you're in the right gradient. And with that we have all the right weights and we can say our network is trained. So here we have just some these are some of the big names out there right now in development for deep learning platforms. TensorFlow, which we'll actually do an example in a minute. Deep Learning for J, which is in the Java platform. So if you're a Java programmer. By the way, as TensorFlow is accessed, most people are using Python to access it, but it is a system that's kind of separate from a lot of the programming languages, which makes it a lot more flexible as far as use. Deep Learning for J is Java based. And then Keras is just exploding right now. And this is interesting. Keras is working with TensorFlow. It actually can sit on top of TensorFlow and it can also do its own thing. So if you're studying deep learning, you're getting into it, you'll want to know the basics of TensorFlow, but you also are going to want to know the upper level of Keras sitting on top of TensorFlow. We're just looking at TensorFlow today though in our example. And there's also Torch on there. There's a bunch more that we didn't list on here. Even sklearn or the side package in Python has a neural network you can program, a very basic one. And it is the same basic one that you could do in TensorFlow if you stripped everything out of it, and then TensorFlow has a lot of tools they've added in, and so has Keras. But we're going to be looking specifically at TensorFlow in our example. And TensorFlow is an open source tool used to define and run computations on what they call tensors. Very common language now. So more and more we see the term tensor as being a standard in the deep learning language. And this was originally developed by Google. So let's take a little bit big in there. What are tensors? Tensors are just another name for arrays. So a tensor of dimension 5. You can see here we have A, B, K, M, Q, whatever. So it's an array coming in. And the tensor of dimension 5, 4, more like a picture. Very common to see that in a picture. You can also see a tensor even more detailed in a picture as we go to the next one, tensor of dimension 3, 3, 3. This is 3D space. You might have a picture that also has colors. That might be the third dimension. You might have 4 dimensions because you have both your grid and your different color channels and your z-plot. You can see where you can now process a very high level set of data coming in, whether as an image or features. They could be features that have nothing to do with images. So there's a lot of stuff you can do now with the tensors coming in. Thus, this is where the term TensorFlow comes from. So we have right now that TensorFlow is the most popular library in deep learning. And I did mention Keras now works with TensorFlow. So there's a lot of stuff you can do between the two. It's an open source software library developed by Google. So they hit a roadblock and they realized, hey, this is an infant stage technology. You know, we thought it was going to be the next greatest thing and we were going to have a hold on it, but it's really infant as far as how it's applied and what we can do with it. Let's open source it so everybody can work on it. Let's take it to the next level. And that's really what open source does to a lot of these packages when they release them. And you can run on either a CPU or a GPU. So when we look at the details, if you have your graphic processing units, what's nice about those is they run a lot faster. The downside is you have to play with them a little bit to get them up and running, and it's a hardware upgrade. When we run it, I'll be running it in the CPU mode. I have played with it in my GPU on my personal computer. You know, it does increase the processing, but I did run into some version problems with my Python and stuff like that, and when I did finally work it out, I went back to the CPU because it didn't increase my speed enough for what I was working on. But in a larger group, you might be able to put that on. If you're working with a larger stack of computers, you might want to run it in the GPU. You can create a data flow graphs that have nodes and edges. So there's our edges coming in. We didn't talk about edges, but that's a very up and coming way of looking at your analytical data is how do different nodes connect? What do those edges look like in between them? And it's used for machine learning applications such as neural networks. It is mostly a neural network, but they have all kinds of tools which sit on top of our basic neural network. They have new stuff evolving into the TensorFlow library. So it's very much just exploding. Great time to jump into TensorFlow because there's all kinds of cool things they're doing with it and all kinds of cool applications you can now use TensorFlow for. So let's take a look at implementation in TensorFlow. And we're going to build a neural network to identify handwritten digits using the MNIST database, or the MNIST database. And that stands for Modified National Institute of Standards and Technology Database. It is a collection of 70,000 handwritten digits, and the digit labels identify each of the digits from 0 to 9. This is a cool example because it's simple enough that you could actually run this through some basic machine learning categorizing algorithms and train them. And you'll get about the same answer because, again, it's simple grid. The digits on the grid don't have a huge amount of variation like you would, say, an automated driving car looking at the environment. So you could still do this with a lot of your different linear models and stuff like that. You can solve this and you'll get about the same answer. When I ran a comparison between TensorFlow and between some basic regression models or category models in machine learning, they came up pretty even as far as their output. So this is kind of where we start to see the complexity of something coming in this case a tensor, or a grid of information, where the deep learning model does as good as the regular models. And when you get past this kind of complexity and features, suddenly the neural networks come up with better answers, better solutions, and a better build. And that's why there's such a move into neural networks, is we live in a complicated world, and it's just really cool what we can do with this. So the handwritten digits from the NIST database, they come in, the data set is used to train the machine, a new image of a digit is fed, and the digit is identified. And if you've looked at any of our other machine learning tools where we're doing training, where we train our model to fit and then you test it out, this will look pretty familiar. And there is some tools out there for, say, untrained categorizing, where it's just looking for features that fit together. So there are tools that don't need that training. But this is where, when we talk about neural networks, we do need to train them, and this is what we're looking at. So for this, I'm going to use the Anaconda Navigator just because it's a very nice visual tool. You might be in PyCharm or one of your other IDEs for editing Python, because we are looking at Python TensorFlow. And under Anaconda, we have the notebook, which is something we use pretty regularly, and they have the Jupyter Lab. The Jupyter Lab is the Jupyter Notebook, but with tabs and a few new features. So we'll be using the Jupyter Lab today. And under the environment, you'll want to go ahead and if you haven't yet, you'll see that I have a number of different setups in here. Right now I have the Python version 3.6 and the TensorFlow. In this case I have TensorFlow 1.12. If we scroll down you can see that. Here we go, TensorFlow, and it's version 1.12. And in here, if you haven't yet, you'll need to install those and go in and just open our terminal. And if you've never used the Anaconda, or if you're in your other thing, you might have something simple like pip. Conda is what I use for my install, and you can simply do conda install TensorFlow. And that should bring in the most current version. Now, when I installed this a few months ago, Python version, I'm not going to run this because I already have it installed on here, Python version 3.7, the newest one out, still had a couple glitches with the TensorFlow. I believe they've fixed it as of writing of this, but I'm going to stick with 3.6 just so I don't get any surprises on there. So this is Python version 3.6 with TensorFlow 1.12 on here. And if you haven't installed it yet, you also want to install NumPy for this example. That's numbers Python, or NUMPY. You can just simply run an install on there. Keep in mind, if you're in Anaconda and you've created one of these environments specific to this, keep with Conda. If you're going to use Conda. If you're going to use pip, keep with pip. Don't install one package with pip and one under Conda, because that's how they track those version numbers and how they fit together, and you can end up with a problem. Pip doesn't see Conda and vice versa. So just keep that in mind when you're running your installs. We'll go ahead and open up Jupyter Lab, and we're going to launch that. So here's my Jupyter Lab. One of the really cool features of Jupyter Lab is you have tabs now, so you can open up multiple notebooks. And this is nice because I have my notes I'm working on and then our actual window we're looking in. And we'll go ahead and zoom in a little bit here. There we go. So you have a nice, hopefully easy to see fonts. And then we'll go ahead and do a simple, or get our imports out of the way. And so we're going to import our TensorFlow as TF. That's pretty much a standard for TensorFlow. NumPy, our numbers Python, as PY. And we'll import our matplot library as PLT. Again, these are very common. So if you see TF or PY or PLT, this is a standard that most people use. Do you have to? No. You could just do import NumPy instead of doing as PY. And then from TensorFlow.examples.tutorials, this is always nice because they actually include data set we're going to play with. So we're going to import input data. So those are data coming in. That's all we're doing is telling it this is where it's coming from. And if we're going to tell where it's coming from, we need to go ahead and create a variable with that information in it. And we'll just call this MNIST or minced. You know, I don't really know how they pronounce that. I should probably look that up. It's a very common data set to use. And there's our input data, and we're going to read data sets. And this is, if you look at this, we imported input data from our TensorFlow. And so this is a TensorFlow read statement for their tutorials. So this isn't like some special Python setup. This is just their setup. It makes it easy to pull it in. So once we get into their data sets, we need to go ahead and tell it what kind of data set. And again, this is what we brought in, but it's going to be the NINST data. And this part is very important. One hot equals true. This means that instead of importing a value from 0 to 9, we evaluate the data set, it's going to bring it in as one hot. Whenever you see one hot encoder, we're flattening that out, and we have true false for 0, true false for 1, true false for 2. So our output, if you remember from our output from the slide we did earlier, in this case I grabbed the one for bike price, doesn't really matter which one we use. This has one output, so we have our bike price. On this, we're going to have, instead of one output, we're going to have 10 outputs representing each of the digits in there. And this code really isn't going to show us anything. It's good to see what we're actually looking at. So let's go ahead and do a figure. AX equals, go into our plot library, subplots, 10, 10. And that is, if you remember, we talked about tensor being data coming in. This is a 10 by 10 grid, or 100 pixels on there. And if we're going to display it, let's go do K0 for I in range 10. Just a simple loop through on the data. Let's do, what is it, for J in range 10. So I actually misquoted that. 10 by 10 is not the actual size of the pixels. The actual pixels are going to be, when we look at the shapes, and we'll get into that in just a second here. We'll take a quick look at shape on there. Turns out they're, they are, I believe, 28 by 28. So let's take a look at that. And we're just going to plot these. What are we looking at? What are we working with? As a data scientist, you should always be looking back at your data and seeing what it looks like and get that human perspective, because you just never know. You know, the computer might put something out that makes no sense, and at that point you want to go back and reevaluate what you did. So we're going to go ahead and plot. We're going to plot 10 of the digits by 10 of the digits, and here's our AX. We'll create the IJ on our subplots, and we're going to do an image show. We're going to look at the training image for images of K. And then we want to reshape this. We're going to reshape this, and we're going to reshape this 28 by 28. That's how I knew I had it wrong, is because I looked down my notes and I was like, oh no, that says 28, it's not 10 by 10. And I should know that already because I've done enough messing with this data set that I should have remembered. But it's 28 by 28, and the aspect we're going to do is auto. And this is all, if you look at this, here's our variable NIST. The NIST is coming from data set. So this is all part of the TF TensorFlow learning or examples tutorial in there. And then we'll go ahead and do K plus equals 1, so we just keep paging through our different images, and let's see what that looks like. Let's go ahead and do a plot show, and we'll go ahead and run this so we can take a look and see what we have here. And so we have a nice plot here, and you can just see that we have some random numbers showing up in each one of these little subplots. If you're wanting a copy of this code, put a note down in the YouTube video and let us know, or come visit us at www.simplilearn.com, and we'll send you out a copy of what we're working on. You can get a copy of that for your own setup. So now we've taken a look, and we can just see we have, here's our pictures that are coming on. We plotted them so we have an idea of what we're looking at. Let's go ahead and let's look at the shape of the features. So when we have this, we have our NIST train images, and we'll do the shape on there. Let's take a look and just see what we're looking at. As far as our count and everything. And so you can see here we have 55,000. That's basically how many images we have, and this by 784. And in this data set, there's also our labels. So let's take a look at that. We have our NIST train labels shape. Let's take a look and see what that looks like. And there we have 10, because there's 10 digits. So we brought in, that's our output we're looking at. And so we have, there we go, 55,000. They match. They should match, because you should have equal numbers in both of those. You know, here's our data in, and here's our answer. If you remember, this is a bunch of zeros, and with one, each one will be 0001, would be what, letter 4 or something like that. So let's take a look at what our one hot encoding did for the first observation. And this is, when we're exploring data, you really want to dig in there and just see what the heck am I looking at. So we're going to look at the labels, and this would be the first label that comes up, and we'll go ahead and run this. And when we look at that, you can see this is what I'm talking about. 0, 0, or 1 is 0, 2 is 0, 3 is 0, 4 is 0, 5 is 0, 6 is 0, 7 equals 1. So our very first label is a 7, but our very first label comes up that it's a 7. And so we don't have like 0 through 9. We have a bunch of zeros and just the 1 to mark it as a 7 on here. So now we've kind of looked a quick look at the data. And in here you might ask some questions like, what is 784? 24 times 24. Remember, that's the size of our grid on there. or our tensor coming in. So 784 is the setup on there. And we've gone through all this viewing the data. We'll go ahead and start looking at our TensorFlow. So let's take our X variable. This is going to be our training set. We'll do a placeholder, and then we're going to have these come in as float. Now, if I remember correctly, they're actually, 0 or 1 for the values, because they're either, but we have them coming in as a float value, and we have a little bit of a shape coming in here, and there's our 784. So we let it know that this is what our input is for our TensorFlow, and this is our training set. So we'll just put a label on there to help us track that, train set, and then W, and with W we'll go ahead and do TF variables, and we'll do this as zeros. Variables, TF zeros, and we'll set this as 784 by 10, 10 being the output, 784 being our number of variables in, and this is our weights. Remember, we have a bias in there too. And I'll go back over this in just a second as we see how that fits together in our TensorFlow. And we'll do this one with our variables. Again, we have 10, so we're going to do the bias. We're going to do it the same kind of format and setup on here. And so we'll do that as TF zeros of 10. So we'll just create an array of 10 there, and this is our bias. So with these 3 lines, and they're coming out with the eager execution, which would bypass some of what we're doing. But this is important to understand, is the first thing you have to do with TensorFlow is we have to allocate a space for the variables. In our TF placeholder and our TF variable with our weights and our biases, this actually hasn't done anything yet. So all it is placeholders. That's why it's okay to use zeros. You could have just as easily used ones or anything else, and it wouldn't matter. The next stage is to go ahead and set up some of the functions going on. But before we do that, just note that this hasn't done anything. Even if I execute it, all it's done is created placeholders until we do the final initialization. And so we need to go ahead and set up, we'll do y equals tf.nn.softmax. And the code for this is tf.matmul xw plus b. And this is our sum. Let's just put a note here so we can keep track of what's going on. We're finding weighted sum of inputs plus the bias. So there's our plus b, the bias. And then we need to go ahead, let's do y underscore, and again another placeholder. And this one will set, we'll put in as TF placeholder on here. TF placeholder float none 10. There's our one hot encoder going on there. So our 10 values coming out. And we'll do a cross entropy on here. And this is going to be minus TF reduce sum, and we'll do y. Here's our y underscore, which is, remember, we have your y output and your actual output. So this will be our y underscore times the TF log of y. And then finally, before we do the actual initialization of all our variables, we'll set up our train step. This equals our gradient descent optimizer. Very important. Remember, we looked at that chart on our slides, and so we've set up all these formulas, and here's our gradient descent optimizer, and as it keeps looking for that 0 value. That's what we're doing with that particular formula. So let's take a look and see what we're doing here. We just put together all of our pieces for TensorFlow. And, the devil's in the details. We have here our training set coming in. We have to put a placeholder on there. We have our variables with their weights. We have our biases coming out. And then we put in our the weighted sum. So here's summizing our summation here. Then we have our y variable output. So there's our y, how it works, and then of course the actual output on there. And then we have our cross entropy coming in, and that's our minus TF dot reduce sum, the y times the TF log of y. And then the training step, gradient descent optimizer. We're using a 0.01 in this, and we're going to minimize cross entropy. So we're going to let it do all the work. So once we've set up all of these different layers, we've allocated for them, we need to go ahead and initialize them. So we're going to do an init TF initialize, and it's going to be all variables. One of the cool things is they're in the process of doing away with this. So all these steps would be bundled into one instead of having to have placeholders. You initialize them in the same process going on. And then finally, everything in TensorFlow is based on your session. Now this is changing, that there's other options to be able to run this. But we want to go ahead and do session. There's our TF, which is a TF session. And then we want to go ahead and do session run. And what are we going to run? Well, we did initialization of all our variables. So this is what we're running. And this is where actually, once we do this, we actually create our TensorFlow object. So this whole piece of code right here is our TensorFlow object. We have our input coming in with our weighted variables coming in, our softmax for our metmul going out. How does it add it together for our y value? And then we have the actual float value coming out, checking on our all the way down. So you can see all the different stages going through that we're setting up. And this is one of the reasons that a lot of people like TensorFlow, is because you can designate all these different pieces one step at a time. This is also one of the reasons people don't like TensorFlow, is because you have to designate all the different layers coming down. And there's a lot of steps being made right now to minimize this, to make it either easier to automate it or to allow you to do more complicated things. And all those steps are still at play, so it's worth looking into the more advanced version of what's going on with Keras on top of TensorFlow. It's also important to understand what's going on these individual levels if you're going to play with them. It's important to understand, hey, what's going on with the finding the weighted sum of the inputs plus the bias, because there's other ways to do that. There's all kinds of other tools in there now. But this is the basic setup that you want to do on a TensorFlow coming in. And we want to go ahead and just run and init our TensorFlow. So let's go ahead and do that. Let's run this. We do get a warning here because there's a move to use global variables. This is one of the changes they're making. But as far as this example, it's not going to make a difference because we're doing, once we initialize it, this is initializing our variables. And again, these are only placeholders up here until we initialize them. And I would highly suggest put a note down there or go over to Simplilearn.com and let them know and have them email you a copy of the code so you can actually play with this code right here. Because this is the body of what's going on in TensorFlow. This is the build in neural networks. And then once we've done that, now comes kind of the fun part, is we need to go ahead and train it. So we've created our TensorFlow. We've created our network. And now we need to go ahead and train it. So let's put together that training code. And let's just do for I in range 1000, 0 to 1000. So we're just going to look at the first 1000 in our training. And the way we pull that data from our mince train next batch of 100. So you look at this, we're going to be doing groups of 100, and then there's going to go through 1,000 of them. This is very important that TensorFlow builds this in. This is one of the downsides of doing sklearn or one of the older packages, is they don't let you batch groups in. They wanted to have it all up front, and then you have to build your own batch programs right now. This lets us go ahead and do that. And you can see here we have batch x of s, batch y of s. So there's our x and our y. You can look at this as our training of x and our train of y, or the data in and the answer in. And then we simply do our session run. So here's our session that we've created. We're going to run it, and we want to do the train step. Remember, we initialized our train step up here in our TF, and so there's our train step. Feed is a dictionary coming in, which we're going to create right here. Is x is our batch, x of our sample, comma, and our y underscore is going to be our batch of our y sample. And so this goes through, and we've now hit the run button, and we've trained our session. We've trained this setup on here. And once we've trained it, then we need to go ahead and find out how good our accuracy was and actually start running some predictions through there. So we'll go ahead and create a correct prediction, and this is where our tf.equal, we'll use our argmax y of 1 and tf argmax of y of underscore of 1 to help us get the correct predictions on there. And then we want to use that to feed into an accuracy. And so our accuracy is going to be tf reduce mean, and we'll take that and we'll do a cast, and this is the correct prediction that we're sending in there, and it is a float value. Keep it simple, and let's go ahead and print this out so we can see what we're looking at. So what are we printing out? We need to do a session run. This session run is going to be on the accuracy. Where did accuracy comes from? This is we're casting our TF on there with the correct predictions on that. So here's our accuracy. Feed in, so it needs a dictionary for the data coming in. We're going to create our dictionary, and x is going to be our NIST test images, and y underscore there is going to be our NIST.test labels. Let me just double check and make sure I have that typed in there correctly. There we go, and let's go ahead and run that and see what comes up, and we end up with a 0.9165 for our accuracy, which means our trained neural network does a pretty good job letting us know what these different symbols are. In guessing that a 7 and a 3 and a 4, something that as humans we kind of take for granted, I even have trouble reading this. So I don't know if I would be able, like that first one, I would sit there for a long time figuring out that's a 7 versus a 2. That could have easily been a 2 to me. So you can see we do a pretty good job analyzing this data, and this is used to analyze something very complicated on these images. Very different than just a straight value of cost of sales, and here's our return and our marketing. We can now create this nice neural network that does all kinds of cool things.
Learning objectives. Welcome to Math Refresher, Probability and Statistics. In this lesson, we are going to explain the concepts of statistics and probability. Describe conditional probability, define the chain rule of probability, discuss the measure of variance, identify the types of Gaussian distribution. Basic of statistics and probability. Probability and statistics. Data science relies heavily on estimates and predictions. A significant portion of data science is made up of evaluations and forecast. Statistical methods are used to make estimates for further analysis. Probability theory is helpful for making predictions. Statistical methods are highly dependent on probability theory, and all probability and statistics are dependent on data. Data is information acquired for reference or research via observations, facts, and measurements. Data is a set of facts structured in the form that computers can interpret, such as numbers, words, estimations, and views. Importance of data. Data aids in seeing more about the information by identifying possible connections between two features. Data assists in the detection of distortion by uncovering hidden patterns. Based on prior information patterns, data may be utilized to anticipate the future or predict the current state of affairs. Also, data aids in determining whether two pieces of information have any instance in common or not. Types of data. Data might be quantitative. That is data that can be measured or counted in numbers. Or it may be qualitative, which is data which is generally divided into groups, or in simpler words, which cannot be counted or measured in numbers. Let's consider an example. A customer information data of a bank may contain quantitative and qualitative data. Consider this snapshot where we have customer ID, surname, geography, gender, age, balance, has C or card, is active member. Amongst these variables, we can see surname is mostly qualitative as it cannot be counted and measured in numbers. Geography and gender are also qualitative as they cannot be counted in numbers and are mostly groups. Has C or card, that is, has credit card, and is active member, although are containing numerical in form. But these are categorical. That means these have been divided into groups of 1 and 0 that represent yes and no as an answer. Hence, these two variables are also qualitative. Customer ID is again, although a numerical data. However, the significance or intuition behind customer ID is categorical. Hence, it may be kept in the qualitative data also. However, age and balance. These are numerical information which have been measured or counted, and numerical operations can be performed on them. Hence, these are under quantitative data categories. Introduction to descriptive statistics. Descriptive statistics. A descriptive measurement is a summary measure that quantitatively portrays the most important features of a set of data, allowing for a better comprehension of the information. Data can be measured as different levels. The levels of measurement describe the nature of information stored in the data assigned to the variables. Qualitative data can be measured as nominal or ordinal. Quantitative data can be measured in terms of interval and ratio type. Nominal data. The data is categorized using names, labels, or qualities. For example, brand name, zip code, and gender. Ordinal data can be arranged in order or ranked, and can be compared. Examples include grades, star reviews, position in race, and date. Interval data is the data that is ordered and has meaningful differences between the data points, example, temperature in Celsius and year of birth. Ratio data is similar to the interval level with the added property of inherent zero. Mathematical calculations can be performed on both interval as well as ratio data. For example, height, age, and weight. Population versus sample. Before analyzing the data, it's important to figure out if it's from a population or a sample. Population is a collection of all available items as well as each unit in our study. Sample is a subset of the population that contains only a few units of the population. Population data is used for study when the data pool is very small and can give all the required information. Samples are collected randomly and represent the entire population in the best possible way. Measures of central tendency. The central tendency is a single value that aids in the description of the data by determining its center position. Measures of central tendency are sometimes known as summary statistics or measures of central location. The most popular measurements of central tendency are mean, median, and mode. The normal distribution is a bell-shaped, symmetrical distribution in which mean, median, and mode all are equal. The curve over here shows the bell-shaped curve or the normal distribution of variable x. The point over here that is x1 is the point which represents the mean, median, and mode of this distribution. Mean. Mean is calculated by dividing the sum of all data values by the total number of data values. It gets affected when there are unusual or extreme values. It is sensitive to the outliers. Mean can be calculated as summation over all the values of x in a collection divided by the size of the collection. For example, we have a collection where we have values as 7, 3, 4, 1, 6, and 7. We find out the sum of these values, which is 28, and there are a total of 6 values. So 28 divided by 6 gives us a mean value of 4.66. Median. It is the middle value in the set of the data that has been sorted in ascending order. It is a better alternative to mean, since it is less impacted by outliers and skewness. It is closer to the actual central value. Median is calculated differently for different sizes of data. Differentiated as if the total number of values is odd, or if the total number of values is even, if the size of the data is odd. For example, in this case, we have 5 elements. After sorting, whatever middle value we get. That means n plus 1 by 2th term in this case. 5 plus 1 divided by 2. That is the 3rd term, which is 4 is the median value. In case when the total number of values is even like here, there are 6 values. The average or the mean of the 2 central values is considered as the median. In this case, the median is the mean of 6 and 4, which is 5. Mode. Mode represents the most common value in the dataset. It is not at all affected by extreme observations. It is the best measure of central tendency for highly skewed or non-normal distribution. Mode for categorical data is determined by estimating the frequencies for each categories, and then the category with the highest frequency is considered to be mode. Like in this case, 7 has the highest frequency, hence 7 becomes the mode value. However, in case of continuous data or quantitative data, the calculation of mode is slightly different. The first step in calculation of mode is dividing the data into classes which are equal with, then getting the frequency of data points lying within that range of classes, and finally selecting the class with the highest frequency. Using the range of that class and the frequencies, we can get the final mode value. Using the formula L plus Fm minus F1 multiplied to H divided by Fm minus F1 plus Fm minus F2. Here L is the lower limit, or the lower observation of the mode class. H is the size of the mode class. Fm is the frequency of the mode class. F1 is the frequency of the class proceeding to mode. And F2 is the frequency of the class succeeding to mode. This gives us the final mode value. Mean versus expectation. Now let's talk about mean versus expectation. So in general, we use the expected value or expectation when we want to calculate the mean of a probability distribution that represents the average value we expect to occur before collecting any data. And mean, on the other hand, mean is basically used when we want to calculate the average value of a given sample. This represents the average value of raw data that we may have already collected. We can understand this by using a simple example. Now, to calculate the expected value of this probability distribution, we can use a specific formula from the previous discussion. This is going to be the expected value, where x is going to be the data value, and this px is the probability of value. For example, we could calculate the expected value for this probability distribution to be as shown. So here, it will be 1.45 goals. So this represents the expected number of goals that the team will score in any given game. And then if you talk about calculating mean, so we typically calculate the mean after we have actually collected raw data. For example, suppose we record the number of goals that a soccer team will score in 15 different games. Now to calculate the mean number of goals scored per game, we can use the following formula, where sum of x is basically the sum of all the goals divided by n and the number of records, or we can say the sample size. It is as shown on the screen. So this represents the mean number of goals scored per game by the team. Measures of asymmetry. The difference between the three distinct curves can be studied in this image. The central curve is the normal or no skewness curve. Here mean, median, and mode all lie on the same point. This normal curve is symmetrical about its mean, median, and mode. That means the left-hand side of the curve is a mirror image of the right-hand side of the curve. However, in case of negatively skewed data, the tail is elongated on the left-hand side, and the mean is smaller than the mode and the median values, or is on the left-hand side of the mode, hence indicating that the outliers are in the negative direction. On the other hand, in case of positively skewed, the data is concentrated on the left-hand side of the curve, while the tail is elongated or longer on the right-hand side of the curve. The mean is greater than the mode and median, or is on the right-hand side of the mode and median, indicating that the outliers are in the positive direction. Let's consider an example. The graph here shows the global income distribution for the year 2013, and a projection for 2035. If we see the global income distribution statistics for 2003, it is highly right-skewed. We can observe in the previous graph that in 2003, the mean of $3,451 was higher than the median of $1,090. The global income is definitely not evenly distributed. The majority of people make less than $2,000 each year, while only a small percentage of the population earns more than $14,000. Measures of variability. Measures of variability. Dispersion. The measure of central tendencies provide a single value that addresses the full worth. However, the central tendency cannot depict the viewpoint entirely. The metric of dispersion helps us focus on the inconsistency in the data spread. Measures of dispersion describe the spread of the data. The range, interquartile range, standard deviation, and variance are examples of dispersion measures. Range. The range of distribution is the difference between the largest and the smallest amount of data. The range, for example, does not include all of a series' positive aspects. It concentrates on the most shocking aspects and ignores that aren't considered critical. For example, for a set 13, 33, 45, 67, 70, the range is 57. That is, the maximum of this, which is 70 minus the minimum over here, which is 13. Variance. Variance is the average of all squared deviations. It is defined as the sum of squared distance between each point and the mean or the dispersion around the mean. The standard deviation is used as variance suffers from a unit difference. Variance can be computed as sigma square summation over x minus mu square divided by n, where mu is the mean of the data, x is the individual data point, and n is the size of the data. This representation is for a population data. For a sample data, variance can be computed as x minus x bar whole square summation over it divided by n minus 1. Here x bar is the mean of these sample data, and n is the sample size. The units of values and variance are not equal, so another variability measure is used. Standard deviation. Standard deviation is a statistical term used to measure the amount of variability or dispersion around a mean. The standard deviation is calculated as the square root of variance. It depicts the concentration of the data around the mean of the dataset. Standard deviation, as indicated previously, can be computed as square root of variance. For a population data, standard deviation sigma can be computed as square root of summation over xi minus mu whole square divided by n, where mu is the mean of the data, xi are the data points, and n is the size. Let's consider an example. Let's find out the mean, variance, and standard deviation for this data. The data values are 3, 5, 6, 9, and 10. To find out the mean, we first find the sum of all these data values. That is 33, and divide it by the count, which is 5. We get the mean of 6.6. To compute the variance, we start by computing the deviation. That is x minus the mean of x. Here 3 is one of the values of the data, and 6.6 is the mean. So 3 minus 6.6 square, and we do that to find out sum of all the deviations divided by the count, which is 5. We end up getting an overall variance of 6.64. Standard deviation, as we know, is measured at square root of variance. That is square root of 6.64, which amounts to 2.576. Measures of relationship. Measures of relationship, covariance. Covariance is the measure of joint variability of two variables. It measures the direction of the relationship between the variables. It determines if one variable will cause the other to alter in the same way. Covariance between variable x and y can be computed as summation over the product of xi minus x bar and yi minus y bar the whole divided by n minus 1. Here x bar and y bar are the mean of x and y respectively. The value of covariance can range from -infinity to a +infinity. Correlation. Correlation is normalized covariance. It measures the strength of association between two variables. The most common measure for correlation is the Pearson correlation coefficient. Correlation between two variables, x and y, can be measured with respect to covariance as covariance between x and y divided by the standard deviation of x and standard deviation of y. The value of correlation ranges from a -1 to +1. Types of correlation. Correlation can be either a positive correlation, zero correlation, or a negative correlation. The first picture over here represents a perfect positive correlation, wherein a straight line with a positive slope is representing the relationship between the two variables. Zero correlation means that the line representing the relationship between the two variables is horizontal to the x-axis. Perfect negative correlation can be represented by a straight line with a negative slope. Correlation equals to 1 implies a positive relationship. That is when one variable increases, the other variable also increases. A correlation value of -1 implies a negative relationship. That is when one variable increases, the other decreases. The correlation coefficient of 0 shows that the variables are completely independent of each other. Let's consider an example. Here, we have two variables, height and weight. To compute the correlation between height and weight, we use the correlation formula as covariance of x and y divided by standard deviation of x and standard deviation of y. Here height is the x variable and weight is the y variable. First, to compute covariance, we compute the x minus x bar and y minus y bar values, and then the product of them. We then compute x minus x bar square and y minus y bar square values to compute the standard deviations of height and weight respectively. Correlation, as we know, has been defined as covariance of x and I and y divided by standard deviations of x and y. This can also be represented as summation over x minus x bar multiplied to y minus y bar divided by square root of summation over sum of squared deviations. That is x minus x bar square multiplied to square root of summation over y minus y bar whole square. That is sum of square deviations for y. Now, let's find out values to put into this formula. First, we find out the overall sum of height to get the mean of height, which is 5.14. Similarly, we get the sum of weight to get the mean of weight as 50. We now get the summation over x minus x bar multiplied to y minus y bar to get the numerator for the formula. Then we compute x minus x bar square summation and y minus y bar square. That is sum of squared deviation of x and y respectively. Now we put in the values in this final correlation formula to get a correlation value of 0.889. This indicates that height and weight have a positive relationship. It is evident that as height grows, weight also increases. In this module, we will be talking about expectation and variance. So the expected value, or we can say mean of a given variable, that we can denote by x is a discrete random variable where it is a weighted average of the possible values that x can take, and each value is going to be according to the probability of that specific event occurring. So usually the expected value of x is denoted by a simple formula where we can define the expectation based on the x parameter, which is going to be the sum of each possible outcome multiplied by the probability of the outcome occurring. So in more concrete terms, the expectation is what we would expect the outcome of an experiment to be on average. We can take an example for the coin. If a coin is being tossed 10 times, then one is most likely to get 5 heads and 5 tails. Same logic can be discussed if we talk about another example of rolling a die. So there are 6 possible outcomes when you roll a die. 1, 2, 3, 4, 5, 6. And each of these has a probability of 1 by 6 of occurring. So we can say that the expectation is going to be 1 multiplied by the probability of that happening, which is going to be 1 by 6, plus 2 by 6, plus 3 by 6, plus 4 by 6, plus 5 by 6, plus 6 by 6, and that is going to give us 3.5 as an output. The expected value is 3.5. So if you think about it, 3.5 is halfway between the possible values that I can take. And this is what we should have expected. Next, we talk about the concept of variance. So variance of a random variable allows us to know something about the spread of the possible values of the variable. So for a discrete random variable x, the variances of x is going to be denoted by using a simple formula that is going to be var x equals ex minus m, the whole square where m is basically the expected value of the expectation of x. So this is more like a standard deviation of x, which can also be represented by using this formula. So the variance does not behave in the same way as expectation when we multiply and add constants to random variables. So now there are 2 different types of variance that we can have a fair understanding on. First of all, we have low variance, and then we have high variance. So low variance simply means that there is a small variation in the production of the target function, with changes in the training data set, and at the same time, high variance, as we can see here. High variance shows a large variation in prediction of the target function, with changes in the training data set. So a model that shows high variance learns a lot and perform well with the training data set. And it does not generalize well with the unseen data set. And that's why, as a result, such a model gives good results with training data set, but shows high error rates on the test data set. And since the high variance a model learns too much from the data set, it leads to an overfitting of the model. So model with high variance will be having a couple of issues, like it may lead to overfitting, or it may also lead to increase in model complexities. Next, we have skewness. So skewness in simple terms is basically a measure of asymmetry of a distribution. So distribution is asymmetrical when its left and right sides are not the mirror images. Right now, this is a mirrored image, and a distribution can have right positive, or we can say negative, or it can have 0 skewness. So right skewed in this scenario is basically the distribution is longer on the right side of its peak. And a left skew distribution is going to be, we can say, where it is longer on the left side. So we can see we have this one as a part of right side. it is more elongated towards the right side, and this one is more elongated towards the left side. So we can think of skewness in terms of tails. A tail is long tampering and the end of a distribution. So it simply indicates that they are observations at one end of the distribution, but that they are relatively infrequent. So a right skew distribution has a long tail on the right side, as you can see here, so the number supports observed. Let's say we have a data on a per year basis. So again, we can have a more skewness towards the right side, where data is being dropping as we continue to increase the number of years. For example, we may have a high sales towards the beginning of year, suppose in 2022. But again, as we proceed to 2023, second half we are seeing the dip in performance. So that is rightly skewed. And same way, let's suppose if we started with the sales figure, it was really less in suppose 2002. But again, as we proceeded to 2023 now, our sales have been gradually increasing. So it's more like skew towards the left section as a part of negative skew. Next we have kurtosis. So kurtosis is basically a measure of the tailedness of a distribution. So tailedness is how often the outliers occur, and acts as kurtosis is the tailedness of the distribution related to a normal distribution. So a distribution with medium kurtosis is called as mesokurtic. A distribution with low kurtosis like this one. This is called as the platykurtic, and then distribution with high kurtosis like this one. This is called as the leptokurtic. So tails here, they are tapering ends on either side of a distribution like this. So they represent the probability or the frequency of values that are extremely high or extremely low to the mean. In other words, tails here represents how often the outliers occur. So there are three types of kurtosis. We have platykurtic, which is negative, leptokurtic, which is a positive towards the upper end, and then we have mesokurtic, which is a normal distribution. So mesokurtic is the medium tail. So normal distributions, they have a kurtosis of 3. So any distribution with a kurtosis of a prox value of 3 is going to be mesokurtic, and kurtosis is described in terms of excess kurtosis, which is kurtosis minus 3. And since normal distribution, they have a kurtosis of 3-axis kurtosis, makes comparing a distribution kurtosis to a normal distribution even easier. Introduction to probability. Probability theory. Probability is a measure of the likelihood that an event will occur. Let's consider an example of coin toss, where the chances of getting heads on a coin are 1 by 2 or 50%. The probability of each given event is between 0 and 1, both inclusive. Sum of an event's cumulative probability cannot be greater than 1. Hence, the probability of an event x lies between 0 and 1. This means that the integral of probability of distribution over x equals to 1. Conditional probability. Conditional probability of any event A is defined as the probability of occurrence of A, given that event B has previously occurred. Condition probability of event A given B can be estimated as probability of A intersection B, that is, probability of both A and B happening together, divided by the probability of B. It is also written as that probability of A intersection B equals to probability of A given B multiplied to probability of B. Let's consider an example. In a coin, we are doing a 2-coin flip. Coin 1 gets heads, and tails in subsequent flips, while coin 2 gets tails, heads, and tails in the subsequent flips. Now the probability that coin 1 will get a head is 2 out of 4, while the probability that coin 2 will get heads is again 2 out of 4. The probability that both coin 1 and coin 2 will have a heads is just 1 out of the 4 flips. Hence, the probability that coin 1 will get heads given that coin 2 is already heads can be computed as probability of coin 1 edge intersection coin 2 edge. That is 1 by 4 divided by probability of coin 2 edge. That's a given that is 2 by 4, which is going to be 0.5 or 50% based. Bayes theorem. Bayes' theorem calculates the conditional probability of an event based on its prior probabilities. Basically, Bayes' theorem incorporates the prior probability distribution to predict the posterior probabilities. Bayes' theorem for conditional probability can be expressed as probability of A given B equals probability of B given A divided by probability of B multiplied to probability of A. Bayes' theorem allows updating the probability values by using new information or evidence. Here, probability of A is known as prior probability. That is the probability of event that before any new data is collected. Probability of A given B is known as the posterior probability. It is the revised probability of an event occurring after taking into consideration the new information. Probability of B given A is known as the likelihood, and probability of B is probability of observing an evidence. Bayes model. An example. Consider an example for calculating the likelihood of having diabetes based on frequency of fast food consumption. Here is the observed data. Let's say the fast food audience is 20%. Diabetes prevalence is 10%, and 5% is fast food and diabetes. The chances of diabetes given fast food, that is the conditional probability of D given B, can be calculated as probability of diabetes and fast food together divided by probability of fast food. That means 5% divided by 20%. That equals 25%. Define an analysis can state eating fast food increases the chance of having diabetes by 25%. The multiplication rule of probability. If events A and B are statistically independent and probability of A intersection B can be given as probability of A given B multiplied to probability of B. However, probability of A intersection B is also given as probability of A multiplied to probability of B. Here, probability of A given B equals to probability of A when we assume that probability of B is non-zero. Similarly, probability of B equals probability of B given A, assuming probability of A is non-zero. Chain rule of probability. Joint probability distributions over many random variables can be reduced into conditional distributions over a single variable. It can be expressed as probability of x1, x2, so on until xn equals probability of x1 intersection probability of xi, given probability of x1 till xi minus 1. For example, the joint probability of A, B, and C can be given as probability of A given B. C multiplied to probability of B given C multiplied to probability of C. Logistic sigmoid. The logistics function is a type of sigmoid function that aims to predict the class to which a particular sample belongs. Its outcome is discrete binary value, a probability between 0 and 1. The logistics sigmoid is a useful function that follows the yes curve. It saturates when the input is very large or very small. Logistics sigmoid is expressed as sigma of x equals 1 upon 1 plus e to the power minus x. The logistic sigmoid can be expressed as sigmoid function of x is given as 1 upon 1 plus e to the power minus x, where e is the Euler's number. Gaussian distribution. The Gaussian distribution is a type of distribution in which data tends to cluster around a central value with little or no bias to the left or right. It is often referred to as normal distribution. In absence of prior information, the normal distribution is frequently a fair assumption in machine learning. Equation. The formula for calculating Gaussian distribution is described as the normal distribution of x. That is the function of x given mean as mu and variance is sigma square can be calculated as 1 upon sigma square root of 2 pi e to the power minus half x minus mu divided by sigma whole square, where mu is the mean or peak value, which also is the expected value of x. Sigma is the standard deviation, sigma square is the variance. A standard normal distribution has a mean of 0 and a standard deviation of 1. Gaussian distribution can be univariate, which describes the distribution of a single variable x. It can also be multivariate, where it can just use to describe the distribution of several variables. It is represented in 3D of ND formats. Law of large numbers. Now let's talk about law of large numbers. The law of large numbers states that an observed sample average from a large sample will be close to the true population average, and that it will get closer in the larger sample. So the law of large number does not guarantee that a given sample, spatially a small sample, will reflect the true population characteristics, or that a sample does not reflect the true population will be balanced by a subsequent sample. This is for the law of large numbers to express the relationship between scale and growth rate. So there are multiple examples through which we can understand, and it is widely used in statistical analysis in working with the central limit theorem in terms of the business growth. So there are multiple real-time setup in which these are going to be used. So if you talk about tossing a coin, so tossing a coin in a number of times will give us two different type of outcomes. The result will spread evenly between head and tails, and the expected average value is going to be half. That means 50 times tails and 30 times heads. But again, if you toss a coin 1,000 times, then the result can be in different manners, because out of 1,000, let's say 850 times it has been head, and only 150 times it has been tails, and so on. So that's why the possibility of one event occurring is going to be changed in large sample sets as compared to a small sample sets, as in let's say 10 times. So the number of heads and tails unbalanced for lower number of trials, so we can see it is unbalanced. But again, as soon as we toss more number of coins, more leans towards the balance value, or we can see the observed averages. Next, we have p-value. So p-value is basically a number calculated from the statistical test that describes how likely we are to have found a particular set of observations if the null hypothesis were true. So p-values are used in hypothesis testing to help decide whether to reject the null hypothesis. And the smaller the p-value, the more likely we are to reject the null hypothesis. So we have a term called as null hypothesis. So all statistical tests, they have null hypothesis. So for most tests, the null hypothesis is that there is no relationship between our variables of n first, or that there is no difference among groups. For example, in a two-tail t-test, the non-hypothesis is that the difference between two groups is going to be 0. So p-value is going to tell us how likely it is that our data could have occurred under the null hypothesis. It is done by calculating the likelihood of a test statistic, which is the number calculated by a statistical test using our data. So p-value tell us how often we would expect to see a test statistic as extreme or more extreme than one calculated by a statistical test. if the null hypothesis of the test was true. So there are multiple limitations as well. So first one is the results can be significant, but again, they may not be practical as we have compared. It can be based on multiple hypotheses for a game, for the healthcare test. If the test is going to be positive or not, it may show even values of the effect of a variable, but not the magnitude in real life. What exactly is going to be the application of a drug test being failed in pharma company? Therefore, it is recommended to use confidence and levels in addition to the p-values to quantify, or we can say to give a solid figure to the reserve, which we are going to get. The p-values, they are interpreted as supporting, or we can say refuting, the alternative hypothesis. So p-value can only tell you whether or not the null hypothesis is supported. It cannot tell us whether our alternative hypothesis is true or why. So the risk of rejecting the null hypothesis is often higher than the p-value. So especially when we are looking at a single study or when using small sample sizes. So this is because the smaller frame of reference, the greater are the chance that as we stumble across a statistically significant pattern completely by accident. Key takeaways. Key takeaways. Probability and statistics structure the premise of the data. The data helps in anticipating the future or gauging in view of the past patterns of information. The central tendency is a single value that helps to describe the data by identifying these central positions. The mean, median, and mode are the measures of central tendencies. The distribution where the data tends to be around a central value with a lack of bias or minimal bias towards the left or right is called as Gaussian distribution.
Have you ever wondered how facial recognition works on social media? Or how object detection helps in building self-driving cars? It is all possible thanks to Convolutional Neural Network CNN. Hello everyone, I am Mayank and welcome to Simplilearn. Today we will take you through a hands-off lab demo of how we can use CNN model for image classification in machine learning. For amazing videos like this, subscribe to our YouTube channel and press that bell icon to stay updated. In today's session, we will discuss what CNN model is, and moving ahead, we will discuss how does CNN recognize images. After that, we will see layers in CNN. At the end, we will do a hands-off layer demo of image classification using CNN. In fact, a study says there will be more than 2.3 million job openings in field of artificial intelligence and machine learning by 2023. But you can beat the curve with our professional certificate program in AI and machine learning, co-sponsored by Purdue University and IBM, which is designed after Simplilearn Intense Bootcamp Learning Model AI and ML certification course. This course covers tools and techniques like Python, TensorFlow, Keras, NLTK, and many more, along with industry projects like social media by Twitter, delivery service provider by Zomato, transportation service provided by Uber, and many more amazing projects. Choosing this course can you get hired by renowned companies like Google, Amazon, LinkedIn, and Adobe, and an average salary hike of 70%. So what are you waiting for? Join the AI and ML Professional Certificate Program and excel your career in artificial intelligence and machine learning. The link is in description box below. Before we move on to the programming part, let's discuss what CNN is and proceed further for the same. What is CNN? A convolutional neural network is a feed-forward neural network that is generally used to analyze visual images by processing data with grid-like topology. It is also known as convnet. A convolutional neural network is used to detect and classify objects in an image. So this is a neural network that identifies two types of flowers, orchid and rose. In CNN, every image is represented in the form of an array or pixel. Here you can see it is a real image of digit 8 and it is represented in the form of an array, and here 0 represent negative values and 1 represent positive values. Okay, it's creating 8 here. So digit 8 represent in the form of pixels of zeros and ones. So now let's understand the convolution you're operating using two matrices A and B of one dimension. Now let's understand the convolution operations using two matrices A and B of one dimension. A equals to 532, 597, B equals to 123. So in convolution operation, the arrays are multiplied element wise and the product is summed to create a new array which represent A into B. So here A into B 532 and 123, multiply the arrays element wise, and this is the sum of the product. So the first three elements of the matrix A are multiplied with the elements of matrix B. and the product is summed to get the result. So A into B is 17. The next three elements from the matrix A are multiplied by the element in the matrix B, and the product is summed up. So here sum of the product is 22. So A into B is 17 and 22. This process continues until the convolution operation is complete. So moving forward, now let's discuss how does CNN recognize images. So consider following these images. The boxes that are colored represent a pixel value of 1 and 0 if not colored. When you press backslash, the below image gets processed. And when you press the forward slash, the below image is processed. Here is another example to depict how CNN recognizes an image. So consider this is a real image. Now it is represented in the forms of black and white pixels. And this image is represented in the form of matrix of number. Here you can see where here the black part and here is one value. So it's creating the image. Image represented in the forms of matrix of numbers. So as you can see from this diagram, only those values are lit that have value of 1. Okay, this is how the CNN recognize the images. Now moving forward, let's see layers in convolution neural network CNN. A convolution neural network has multiple hidden layers that help in extracting information from an image. The 4 important layers in CNN are: first is convolution layer, second is pooling layer, third is ReLU layer, and fourth is fully connected layer. So now let's start with convolution layer. So this is the first step in the process of extracting valuable features from an image. A convolution layer has several filters that perform the convolution operations. Every image is considered as a matrix of pixel value. So consider this the following 5x5 image whose pixel values are either 0 or 1. There is also a filter matrix with a dimension of 3x3. Slide the filter matrix over the image and compute the dot product to get the convolved feature matrix. And the second is ReLU layer. ReLU performs an element-wise operation and sets all the negative pixels to 0. It introduces non-linearity to the network, and the generated output is a rectified feature map. So below is the graph of ReLU function. So the original image is scanned with a multiple convolution and ReLU layers for locating the features like this. ReLU layers creates the feature maps like this, and after that input feature map creates the rectified feature map. This is how black negative is to white non-negative values or positive values you can say. So it will create the rectified feature map, ReLU layers. So now third layer comes into the action, pooling layer. So pooling is a downsampling operation that reduces the dimensionality of the feature map. The rectified feature map now goes through a pooling layer to generate a pooled feature map. So this is a rectified feature map. So here 3, 4, 1, 2. From this it will take the maximum value. Here is 4, and from this it will take the maximum value 7, and from this it will take the 8 and 6. Okay, so max pooling with 2x2 filters, and this is the stride 2. The pooling layers uses various filters to identify different parts of images like edges, corners, body, feathers, eyes, and beak, as you can see from the picture. So now let's see how the structure of CNN looks so far. Here's the diagram represent the structure of CNN so far. So the next step is a process is called flattening. This is called the flattening process. So flattening is used to convert all the resultant two-dimensional array from pooled feature maps into a single long continuous linear vector. So as you can see, it is a pooled feature map. After flattening, it converts into single long continuous linear vector. The flattened matrix is fed as input to the fully connected layer to classify the images. So this is CNN, here comes the ReLU, then pooling, then it is the input to the final layer. After this, so input image, then convolution layer, then ReLU layers comes in, then pooling layer, then flattening. Now this is fully connected layer, which is CNN. This is how the CNN create after connecting the 3 layers, ReLU, convolutional, and pooling layers. So this is how exactly does CNN recognize images. Okay, the pixel from the image are fed to the convolution layer that perform the convolution operations here. Then it results in a convolved map. The convolved map is applied to ReLU function here. The convolved map applied to ReLU function to generate a rectified feature map. Here it creates the rectified feature map. And the image is processed with multiple convolution and ReLU layers for locating the features. Then different pooling layers with various filters are used to identify specific parts of the image. Here the max pooling does. So the pooled features is flattened and fed to fully connected layers to get. This is the flattened fed to fully connected layers. This is fully connected layer, and that is how it got the final output bird. Okay, this is a feature extraction in multiple hidden layers, classification in the output layer. So now moving forward, let's start the programming part. So here, so this is the Python kernel file. So here first we will change the name CNN for beginners. Okay. Rename. Okay. Yeah. So first we will import some major libraries of Python. So I will write import numpy as np. Then I will write import pandas as pd and import matplotlib dot pyplot as plt. Import cborn as sns. Then import Keras. After that, import TensorFlow dot Keras. So NumPy is a Python library used for working with arrays. It also has a function for working in the domain of linear algebra and matrices. It is an open source project and you can use it freely. NumPy stands for numerical Python. And the second one is Pandas. Pandas is a software library written for the Python programming language for data manipulation and analysis. In particular, it offers data structure and operations for manipulating numerical tables and time series. And the third one is matplotlib. So for Python and its numerical extension NumPy, matplotlib is a cross-platform data visualization and graphical charting package. As a result, it represents a strong open source substitute for MATLAB, and the API application programming interfaces for matplotlib allows programmers to incorporate graphs into GUI applications. And the fourth one is cborn. Cborn is a Python data visualization library based on matplotlib. It provides a high-level interface for drawing attractive and informative statistical graphics. For a brief introduction to ideas behind the library, you can read the introductory notes for the paper. And the Keras. Keras is an open source software library that provides a Python interface for artificial neural network. Keras acts as interface for the TensorFlow library up until version 2.3. Keras supported multiple backends including TensorFlow, Microsoft Cognitive Toolkit, Theano, and PlayML. And the fourth one is TensorFlow. TensorFlow is a free and open source software library for machine learning and artificial intelligence. It can be used across a range of tasks but has a particular focus on training and inference of deep neural networks. Okay, so here we are going to load data. First, let me write the line x train, comma y train, comma x test, comma y test equals to Keras dot datasets dot fashion mnist dot load data. Okay, so there are 10 different classes of image as following, like t-shirt, top, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot. And the image that I mentioned are 28 by 28. So in this, we are splitting the data into training and testing set. So what is MNIST? So fashion MNIST consists of 60,000 training images and 10,000 testing images. It is a MNIST like fashion product database. The developers believe MNIST has been overused, so they create this as a direct replacement for the dataset. Each image is in grayscale and associated with a label from 10 classes. Each image is 28 pixels in height and 28 pixels in width for a total of 784 pixels in total. So each pixel has a single pixel value associated with it, indicating the lightning or darkness of that pixel. With higher number, meaning darker, the pixel value is an integer between 0 and 255. So moving forward, we will see that how much data we have in training and the testing. So here I will write x train dot shape there is no need, I guess, for this, comma, y train dot shape. Okay. See, we have 60,000 rows and 28 columns for a particular data set. Okay. Now, x test dot shape, comma, y test dot shape. Here are in the testing we have 10,000 rows and 28 columns. I already told you before when I talked about the data set, like we have 60,000 training images and that 10,000 testing images. Okay. So, and if you want this full code, I will provide you in the description box below. Just comment for the same that you want the full code. Okay. So now let's train the data. Okay. Then x train the label y underscore train. Let's see this. Fine. So what I will do with better visuals, I will do like this. So now let's see for the show images. So here I will set the class labels. Class labels t-shirt, t-shirt, or it can be top. Okay. Then trousers, then pullover, then dress, then coat, then sandal, shirt, sneakers, then bag, ankle boot. So let's see some images. So what here? I will write class. No. I will write plt dot show xtrain cmap show great. So see, it is ankle boot. It's look like an ankle boot. Let's see one more. Okay, plt dot I am show strain cmap equals to grays. Okay, it is a t-shirt. We have 60,000 images in the training set, so we can check the any. Let's see one more. BLT dot I am sure strain 15 equals to grace. Okay, there's a shoe. Okay, let's copy it. The last we are checking for the 50. Something dress. Okay, so this is that for the training. That is why we are writing here extrain. Right. So now let's see the all the categories. Okay, like sneaker, ankle boot, coat, and t-shirt. Okay, sandal and all. So for that, I will write here plt dot figure figure size. I will give 16 by 16. J equals to 1 for I in np dot random dot rand int 0 comma 10,000, sorry, 1,000 only, 25 elt dot subplot 5 comma 5 comma j plus equals to 1 plt dot I am sure xtrain I cmap equals to what? Grays. Okay. Then plt dot axis of and plt dot title again calibrated. What I will write here dot format class equals train train. Okay, so now let's see, run it. Okay, so there is an error. Object has no property cap. Okay, it is cmap. See, now you can see the sneaker, bag, pullover, sandal, dress. So all the categories. Okay, shirt, coat, bag, sneaker. This is for the training. The trousers we are training all the images. Okay, for the model. So now what we will do, we will reshape some training data. Okay, the length and the testing data length. Okay. So moving forward, we will do that. Let's do the reshaping and all. So fashion m equals to Keras dot datasets dot fashion right here x train y train comma x test equals to fashion data x train this dimensions. So here I will write x train minus 1. Okay, or we can write x train equals to x train dot reshape length x train. Okay, here I will write x test equals to np dot expand dimensions x test comma minus 1. Okay, here I will write a1 equals to np dot array d dot unique train one equals to and here I will write for a1 then e index 1 dot append to list y train dot index I. Okay, then print index 1. Okay, so cross check for I in index print y train I. Okay, so here I will write plt dot figure size equals to 24 comma 24. Okay, for x comma y in enumerate index 1 this. Here I will write print x train dot shape then plt dot subplot 2,5, comma x plus 1 plt dot I am show TensorFlow quiz and x train y equals to grace. Okay. plt dot title dot format k1 x. Okay, x train and p dot index to expand gives x train minus 1. Okay, so there is a okay. Valid index. What I wrote here, let me check. Import numpy as np. The error. Okay, let me check the other. Working. These are the 10 category. Okay. These are the pixel size 28 into 28. Okay. So moving forward, what we will do, we will change the dimensions. Okay. And then after that, we will do the feature scaling. Okay. For the changing dimension, we'll do x train dot ndim. 3 means 3-dimension image. This one is the 3-dimension image. Then x train dot shape is 60,000. Then what I will do, x train equals to np dot expand train comma minus 1. Test equals to np dot expand test comma minus 1. So 4-dimension image x train Okay. And dim. This is a 4-dimension image. Okay. The next train dot shape. Okay, fine. So now what we will do the feature scaling. So for the feature scaling, I will write here x train equals to x train by 255. Okay. So here I will write x test equals to x test by 50. So what is feature scaling? Feature scaling is a method used to normalize the range of independent variables or features of the data. So in data processing, it is also known as the data normalization and is generally performed during the data pre-processing steps. Okay. So let's see the data is in 0 to 1. For that, I will write here small code x train in 0. So now what we will do, we will split the data set for the validation set. Okay, for that we will write here from sklearn dot model model selection import train test it train x value comma y train y value equals to train test split and here I will write train test split, then okay split, then I will write here x train comma y train comma test over here. Now I will write x train dot shape y train shape 8000. Okay, then x value dot shape comma y value dot shape. Okay, 12,000. See, our total images in x train were 60,000. So now we did the train test split. Okay, so test size is 0.2, so we split into like 80 and 20. Okay, so that is why there are 48,000 images. So now we'll make CNN model. Okay, convolutional neural network. So for the convolutional front end, we can start with the like 3 convolution layer with a small filter size and modest number of filters. Okay, followed by a max pooling layer. The filter maps can be the flattened to provide features to the classifier. Okay, so we know that we required an output layer with like 10 nodes in order to predict the probability distribution of an image belonging to each of the 10 classes. This is also require use of softmax activation function between the feature extractor and the output layer. We can add a dense layer to interpret the feature, in this case with the 128 nodes. Okay, so listen that like all layers will use the ReLU activation function and the weight initialization scheme, like both best practices. What we will do, we will create model. Okay, so this is the code for the model. Okay, so in this we use the layers. These are the three layers: layer 1, layer 2, layer 3. Okay, so as I said to you, we will start from the max pooling layer. Okay, so here we used units equals to 128 and activation equals to ReLU. Okay, and there is dense again the layer. So max pooling, here is a term max pooling 2D. So it is a pooling or max pooling operation which calculates the largest or the maximum value in every patch and in the every features. Okay, so it is used in the pooling operation that calculates the maximum value for the patches and to create the pooled feature map. Got it? And here is a dense. So dense is like in any neural network, a dense layer is a layer that is deeply connected with the preceding layer. So which means the neurons of the layer are connected to every neuron of its preceding layer. The layer is mostly commonly used in artificial neural network. Okay, and there is dropouts, like how much it will be dropout for every layers, from every layers. There is one more word, flatten. So flattening is used to convert all the resultant two-dimensional array from pool feature map into a single long continuous linear vector. The flattened matrix is fed as input to the fully connected layer to the classify image. Okay, and this softmax is a like equation or a function you use to activation function in the output layer of the neural network, and that predict a multinomiality probability distribution. That is, softmax is used as the activation function. Okay, and ReLU is again you know uh, a particular layer forward. The visuals. So now what we will do, we will plot the neural network for the workflow. Okay, Keras dot details plot model to file equals to model dot png. It's happening. Show tips equals to true. Here I will write show layer equals to true. There is an error. Okay, model is not defined. So what we have to do, we have to install here pydot. Okay, pip install pydot and install graphviz. Okay, so let me install and I will come back to you. So here what I will write, we'll see the model dot summary. This is the model summary. Okay, and now what we will do, we will compile and model fitting, do the model fitting. So here I will do the model dot compile optimizer equals to Adam equals to categorical cross tropy. Okay, here I will add matrix equals to accuracy. Okay, so now I will write model dot fit. Okay, will write here. Let me delete this. Model dot fit train comma train comma epochs equals to 20 comma batch size equals to 512 comma verbose equals to 1 comma validation data equals to x var comma y. Okay. So it will take time. It will run till 94. Okay. The loss, the accuracy will come. So we have to wait for some more minutes. We'll let it be complete. It will go till 20. So I will get back to you when it will be complete. Almost 14 done. 15, 16, 17, 18, 19, 20 are left. So we'll wait and we'll see. So an epoch is when all the training data is used at once and is defined as the total number of iteration of all the training data in one cycle for the training and machine learning model. So another way to define an epoch is the number of passes a training dataset takes around an algorithms. Okay. We'll wait till 20. Maintain. 3 more left. They are the loss, accuracy, and validation loss, value loss. If you want this full code, you can comment. And if you have any query related to Python, machine learning, or anything, okay, you can comment down. Our team will reach you as soon as possible. So, two more, 19 and 20. Accuracy, our model accuracy is good, 93. If you have any query, you can comment down below. Okay, 19 is done. Final 20 is going on. Epoch. You can enroll in our course of AI and ML. You can check the link in the description box below. It's in course. After this, we will test the model, then we will do evaluation, then confusion metrics, and then visualization of the output, the final output. Okay. Yeah, so it's done. So now let's test the model, testing of the model. So now let's start the testing the model. Okay. So here I will write model dot predict np dot expand okay, x test at 0 axis round. Okay. Round is how many decimal points. Okay. So now np dot argmax and model dot predict np dot expand aims x test this will be 0, this will be 0 dot round at the 2. Okay. Okay. Axis not okay. So here I have to write x equals to 0. Okay. So now cross check y test 0 same. Okay. Then y prediction equals to model dot predict then x test to prediction. So now we will evaluate. So model dot evaluate test comma y test. Okay. So now let's do the model evaluation. So accuracy given by train set is 0.94, which is very good, 94%, and accuracy given by test set is 90%. So thus we can say that our model is generalized, so no overlifting or not underfitting. Okay. So now confusion matrix. So from sklearn dot matrix import confusion matrix. Okay, then plt dot figure, then figure size equals to 16 comma 9 y underscore prediction y prediction equals to np dot arg max label or label in y prediction. Then cm confusion matrix equals to confusion matrix y test by prediction labels. Okay, so now we will write map. We'll create heat map sns dot heat map confusion matrix comma a not was to true, then fmt equals to d comma x tick labels equals to class dot labels, then y tick label equals to class labels. Okay, there's an error. Yeah, see, the heat map is came. Okay, this is for the t-shirt, pullover, dress, coat, and hair also. Okay, so now we will visualize the output. So plt dot, so it is like coming correct or not. Okay, expected and predicted. Okay, or you can say the actual and predicted. So plt dot figure figure size equals to 16 comma 30 equals to 1 or I in np dot random dot tangent comma 60 plt dot subplot x comma j. Then here I will write j plus 1 plus equals to 1. Then plt dot I am show x test I reshape 28, it's 28 height and width, and cmap equals to grace. plt dot access of plt dot title Here, right, actual equals to okay. Slash n predicted equals to dot format class labels my test test I p dot the max and y predicted is I, then we'll write np dot arg max y predicted I. Press enter. Loading. So as you can see, actual is t-shirt shop, t-shirt and top, then predicted is also fine. Okay, some error, then trousers are same, sandals are same, ankle boot also same. So as you can see here, some are right and some are wrong. See, because the testing accuracy is 90%, the predicting accuracy is, the training accuracy is 94%. That is why. Okay. So this is the CNN of image classification, how you can use. And if you have any queries related any code or you want this full code, you can ask me in the comment section. Okay, I will provide you the full code. So mostly the predicted and actual are coming. Till then everything is coming good.
What's in it for you? First, we will introduce you to each of these platforms, TensorFlow, Keras, and Pytorch in brief. Then, we will look at how these platforms differ from each other based on certain criteria such as level of API, speed, architecture, datasets and debugging, ease of deployment, and ease of development. And finally, we will wrap up this video by seeing which framework you should use. So, let's get started. Before we can see the differences between these platforms, we first need to know what exactly each of these platforms are. Let's start with TensorFlow. What is TensorFlow? TensorFlow is a low-level software library which is created by Google to help implement machine learning models and to solve complex numerical problems. TensorFlow is nothing but a free and open source software library for machine learning. It can be used across a range of tasks but has a particular focus on training and inference of deep neural networks. TensorFlow is a symbolic math library based on data flow and differential programming. It is used for both research and production at Google. What do you mean by data flow? It basically means that we perform calculations by converting every element into graphical form. The variables of the graph are called tensors and mathematical operations are called operators. Here, in the computational graph shown, you can see that x, y, and 2 are the variables. They will also be called tensors, and division, multiplication, and addition are the operators. This graph basically shows us the calculation that is going to occur in a machine learning model where x and y are going to be divided and y and 2 are going to be multiplied. The results of these two calculations are then going to be added to give us the final output. I told you that x, y, and 2 are also called tensors. What exactly are tensors? Tensors are multidimensional arrays with a uniform type. All tensors are immutable like Python numbers and strings, which means that you cannot update the contents of a tensor. You can only create a new tensor. Next, let's look at the API Keras. What exactly is Keras? Keras is a high-level deep learning API written in Python for easy implementation and computation of neural networks. Keras is an open source software library that provides a TensorFlow interface for artificial neural networks. Keras acts as an interface for the TensorFlow library, which means that it runs on top of TensorFlow. Up until version 2.3, Keras supported multiple backends, including TensorFlow, Microsoft Cognitive Toolkit or CNTK, R, Theano, and PlaidML. As of version 2.4, only TensorFlow is supported. Designed to help enable fast experimentation with deep neural networks, it focuses on being user-friendly, modular, and extensible. Keras is a high-level API of TensorFlow, an approachable, highly productive interface for solving machine learning problems with a focus on modern deep learning. It provides essential abstractions and building blocks for developing and shipping machine learning solutions with high iteration velocity. Keras does not perform its own low-level operations such as tensor products and convolution. It relies on backend engines for that. Even though Keras supports multiple backend engines, its primary backend engine is TensorFlow, and its primary supporter is Google, which means that Keras acts as nothing more but a wrapper class around TensorFlow, Theano, CNTK, PlaidML, or MXNet, which are low-level APIs. Next, we will look at Pytorch. What exactly is Pytorch? Pytorch is a low-level API which is developed by Facebook for natural language processing and computer vision. It is a more powerful version of NumPy. It is an open-source machine learning library based on the Torch library used for applications such as computer vision and natural language processing. Primarily developed by Facebook's AI Research Lab, it is free and open-source software released under the modified BSD license. Although the Python interface is a more polished and the primary focus of development, Pytorch also has a C++ interface. Python is a widely liked language because it is easy to understand and write. Pytorch emphasizes flexibility and allows deep learning models to be expressed in basic Python. Pytorch is mainly used for natural language processing and for computer vision. Now let's move on to the differences between TensorFlow, Keras, and Pytorch. The first difference that we'll be looking at is called level of API. There are two main types of APIs, a low-level API and a high-level API. API stands for Application Programming Interface. A low-level application programming interface is generally more detailed and allows you to have more detailed control to manipulate functions within them on how to use and implement them, while a high-level API is more generic and simple and provides more functionality with one command statements than a lower-level API. High-level interfaces are comparatively easier to learn and to implement the models using them. They allow you to write code in a shorter amount of time and to be less involved with the details. In this case, TensorFlow is a high and low-level API. Pure TensorFlow is a low-level API, while TensorFlow wrapped in Keras is a high-level API. Keras in itself is a high-level API which uses multiple low-level APIs as a backend and simplifies the operation of these low-level APIs. Pytorch is a low-level API. The next criteria that we'll be looking at is speed. TensorFlow is very fast and is used for high performances. Keras is slower as it works on top of TensorFlow. Not only does it have to wait for TensorFlow to finish implementation, it then starts its own implementation. Meanwhile, Pytorch works at the same speed as TensorFlow as both of them are both low-level APIs. Now, Keras is a wrapper class for TensorFlow and has added abstraction functionalities on top of TensorFlow, which make it slower than TensorFlow and Pytorch. In computation speed, both TensorFlow and Pytorch are almost equal, and in development speed, Keras is faster as it has built-in functionalities which can significantly reduce your development time. The next difference is on the architecture. TensorFlow is not very easy to use, and even though it provides Keras as a framework that makes it work easier, TensorFlow still has a very complex architecture which is hard to use. Meanwhile, Keras has a simpler architecture and is easier to use. It provides a high level of abstraction which makes implementation of programs in Keras significantly easier. Pytorch, on the other hand, also has a complex architecture and the readability is less when compared to Keras. TensorFlow uses computational graphs which makes it very complex and hard to interpret, but it has amazing computational ability across platforms. Pytorch is a little hard for beginners but is really good for computer vision and deep learning purposes. Datasets and debugging. TensorFlow works with large datasets due to its high execution speed, and debugging is really hard in TensorFlow due to its complex nature. Meanwhile, Keras only works with very small datasets as its speed of execution is low. Programs do not require frequent debugging in Keras as they are relatively simpler, and Pytorch can manage high-level tasks in higher dimension datasets and is easier to debug than both Keras and TensorFlow. Next, we'll be looking at ease of development. As we said before, TensorFlow works with many hard concepts such as computational graphs and tensors, which means that writing code in TensorFlow is very hard. It is generally used by people when they are doing research work and really need very specific functionalities. Keras, on the other hand, provides a high level of abstraction which makes it very easy to use. It is best for people who are just starting out with Python and machine learning. Pytorch is easier than TensorFlow but is still comparatively hard than Keras. It is not very easy to learn for beginners but is significantly more powerful than just plain Keras. Ease of deployment. TensorFlow is very easy to deploy as it uses TensorFlow serving. TensorFlow Serving is a flexible, high-performance serving system for machine learning models designed for production environments. TensorFlow Serving makes it easy to deploy new algorithms and experiments while keeping the same server architecture and APIs. TensorFlow Serving provides out-of-the-box integration with TensorFlow models but can be easily extended to serve other types of models and data. In Keras, model deployment can be done with either TensorFlow Serving or Flask, which makes it relatively easy but not as easy as it would be with TensorFlow and Pytorch. Pytorch uses Pytorch Mobile, which makes deployment easy, but again, for TensorFlow deployment is way easier as TensorFlow Serving can update your machine learning backend on the fly without the user even realizing. There's a growing need to execute ML models on edge devices to reduce latency, preserve privacy, and enable new interactive use cases. In the past, engineers used to train models separately. They would then go through a multi-step, error-prone, and often complex process to train the models for execution on a mobile device. The mobile runtime was often significantly different from the operations available during training, leading to inconsistent developer and eventually user experience. All of these frictions have been removed by Pytorch Mobile by allowing a seamless process to go from training to deployment by staying entirely within the Pytorch ecosystem. It provides an end-to-end workflow that simplifies the research to production environment for mobile devices. In addition, it paves the way for privacy-preserving features via federated learning techniques. At the end of the day, the question that really matters is which framework should you use, Keras, TensorFlow, or Pytorch? Now, TensorFlow has implemented various levels of abstraction to make implementation of deep learning and neural networks easy. This has also made debugging easier. Keras is simple and easy but not as fast as TensorFlow. It is more user-friendly than any other deep learning API, however, and is easier to learn for beginners. Pytorch, on the other hand, is the preferred deep learning API for teachers, but it is not as widely used in production as TensorFlow is. It is faster, but it has lower GPU utilization. At the end of the day, the framework that we would suggest that you use is TensorFlow. Why? While Pytorch may have been the preferred deep learning library for researchers, TensorFlow is much more widely used in day-to-day production. Pytorch's ease of use combined with the default eager execution mode for easier debugging predestines it to be used for fast, hacky solutions and smaller scale models. But TensorFlow's extensions for deployment on both servers and mobile devices, combined with the lack of Python overhead, makes it the preferred option for companies that work with deep learning models. In addition, the TensorFlow board visualization features offers a nice way of showing the inner workings of your model to, say, your customers. Meanwhile, between TensorFlow and Keras, the main difference isn't in performance. TensorFlow is a bit faster due to less overhead, but also the level of control you would like. Keras is much easier to start with than plain TensorFlow, but if you want to do something with Keras that doesn't come out of the box, it will be harder to implement that. TensorFlow, on the other hand, allows you to create any arbitrary computational graph, providing much more flexibility. So if you're doing more research type of work, TensorFlow is the sure route to go due to the flexibility that it provides.
Welcome to the TensorFlow Object Detection API tutorial. In this video, I will walk you through the TensorFlow code to perform object detection in a video. So let's get started. This part is basically you're importing all the libraries. We need a lot of these libraries, for example, NumPy, we need image.io, datetime, and pill, and so on and so forth, and of course matplotlib. So we import all these libraries, and then there are a bunch of variables which have some paths for the files and folders. So this is regular stuff. Let's keep moving. Then we import the matplotlib and make it inline, and a few more imports. Alright, and then these are some warnings, we can just ignore them. So if I run this code once again, it will go away. Right, and then here onwards we do the model preparation. Now what we're going to do is we are going to use an existing neural network model. So we are not going to train a new one because that really will take a long time, and it needs a lot of computation resources and so on, and it is really not required. There are already models that have been trained, and in this case it is the SSD with MobileNet. That's the model that we are going to use, and this model is trained to detect objects, and it is readily available as open source, so we can actually use this. And if you want to use other models, there are a few more models available, so you can click on this link here, and let me just take you there. There are a few more models, but we have chosen this particular one because this is faster. It may not be very accurate, but that is one of the faster models. But on this link you will see a lot of other models that are readily available. These are trained models. Some of them would take a little longer, but they may be more accurate and so on, so you can probably play around with these other models. Okay, so we will be using that model. So this piece of code, this line, is basically importing that model, and this is also known as frozen model. The term we use is frozen model. So we import, download and import that, and then we will actually use that model in our code. Alright, so these two cells we have downloaded and imported the model, and then once it is available locally, we will then load this into our program. Alright, so we are loading this into memory, and you need to perform a couple of additional steps, which is basically we need to map the numbers to text. As you may be aware, when we actually build the model and when we run predictions, the model will not give a text. The output of the model is usually a number. So we need to map that to a text. So for example, if the network predicts that the output is 5, we know that 5 means it is an aeroplane. Things like that. So this mapping is done in this next cell. Alright, so let's keep moving. And then we have a helper code which will basically load the data or load the images and transform into NumPy arrays. This is also used in doing object detection in images. So we are actually going to reuse, because video is nothing but it consists of frames, which in turn are images. So we are going to pretty much reuse the same code which we used for doing object detection in images. So this is where the actual detection starts. So here, this is the path for where the images are stored. So this is, here once again we are reusing the code which we wrote for detecting objects in an image. So this is the path where the images were stored, and this is the extension, and this was done for about 2 or 3 images. So we will continue to use this, and if we go down, I'll skip this section. So this is the cell where we are actually loading the video and converting it into frames, and then using frame by frame we are detecting the objects in the image. So in this code, what we are doing basically is, there are a few lines of code. What they do is basically, once they find an object, a box will be drawn around those each of those objects, and the input file, the name of the input video file is traffic. It is the extension is MP4, and we have this video reader. It's an excellent object which is basically part of this class called image.io. So we can read and write videos using that, and the video that we are going to use is traffic.mp4. You can use any MP4 file, but in our case I picked up video which has like cars. So let me just show you. So this is in this object detection folder. I have this MP4 file. I'll just quickly play this video. It's a little slow. Yeah, okay. So here we go. This is the video. It's a short one, relatively small video, so that for this particular demo. And what it will do is, once we run our code, it will detect each of these cars and it will annotate them as cars. So in this particular video, we only have cars. We can later on see with another video. I think I have cat here, so we can also try with that. But let's first check with this traffic video. So let me go back. So we will be reading this frame by frame, and no, actually we will be reading the video file, but then we will be analyzing it frame by frame, and we will be reading them at 10 frames per second. That is the rate we are mentioning here, and analyzing it, and then annotating, and then writing it back. So you will see that we will have a video file named something like this, traffic_annotated, and we will see the annotated video. So let's go back and run through this piece of code, and then we will come back and see the annotated video. This might take a little while, so I will pause the video after running this particular cell and then come back to show you the results. Alright, so let's go ahead and run it. So it is running now, and it is also important that at the end you close the video writer, so that it is similar to a file pointer. When you open a file, you should also make sure you close it so that it doesn't hog the resources. So it's very similar. So at the end of it, the last piece or last line of code should be video_writer.close. Alright, so I'll pause and then I'll come back. Okay, so I will see you in a little bit. Alright, so now as you can see here, the processing is done. The hourglass has disappeared. That means the video has been processed. So let's go back and check the annotated video. I'll go back to my file manager. So this was the original traffic.mp4, and now you have here traffic_annotated mp4. So let's go and run this and see how it looks. You see here, it has got each of these cars are getting detected. Let me pause and show you. So we pause here. It says car 70%. Let us allow it to go a little further. It detects something on top. What is that? Truck. Okay. So I think because of the board on top, it somehow thinks there is a truck. Let's play some more and see if it detects anything else. So this is again a car, looks like. So let us, yeah. So this is a car, and it has confidence level of 69%. Okay, this is again a car. Alright, so basically till the end it goes and detects each and every car that is passing by. Now we can quickly repeat this process for another video. Let me just show you the other video, which is a cat. Again, there is this cat is not really moving or anything, but it is just standing there staring and moving a little slowly, and our network will detect that this is a cat, and even when the cat moves a little bit in the other direction, it will continue to detect and show that it is a cat. Okay, so yeah, so this is how the original video is. Let's go ahead and change our code to analyze this one and see if it detects, our network detects this cat. Close this, here we go, and I'll go back to my code. All we need to do is change this traffic to cat, the extension. It will automatically up because it is given here, and then it will run through. So very quickly, once again, what it is doing is this video underscore reader has a neat little feature or interface whereby you can say for frame in video underscore reader. So it will basically provide frame by frame. So you're in a loop frame by frame, and then you take that each frame that is given to you, you take it and analyze it as if it is an image, individual image. So that's the way it works. So it is very easy to handle this. Alright, so now let's once again run just this cell. The rest of the stuff remains the same. So I will run this cell again. It will take a little while, so the hourglasses come back. I will pause and then come back in a little while. Alright, so the processing is done. Let's go and check the annotated video. Go here. So we have cat annotated.mp4. Let's play this. Alright, so you can see here it is detecting the cat, and in the beginning you also saw it detected something else here. There looks like it detected one more object. So let's just go back and see what it has detected here. Let's see. Yes. So what is it trying to show here? It's too small, not able to see, but it is trying to detect something. I think it is saying it is a car. I don't know. Alright, okay, so in this video there's pretty much only one object, which is the cat, and let's wait for some time and see if it continues to detect it when the cat turns around and moves as well. Just in a little bit that's going to happen, and we will see. There we go. And in spite of turning the other way, I think our network is able to detect that it is a cat. So let me freeze and then show here it is actually still continues to detect it as a cat. Alright, so that's pretty much it. I think that's the only object that it detects in this particular video. Okay, so close this. So that's pretty much it. This is a list of libraries that are required, and they have been shown in the code as well. The exact purpose of each of this library, why it is required, is out of the scope of this tutorial, but we will see in the code as we walk through some of these libraries how and why they are used. The COCO data set. COCO stands for Common Objects in Context. So this data set consists of 300,000 images of 90 most commonly found objects like chairs and tables and so on and so forth. So this model has been trained, or in fact a set of models have been trained on this data set, and this is pretty good to detect the most common objects in the images and videos. So with that, let's get into the code. Alright, so the first part is to import all these libraries, and this we have shown you in the slides as well. Again, a large part of this will be for doing some helper functions and maybe for visualizing the images and so on and so forth. So that's the reason they are required. As I said, the exact details of each and every library probably is out of scope, but these are needed. So as a first step, maybe you just go ahead and include these libraries and run the code, and maybe at a later point we can discuss what each of these libraries does. Now this will work with TensorFlow version higher than 1.4. So if you are having TensorFlow version below 1.4, you may have to upgrade to a higher version. So let me go ahead and execute the cell, and we also need this line of code to make sure that once we run this object detection, the labeled images are displayed within this notebook, and many of you by now must be familiar with this. And we will import a few utility libraries, and you will see that we will be using some of these for visualization purpose. So once the objects are detected, we need to display the information, what that object is, and then what percentage of confidence the model has. So all these details, that's the utility functions that are stored here. And then the next part is to prepare the model. As I mentioned, we will be using an existing trained model. The TensorFlow team has actually provided these models. The one that we will be using is SSD with the mobile net, but you can actually use any one of the ones that are listed in this URL. Let me just quickly take you through this URL. These are a bunch of models, trained models that are readily available for anybody to use. It is open source. And let me scroll down. The only thing is that if there are some of them where the accuracy is much higher but they take longer, and there are some where the accuracy is not so high and they are much faster. So they are faster but the accuracy may not be that very high. So you can play around with some of these, and we in this particular exercise or in this particular tutorial we are using this SSD model, which is SSD mobile net version 1. So that's the model that we'll be using. So in this cell we are primarily creating a bunch of variables with the various, for example, the name of the model, the path, and so on and so forth, so that we will be using these names in the next step, which is to download this model and install it locally. These are also referred to as frozen models. So once they are trained, and then you kind of extract or you freeze the model. So that's the reason they are called frozen models, so that others can just use this without any further training. So this is where we download and extract our model locally. So this will take a little while. Let me see if I can wait or maybe pause the video and come back once it is done. Might take a little while. Let's see if it completes. I have a pretty high speed network, but even then it takes some time, so that's good. But this part is over. Now let us see this part, and yes, both are done. So once that is done, we need to load some label mapping. Basically what this will do is your model, as you may be aware by now, if you do some classification, the model will actually not give any output as a text. It will give some numbers. So if there are 5 classes, it will say, okay, this belongs to model class 1 or 2 or 3 or 5 and so on, the numbers. Now each of these will obviously, the numbers will not make any sense to the outside world, so we need to do some small mapping. So in this case, let's say 1 may be a chair, 2 may be a table, 3 may be a balloon, and so on. So that kind of number to text mapping we need to do, and that is what is being done in this particular cell. And then we have a helper code which will load the image and convert it into a NumPy array, so that the NumPy array is what gets processed and used by the model to do the detection part of it. So that is what this method is all about. So we will be later on we will be calling that function. And next is preparation for detection. So here we are basically telling where the images are stored and how many images, or what is the naming convention or format of the images. Now if you want, you can modify this code. For example, currently I have test_images as my folder. So let me go and show this to you. So this is under my object detection folder. I have another subfolder where I am storing my images, which is text_images. Now you can rename this folder and give some other name, and then in your code you can probably give that particular name for the subfolder. Similarly, the format of these files, what is the name and format of these files? Here it is in a very simple format, which is the names of the files are like beach1, beach 2, beach 3, and so on. So I have taken beach as the theme. So I have images which are related to beaches. So this is beach 1, beach 2, and then beach 3. I have a few others, but we will use these 3 for our demo. And so that's what I'm saying here. The name of the images will be beach something.jpg, which is JPEG format, and in this curly braces basically we will be filled with either 1, 2, or 3 based on in this particular for loop. Okay, so that is what this is doing. Alright, so the next step is to run inference on these images in a loop, and what we are basically doing here is getting these images one by one and then running through the model to find out what are the objects that can be detected, and then against each of the object a box will be drawn and it will be labeled with the name and the percentage of accuracy or confidence that the model detects these objects. Okay, so that is the function here, and so let me just run that piece of code, and here is basically where we are calling this function. So we are loading these images and then we are calling this function for each image, and then we are displaying this using the matplotlib library. So let's run this. It will take one image at a time and then detect the images. Now the beauty is that the same format of the code can be used for doing object detection in a video. So we have another video for doing object detection in a video. So most of the code out there will be reused from here, and the only thing is that instead of reading the images from the local storage, we read the frames from the video, and there is a neat little video reader that is available and it will be shown in the other video, and frame by frame we read the video and then pass on to this function, and it will act as if each of these frames is an image, and then it will do the same object detection on the entire video. So that's in a separate video, just look out for that, and actually the information about that is provided in the cards, the I symbol. So that's the video object detection in video. That's the separate tutorial. Alright, so now that we have all the pieces together, the last cell is where the whole action takes place. So let's run this and see how it looks. So it will take probably a little while, and there are about 3 images. Let's see what it detects. There we go. So good. So the first one, it has detected a person, and that too with 97% accuracy, which is I think pretty good. Okay, and then the next image, it detects umbrella and chair. There are a few other objects, but it's not able to detect. It has detected umbrella with 63% accuracy, or confidence rather, and the chair with 58%. Again, not bad. Then let's see the next image. So here, these are actually balloons, hot air balloons, but the model thinks it is a kite, which is probably not that bad. It sees there's something in the sky, and therefore probably it thinks it is a kite, and it detects that with 65% confidence. Okay, so that was pretty much all I wanted to show you in this particular tutorial about object detection in images.
The most popular deep learning library in the world. It has really, once they open sourced it, it was just amazing how much it's spread in use and how many tools are linked into TensorFlow. Tensors are vectors or matrices of n dimensions. And you can see here we have dimension 5, we have a dimension 4 by 5, or 5 by 4 as the case is, 5 rows by 4 columns. Here's one where it's 3 by 3 by 3. And so this is kind of nice because when you're processing pictures, there's certain things you want to do where you want the pixels to be next to each other. That's very important. Same thing if you're processing, say, a movie. You might want a 3 by 3 grid coming in where you have the layers of the frames coming in to be processed. So you can see how having different dimensions is really helpful in analyzing certain data structures. And this is what's so great about tensors, is you can, of course, flatten them out like we did earlier, or you can process them based on their location. In TensorFlow, all computations performed involve tensors. So everything going through is always looked at as tensors, as a matrix, or matrices of n dimension. TensorFlow architecture is as follows. Pre-processing data, build a model, train and estimate the model. And what we'll do is we'll go ahead and dig into use case implementation with TensorFlow. To do that, I'm actually going to go into, in this case, I'll be using the Anaconda Navigator. And you can use either Jupyter Lab or Jupyter Notebook. Most people are very familiar with Jupyter Notebook. It's very commonly web-based. The Jupyter Lab is the next version of Jupyter Notebook, and it just lets you have multiple tabs open when you're working on it. And if you're using Anaconda, you'll go under Environments, and you'll want to make sure that you have your TensorFlow installed. And you can simply, we'll do this, I have it installed, but you could do all, we'll do all. You can do a search under all for Tensor, and you can see all the different tensors. It's actually installed in here, version 1.13.1. If it wasn't, you could check the box and then run the install on there and it'd bring it right in. But we'll go ahead and start up our Jupyter Lab, which is going to open up, in this case I use Google Chrome. And in our Jupyter Lab or Jupyter Notebook, if you're in the notebook, you only have one tab and you won't have the added options, like there's a folder and different things you can do in the lab that you can't do in the notebook. But everything we're going to do, you can easily do in the notebook. And you'll start up a new project. Deep Learning is what I'm going to call this. And if you're not familiar, you can definitely, we have some tutorials out on the use of Jupyter Notebook and how to run it and set it up and things like that. The most basic is we put our code in here. It has a nice display, a nice interface, especially for data science. I can display all kinds of things on this page, and then you can just run this page right here. There's no code in it, so it's not going to show any thing until I put some code in there. And of course you can cut your cells and things like that. So the first thing we want to do is we want to import our tools. Now if you haven't, remember you got to install TensorFlow, and we'll also use Pandas. Pandas is a nice database setup. And that again is underneath your environment, and you can see here your whatever you're working on, my Simplilearn setup, where I've installed TensorFlow and Pandas in here. And I'll simply go up here and run this. I'm not going to see anything, so we've just imported those into our notebook that we're working on. So those are now available to us. And it helps to have some data to work with. And we have here, I'm going to create a path and a test path. And we'll go ahead and let's just highlight this whole path. And you can always post a note either down below in the YouTube video, or you can post a note on Simplilearn.com and ask for this path if you're not quite picking it up. But it is over here at the UCI EDU on their setup, and it's in their archive. So it's archive.ics.uci.edu/ML for machine learning /machine-learning-databases/adult. That's quite a mouthful. And in this case, we have adult data and adult test. But let's go ahead and just take a look at that. Let me just paste that right in there to our browser window. And here's our adult data. And if I click on there, it's going to come down as a download. I'm going to go ahead and open it as a text in my notepad. And the guys in the back were kind enough to look up to find out what the actual columns were in this coming across. So let me go ahead and take that to pull that information. And it doesn't matter whether I put it before or below, because these are just variables. But we can see here that we have age, work class, final WGT. I'm guessing that's final. We'll look that up in just a second to see what that matches. In fact, let's pull that up and just put them next to each other so we can kind of see what we got here. So we have age, we have our working class, state gov, maybe final wage, 77,516. Education of bachelor's, education number 13. Marital, never married. Admin, clerical. Relationship, not in family, so on and so on. So it goes all the way across here. And so we've pulled out this information, native country, label, etc. We'll go ahead and run this. And so now we've loaded all our different paths. And this path, by the way, this is the same columns on here, so I don't need to create a separate columns on the adult test. And once we've run this, we've set those variables. Let's go ahead and pull that data in. And to do that, we'll use Pandas. And we'll create a df train, a df test. Each one's going to have our PD for pandas.readcsv. It'll have our path we put in there, our path test. The first one, we went ahead and skip initial space, true, names columns. There's our columns in there. Index column equals false. There's no index column. On the second one, if we went back into here and we open up adult test, let me just go ahead and open that up, pad. You'll see there's an actual row up here we want to skip. 1x3 cross validator with all the same data in it. So we're looking at the same data in there, and here we're going to go ahead and bring in our data. And then once you bring it in, it's always nice to see what kind of shape your data is in. And of course, when we talk about shape, we're talking about how many rows and columns, not whether it's been lifting weights. We can see here we have, each one has 15 columns, and that goes with our columns right here. If we counted them, there's going to be 15. And the first data set has 32,561 rows, where the second one has 16,281 rows. And it's also good to see just how the data came in. So we'll use the pandas D types. We'll run that. And you can see here where age came in as an integer 64. Working class as an object, which makes sense. And then we have our FNLWGT, the education as objects, or, well, this is an integer object, so on, all the way down. And if we flash back to the data, we look at the last column, it's less than or equal to 50K. And if we scroll down enough, we'll see it's also greater than or equal to 50K. So we'd like to kind of give that its own special setup on that label. So on that feature, we're going to set the label equal to, if it's less than or equal to 50K, it's going to be 0. And if it's greater than or equal to 50K, it's going to be 1. So it's one or the other. That's always an easy thing to read. And then we can take this and we can go dftrain.label equals label item for item in dftrain label. And this just loops through all the labels. There's a lot of ways we can do this. Pandas, this might be actually kind of a slower way. There's a way to do just that setup and do the logic within the setup instead of doing a loop. But for this thing, it'll work fine. We're not dealing with a lot of data. You know, it's a large data set, but it's not that big of a data set as data goes. And we also want to do it for our test data. I didn't really mention that we created we're looking at two different data sets. One, we're going to train the data, and then we're going to take it and run the test data to see if it works. So we have our two different data sets, and we didn't catch it off the bat. If you were pulling up this, you're going to pull up one, this is the training set. And if we go back in here and open up the test set, let me just go back and do that, adult test. One of the things that we didn't notice that you'll want to pull up is at the end there's a period. So we're pre-processing our data. We want to make sure that we include that period in every line on the second setup. So when I go back to my Jupyter Notebook, I've got to have a label T, which is less than or equal to 50K period, or greater than or equal to 50K period for 1. Otherwise, it's doing the exact same thing. We're going to change the df train label and the df test label to 0 or 1. We'll just run that. We'll go ahead and print the df train label value counts and the df test label value counts. And this is always a good idea because we want to know, is there any weird stuff going on there? If there's null values, stuff like that, this will turn up on that setup. And we can see here we have zeros, how many ones, and so on there. Just a quick view of the data that we're going through. And if we go back up here, go ahead and print the train D types again. And we run that. You could actually run it up there and it'd give you the new answer because this loaded this information. We now see it's an integer. And if you go back up here, it was an object. So that makes life a little easier as far as what we're doing with this. Now at this point, we're going to look at the data and we can see we have a lot of numbers and we have a lot of categories in here. So categories would be United States, male, never married versus 7. And we can also see that when we looked at this, we have our integers, we have our objects, working class. So the next thing we want to do on there is we want to go ahead and take that where we have integers and the objects, and we want to bring that down here. We want to create those categories in a way that the computer can see them. And we'll start with our continuous features like age. We can see age integer, FNLWGT is an integer, capital gain is an integer, educational number, there's our educational number is an integer, and so on. So if we're going to have these as continuous features where they're an integer, we also need to make a list of the categorical features we want to work with, such as working class, education, marital, occupation, relationship, race, sex, and native country. And again, these are all objects. So that makes sense. And when we flip back over to the data, we can see here we're actually looking at United States. If we continue down, see if I can find another one. A lot of United States on this particular one. I was getting worried there for a second that we only had United States and it was a very biased census, which it probably is for wherever it came from. And of course, bachelor's, associate, vocational, some college. So you can see this is more categorical versus an actual number. So now we have our categorical and we have our continuous features. And this is just the list of these. So let's go ahead and run that and load that list in there so we can now start manipulating our data with it. Now we get our first line of TensorFlow code, which is exciting. And we're going to create a variable continuous features. And what we're doing in here is we're going to go into TF feature columns. So we have the feature columns. We're going to set those up. Numeric columns K for K in continual features. So this is going to go in here and says each one of these is a continual feature, and we're going to feed that into the feature column. Not very exciting on the output because we're just creating this variable here, letting it know what columns are what. Then we're going to create a relationship setup. So we have continuous features, and then we have a relationship. And again, we're doing TF, but in this case, we use feature column. So just like this one, we're telling it feature column, and now we do categorical column with vocabulary list. So that's one of the things we can do with TensorFlow. And we're going to feed it one. We have relationship, and so we're just drilling down to the relationship column. And these are the options they had. So this is going to be the vocabulary attached to this column. And we'll go ahead and run that. So we load up our relationship. And then we're going to do one more way of loading. And this one, we're going to do categorical features. And so in categorical features, we're going to do TF feature column. There's our command we've already seen before. And it's going to be categorical column with hash bucket. We're going to create buckets. In this case, for K in categorical features, so it's going to create a bucket for each one of these categorical features. And the bucket size is 1,000. So we're looking at, and we've actually kind of repeated something because relationship is also in the bucket setup on there. But we wanted to show you three major ways of loading in your different features. One is our features that we know where it's going to be a number. So our continuous features, then we can set it as a relationship. In this case, we actually created a vocabulary, husband, not in family, very clear vocabulary on there. And then we also are loading just general categories into buckets. You can set different bucket settings in here. We went ahead and just went with 1,000, so pretty much everything, since there's not a huge number of categories, each one gets their own kind of bucket setup in there. And as far as the initial setup, we need to go ahead and create a model. And so this is where it starts to come together. We've, as far as the pre-setup, we have our TF, we have an estimator. We're going to do linear classifier on the estimator. In classes equals 2, so we know there's only 2 classes we're looking at. We have ongoing train feature columns. And then we have our different, we have categorical features plus continuous features. So this basically creates our model, what data is going in. And we'll go ahead and run this. And you can see here that it gives us a little information that we had our TensorFlow using default config. You can change a lot of defaults you can change as far as the model directory, random seed, saving summary, checkpoints. There's all kinds of things you can go in here and set up. Rewrite options, keep checkpoint mix, etc. At this point, the model hasn't done anything. All we've done is create the model. So let's just do a real quick rehash of what we've done so far. What we started off with is we grabbed some data. In this case, adult and adult tests. We have a training data set and a test data set. We set the columns up. We took a very short, brief exploration of the data and its shape as far as what we're working with. We changed our label around a little bit so that the label makes a little bit more sense of 0, 1. Instead of, for the machine, it's easier to spit out a 0 or a 1. We can look up here, we double check to make sure how many zeros and ones we have. Double check our data, make sure it's integer 64, nothing weird's going on. And then we looked at 3 different ways that we can kind of label the data as far as the way we're going to read it. We have our continuous features and a categorical features. Here's our relationship, which is one of them. When we went ahead and created our model, we did not put the relationship in here, which you can do. You can actually maybe take it out of categorical and then have its own on here instead of having categorical features and continuous features and so on. So we've created our setup for our model. The next thing we need to do is we need to go ahead and create a function letting it know how to read the data into our model. How are we going to train it? And let's go ahead and create 2 variables. The first one is going to be features. This is just all the features that are in there. And then the second one is going to be our label. And this is basically, we're looking at all the different information we can put into it, and then is that person, based on that information, going to make less than or greater than 50K? That's what that comes down to. Now, the next part, the definition we're going to create has a lot in it. And we're going to feed this definition into our model training. So there's a lot of stuff that goes on here. First, we'll call it get input and function. Def get input function. We have our data set, number of epochs equals none, in batch equals 128, shuffle equals true. So we're running this, and this is going to return a TF estimator inputs pandas input function. And in this case, it's going to be x equals our PD data frame K data set K values for K and features. Y is PD series, dataset label values, batch size equals in batch, number of epochs equals number of epochs, shuffle equals shuffle. So in here we're passing in the number of epochs. We're not too worried about, we're going to just go once through the data because there's a lot of data in there. We don't need to rerun it. Epochs is how many times do you cover all the data? And then how many groups of data do you pull in and batch at a time? So we're only going to look at 128, do the reverse propagation like we talked about, and then it'll go to the next batch, and the next batch, and the next batch, and it shuffles them. So shuffle means that we're randomly picking where they're coming from. And we're not too worried about the number of epochs for this particular model. Depending on how much data you have and depending on what you're running, depends on how many epochs you need to run. And there's a lot of rules on how many epochs you need to run. One of them is if your training data and your testing data, because you'll check your testing data against your training data. If your testing data starts having a better results than your training data, that means you're no longer fitting towards the data, but you're fitting to the answer. So it's kind of these little weird things you start to on here. And TensorFlow is really cool because it actually checks a lot of that for you. But we're just going to set number of epochs equal to 0, and then we have our data set going in. So we're creating our get function. How do we get the data into training our model? And we'll go ahead and run that. So now we have our data function, and now it knows where the data is coming from. So we need to go ahead and train it. And that's simply we take our model we created way up here. That's where we take the model there. We've told it what columns it's going to pull in, so it knows what columns it's looking at, know what the definition where it's going to get the information from. So now we want to go ahead and train it. And here's our input function equals, in this case, get input function. And here we tell it that our data set is a df train, number of epochs equals none, which is already automatically set up there, in batch equals 128, which is what we have up here, shuffle equals false, and we're going to do 1,000 steps. So we're actually going to go through 128 batches, but we're going to do that 1,000 times. And we'll go ahead and run this. And I just ran an update, so it's going to give me some warnings because of that update. And then we're back here and it's still going. To construct pipelines, use TF data module. Not a big problem. We let it go ahead and run all the way through on here. And it takes it just a moment. There we go. There's our 1,000 coming out. As you can see here, here's checkpoints for 1,000, ongoing training, 1,001, global steps. And this is just all the reverse propagation going on. That's what we're doing here. One of the things we didn't cover is we do it in small increments. So it's not all done like one error goes all the way back. You'd only do a part of that error, and each one sends back a little piece, and so you slowly adjust your different weights going all the way back. And then if you're going to train your model, we want to know how it did. So we're going to do model evaluate. And our input function equals, remember our input function up here that we created? Way up here. We're going to take this input function, and instead of the data set that's coming in, we put in the data set here for training. Where's our training? Input train. There we go. df underscore train. Now we're going to go ahead and evaluate, and here it is, get input function test. So we're going to test the data out. Number of epochs 1. We don't need to rerun it more than once. Per batch 128. So on, shuffle, and steps 1,000. So we're going to go ahead and evaluate this. Let's just see how good our test data did, how good our model was programmed on our training data, and how it evaluates on the test. And we can see it going on down here where it's got the evaluating graph was finalized. Let me just highlight that. Ongoing model checkpoint, TensorFlow running local init, evaluate 100 out of 1,000, and so on. And once it gets to the end, we get a nice output here. We have an accuracy, in this case, of 0.79 with a baseline of 0.76. So now we've created a model. Let's go ahead and tweak it a little bit. So we have our accuracy up here. What we're going to do is we're going to look at age. And let's just go ahead and create a new square value for age. And the reason we want to look into the square value of age is we know that if you really look through the data, you'll find that as a young person, the age keeps increasing. And as you get close to retirement, it begins to decrease. So we square the value of age. And that's very data specific when we're looking at data. You'll find that any kind of data that has that kind of like uptick and downtick, by squaring it or square rooting it, you can get some very different results. And so we're going to go ahead and square our age. And this is kind of, it's interesting because at this point, even at the beginning of this, we're focused on deep learning and on TensorFlow. But before I would begin even looking at any of this, I would have probably run some kind of heat map or some kind of of evaluation in R or sklearn in Python to find out the correlation between different features, to see just how well they correlate to each other. And there certainly are some wonderful tools for that, because sometimes you can just mark off some features and other features you bring in. But for the deep learning, we can see how we can just dump it all in there and let it sort it out itself. And we're going to just write a quick little function here to take the square variable. In this case, we have dft, dfte. And this is our training and your test variable, and the variable age coming in. And we just want to go ahead and create a new under dft, and the new is going to be the variable name, whatever we put in there, which will be age. So let's load this. Here's our functions now loaded. And certainly we could have just done that as a line of code, but you start to get the feeling that when you build these functions, you might use it. You can now use this function if you had a number of different features that had this kind of quality to them. And we have our df train new, so we're going to create a new training and a new test, and it's going to equal the square variable df train or df test, and the variable name is age. Let's just go ahead and run that. And so now we have our df train new and df test new. And just like we did before, let's just double check the shape of our data and make sure it all matches. And when we look at the output here, really what's important is that each one of these has 16 features in it. We want to make sure we're not getting something weird on there. And our training set has 32,561 rows in it, and this one has just over 16,000 in there. And everything's pretty much the same, except that in our continuous features new, we now have the new column we put in there. So we need to change that. And we have our continuous features new down here, which we're going to load up with our TF feature column numerical. This would all look familiar because we just did this. And so we're going to load that up with the new being the new value in there. Let's go ahead and run that, and we'll create a model, but we'll call it Model 1. And this is the same that we did before, except now we have our continuous features new in here. So here's our new model, in this case Model 1 instead of model. And we're going to build that model right there. Now we haven't trained it. All we've done is told it where to get the data and how to get the data and what features are coming in. We haven't actually told it everything on the features coming in, because we still need to also build our get input function. So where's the input coming from? So we built the model with the features in it, and now we need to go ahead and create our get input function. This is the same as before, but you'll see we now have it with the data set coming in is going to be the same data set up here. And so if we scroll a little bit to the right, we should see the new. And there it is. Sure enough, there's our new on the right. And so let's go ahead and run that. Now we've defined our model. We defined where the information is coming from. And again, you can go back and review the first part, because this is identical that we did before, except now we have new as the column for the age. And we'll go ahead and do our Model 1, and let's go ahead and train it. There's our input function, get input function, that we defined up here. df train is going to be the same, and everything else is going to be the same. Let's go ahead and run that. And it should go through here and run the tensor info coming in. And it's going to go through, in this case, where we have steps 1000 shuffling. So it's going to go randomly, 128 per batch. And then the epochs is automatic. We're not worried about that today. So now we have a trained TensorFlow model. And with our new model, just like we did before, we want to go ahead and evaluate it. So it's the same setup we had before with our same get input function, with our df test new in here coming in. So there's our new data coming in. And this is really common when you're doing these models. You make little tiny tweaks to see if you can improve it. One of the best articles I read recently was you build your model to fail. You want a running model so that you actually have something to compare against. And then you continually tweak it till you get a better accuracy. Now, I don't expect the accuracy necessarily to get better on this because of the way we partition the data. But we can see here we now have an accuracy of 0.76, which is a little bit over the baseline. And it's about what I would have expected it to be, kind of the same. The reason is because we split the data at the people making over 50K and those making less. And so the age factor shouldn't be a huge factor. It would be if we were looking at more discrete buckets, like 40 to 50, 50 to 60, 60 to 70 when we create buckets. But in this, I didn't really expect it to go up that much. In fact, we could probably run it a dozen times, which would be very bad data science. And we see we actually had a slightly better one up here, but our baseline accuracy was 0.76. And we come down here, we still see, here's our accuracy baseline, 0.763. That didn't really change. And the accuracy didn't really go up that much. I could hit the run button a few times, and I would probably upbeat the one above. So not a big change, but that's all right. This is how we learn. This is how we go through and figure out what's going to work with our data and what's not. What's going to improve the quality of our data so we have a better prediction, and what's not. And we can now go ahead and utilize this model. This is where it gets exciting when you're actually working with somebody or with your clients, and you come in and you say, okay, here's my predictions. We're going to create a list, and we're going to use Model 1, and we're going to predict. And our input function is getInput function. df test new. Again, this probably doesn't make too big of a difference, but we'll go ahead and stick with the new data we created. Number of epochs 1, batch 128. So all this should look pretty familiar, but we're running the prediction. So we're going to load all our predictions into the predictions. And let's go ahead and run that. And you'll see it go through the TensorFlow setup. So it's running, done running local ops. And then let's just go ahead and print the df test new iLocation 0, so row 0. And we're going to look at the predictions also for the same location 0. Let's go ahead and run that. And we can see here that we have age 25, work class private. It has all the information coming in for that individual. And then it comes down here and we go ahead and get our prediction. And in this particular instance, there's our label 0. And then we come down here and we see, it takes a little bit for the setup to look up, but there's our array which also returns a 0. And it has information for us on there, probabilities, logistics on here. So you can see there's all kinds of additional information you can pull from this. And likewise, we could do it for position 3. Let me go ahead and run that. And what's kind of nice about this is you can now see here's label 1, and here's our logistics output. And again, we have to kind of hunt for it a little bit in this particular setup, but here's the output array, and there's our 1. And they match, label 1, 1. So we predicted for the very first one, location 0, that it's going to be a 0 on the label. It's going to make under 50,000. And the individual in 2, working class, private, whatever setup on here, capital gain, capital loss, etc., came up as 1, meaning they're going to make over 50,000. So we covered a lot. I mean, this is the basics, and you can see as you dig deeper, when you look at some of this code, let me just go back up here. We're way back up here at the very top, a little too far overshot. As we start working in here, we have 1, defining your features. And at this point, we didn't show this, but I would probably use either Python or R to show a relationship correlation, because they have some really easy packages in there to pull that up. So you can see what features are really connected and how they're connected. And then we showed you different features. Like we have ones that are integers, and then we have ones like sex that are objects. You're 0 or 1, you're male or female. You're same thing with race. Probably have just maybe 16 different races listed there. Ethnicities, things like that. Native country, again, that's, you don't have like infinite number of native countries. You just have a handful. So we look at this. We have our features. We looked at that. We have our continuous features like age, which is a number, or in this case an integer, and education number, how many years, and so on, along with your race, your sex, your relationship, which are just very abbreviated categorical data. So we looked at that. We went in there and we showed you how to, where was it? Here we go. We go back up here. So we create our model. The model knows what categories are coming in. That's really important. And this is probably one of the more complicated parts of this is our input function. And this input function is so important. So I want to just rehash the input function for that reason. This lets us know how we're pulling the data. It lets us know if we're going to go through all the data 20 times, or we're just going to let TensorFlow itself keep going until the training model reaches a point. That point is based on what they call bias. You can become biased on your training data. And so when it hits a certain point where it becomes overly biased to just that data, then it doesn't really work really good in the outside world. You start losing. You want to keep it generic, but as close as possible to the right answer. So generic answers for a huge amount of data. And then we have our batch size. Are we going to shuffle it, which we did. And then also our estimator inputs. So you have your estimator function here. And then of course where the actual data is coming from. So you can see all this is in that get input function. That's where a lot of the work comes in putting this together. And then we train our model. That's pretty straightforward. Once you have your input function and all your setup, training the model is quick. And then we go ahead and evaluate, and then we can go ahead and create a predict, and then look at our predictions and how they work on individuals. So it gives you a whole roundabout setup on here and how this is set up and how it's working. Certainly there are a lot more things you can do with TensorFlow. This is the basic TensorFlow, and it's always developing, so it's exciting. This is going to be one of the most exciting fields right now because it is really in an infant stage and just exploding in the market.
Today we are talking about must-have Python AI projects and how to build them so that can really help you sharpen your skills and stand out in the growing field of artificial intelligence. So let's quickly see what is Python. Python is one of the most popular programming languages for AI because its simplicity and the powerful libraries it offers, like TensorFlow, Keras, and Pytorch. Building projects using Python is a great way to get started if you want to break into the AI industry. Whereas artificial intelligence is transforming industries like healthcare, finance, and even entertainment. Companies are now looking for experts who know how to apply AI to real-world problems. In this video, we will explore beginner level to advanced level projects. So these projects are designed to give you hands-on experience in building intelligent systems, analyzing data, and even automating tasks. So without any further ado, let's get started. So let's start with beginner level projects. So number one, we have fake news detection using machine learning. So in today's world, fake news is a major concern, causing misinformation to spread rapidly across social media and news platforms. Detecting fake news is crucial to maintaining the integrity of the information we consume. So these projects aim to build a machine learning model that can identify fake news articles by analyzing their textual content, by learning from existing datasets of real and fake news. The model will be able to classify articles into these two categories, thus assisting media outlets and social media platforms in reducing the spread of misinformation. This project is perfect introduction to natural language processing (NLP) as it involves text data manipulation, feature extraction, and supervised learning. It can also be adapted for real-time use on websites or social media platforms to flag suspicious articles and provide more reliable information to users. So now let's see how to build this. In this, first step is data collection. Use dataset like LIAR or fake news net that can contain label, real, and fake news articles. You can find dataset from the Kaggle. The second step is pre-processing. Clean the text by removing stop words, punctuation, and special characters. Tokenize and stem words using NLTK or spacing. The third step is feature extraction. Use TF, IDF, or bag of words to convert the text into numerical data for machine learning models. The fourth step is model training. Train a classifier like logistic regression, naive Bayes, or random forest on the dataset. The fifth step is evaluation. Evaluate the model using accuracy, precision, recall, and F1 score metrics to determine how well it classifies fake and real news. Tools you can use is NLTK, Scikit-learn, and Pandas. Skills you will gain from this are text preprocessing, NLP, classification models. And if you want to make us video on this project, please comment down below. In number 2, we have image recognition using CNN. Image recognition is one of the core applications of deep learning and computer vision, used in a variety of industries ranging from healthcare to autonomous vehicles. This project will guide you through building an image classifier using CNNs, a deep learning architecture designed specifically for image recognition tasks. The goal is to create a model that can accurately classify images, such as differentiating between cats and dogs. By working on this project, you will gain a solid understanding of the fundamental concepts of CNNs, such as convolutional layers, pooling, and activation functions. This project not only introduces you to the basics of CNNs, but also teaches essential skills like image preprocessing, dataset handling, and model evaluation, which can be applied to more advanced computer vision projects in the future. So now let's see how to build this project. In this project, first you have to import dataset. So use a dataset like CIFR10 or Kaggle cats versus dogs with labeled images. The second step is pre-processing. Resize, normalize, and augmented images using libraries like OpenCV or PIL to prepare the dataset. The third step is model architecture. Design a basic CNN model with convolutional, pooling, and fully connected layers using Keras or TensorFlow. The fourth step is training. Split the dataset into training and validation sets and train the CNN model to classify images. The fifth step is model evaluation. Use accuracy, precision, and confusion metrics to evaluate how well the model predicts the correct class label. Tools you will use in this project are Keras, TensorFlow, OpenCV, Pandas. Skills you will gain after doing these projects are image preprocessing, CNN architecture, model evaluation. And if you want to make us video on image recognition using CNN, please comment down below. Second, we have intermediate level projects. In this first, we have AI-based recipe recommendation system. Recommendation systems have become an integral part of modern digital platforms. From e-commerce websites suggesting product to users to streamlined services recommending shows and movies. So in this project, you will build a recipe recommendation system that suggests dishes based on the ingredients a user has on hand. This project demonstrates how recommendation algorithms such as content-based filtering and collaborative filtering can be used to provide personalized suggestions. You will also learn how to pre-process data and clean textual data, such as ingredient lists, and implement a machine learning algorithm to match user inputs with recipe databases. This is an excellent project for understanding how recommendation systems work and how they can be applied in various industries, from food tech to personalized content recommendations. So now let's see how to build this. In this project's first step is data collection. Use web scraping tools like Beautiful Soup to scrape recipes from websites, or use datasets like Recipe1M. The second step is pre-processing. Normalize and clean ingredient data by standardizing ingredient names and handling missing values. The third step is recommendation algorithms. Implement content-based filtering and collaborative filtering to recommend recipes. Content-based filtering matches ingredient list, while collaborative filtering uses user preferences model. Fourth step is model training. Use cosine similarity to match user-provided ingredients with recipe ingredient in the dataset. And the next step is interface and tools. So create a simple web interface using Flask where users can input ingredients and receive recipe recommendation. Tools you will use: Beautiful Soup, Pandas, Scikit-learn, and Flask. So you will gain skills like web scraping, data cleaning, recommendation systems using this project, by doing this project. And if you want to make us video on this project, please comment down below. Number 4, we have chatbot with sentiment analysis. Chatbots have transformed how businesses and services interact with users, providing 24/7 support and personalized responses. In this project, you will build a conversational chatbot that can analyze the sentiment behind user inputs and respond accordingly. By incorporating sentiment analysis, the chatbot will not only understand the content of the user's messages, but also the emotional tone, such as whether the user is happy, frustrated, or neutral. This allows the chatbot to adjust its tone and responses to improve user satisfaction. For example, a chatbot could offer a more empathetic response if it detects a negative sentiment. This project will give you hands-on experience in building a conversational AI system while learning how to integrate machine learning techniques like sentiment analysis. The skills you develop in this project can be applied to customer service, healthcare, education, and more. So now let's see how to build this project. So before jumping to advanced level projects, in this project, the first step is chatbot framework. Use tools like Dialogflow or Rasa to build a conversational chatbot capable of handling various user intents. The second step is sentiment analysis. Integrate a sentiment analysis model using pre-trained models like VEDA or BERT. The third step is conversational flow. Adjust the chatbot's responses based on the sentiment, positive, negative, or neutral, detected in the user's input. The fourth step is integration and deployment. So build an interface, website, or messaging platform where users can interact with the chatbot in real time, and deploy the chatbot on a website or app, allowing user to engage with it and receive sentiment-aware responses. So you will use tools in this are Dialogflow, Rasa, Vader, Transformers, Flask, and you will gain skills like sentiment analysis, chatbot deployment, conversational AI. And if you want to make us video on this project, please comment down below. So now let's see some advanced level projects. In this we have AI-powered image colorization. Image colorization is a fascinating application of deep learning that transforms black and white images into color by predicting and applying realistic colors to grayscale images. This project explores how CNN and GANs can be used to learn mapping between grayscale and colored images. You will gather dataset of colored images, convert them into grayscale, and train the model generate color versions. This project is especially useful in areas such as film restoration, photography, and artistic creation, where colorization can breathe new life into old black and white images. Moreover, it highlights the power of deep learning in understanding and generating complex visual data, giving you insight into how these models work for tasks like image generation, video prediction, and beyond. The skills you learn in this project will also be useful for other creative AI applications like style transfer and image synthesis. So now let's see how to build this project. So in this project, first step is data collection. Use dataset of colored image, convert them into grayscale, and use the grayscale images as inputs while training the model to output colorized version. The second step is pre-processing. Normalize images pixel values and resize them for training. The third step is model architecture. Implement a UNet model or generative adversarial network (GANs), which are well suited for image generation tasks like colorization. Fourth step is training and evaluation. Train the model on grayscale images as input and colored images as output using mean squared error method for guidance. Evaluate with visual inspection and peak signal to noise ratio. The last step is deployment. So create a web interface where user can upload black and white images and get them colorized. So you will use tools like TensorFlow, Keras, OpenCV, and Flask. So we'll gain skills like deep learning, CNNs, JNs, and image preprocessing. And if you want to make a video on AI-powered image colorization project, so please comment down below. And the last we have object detection using YOLO. you only look once. Object detection is one of the most popular computer vision applications, allowing machine to recognize and locate multiple objects within an image or video stream in real time. YOLO is a state-of-the-art object detection algorithm known for its speed and accuracy. This project involves building a real-time object detection system capable of identifying multiple objects in images or videos feeds by drawing bounding boxes around them. Object detection has widespread use in fields such as security surveillance, autonomous driving, and augmented reality, where systems need to understand and interact with their surroundings in real time. By working on this project, you will learn how to pre-process image data, format bounding box labels, and train a YOLO model using a dataset like Coco or Pascal. You will also gain a valuable experience in deploying object detection systems that process video streams, giving you the skills to build application in dynamic environment, from traffic monitoring to industrial robotics. So now let's see how to build this project. So in this project, we will first import dataset. So use a dataset like Coco or Pascal VOC, which contains label objects in images with bounding boxes. The second step is pre-processing. Resize image and normalize pixel values, ensuring bounding box labels are appropriately formatted. The third step is model architecture. Use the YOLO, you only look once architecture, which splits images into a grid and predicts bounding boxes and class probabilities for each object. The fourth step is training and evaluation. Train the YOLO model on labeled data using a framework like Darknet. Evaluate the model using metrics like intersection over union and mean average precision. The last step is deployment. Develop a system that can process video streams in real time, detecting objects and drawing bounding boxes around them. Tool you will use OpenCV, TensorFlow, and Darknet. You will gain skills like object detection, YOLO architecture, real-time video processing. And if you want to make videos on this project, please comment down below. So in conclusion, these Python AI projects not only help you build hands-on skills, but also provide a solid foundation for advancing your career in artificial intelligence. Whether you are working on fake news detection, image recognition, or developing advanced tools like chatbots and object detection systems, these projects offer real-world applications that companies are looking for. Start small, keep learning, and as you complete each project, you will get better prepared to take on the challenges in the growing AI field. With this, we have come to the end of this full course. If you have any question or doubt, please feel free to ask in the comment section below. Our team of experts will help you as soon as possible. Thank you and keep learning with Simplilearn.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.